Hello everyone, welcome to this video. In this video, we will be discussing about haloalkanes and haloarenes, and that's the first topic we are starting with in class 12. As we know that organic in class 12 is extremely huge, so we have decided to start with the organic first. And the first chapter in your organic is haloalkanes and haloarenes. This chapter, part of it you have learned in class 11 GOC and hydrocarbon, and the rest part we'll be learning in this chapter. Okay, some parts you will find that it's very much related to what you have already done in class 11, and some parts will be new for you, and that's very obvious. That's nothing very unusual. Okay, so let us begin with the topic and let us understand what we have to read in the topic. So when we are dealing with haloalkanes and haloarenes, we have to understand preparation of haloalkanes, haloarenes, physical property, chemical property. These are the three vast topic that we are going to read. At the end of the chapter, you will find there is a small topic that is called some important haloalkane like chloroform, carbon tetrachloride, freons. That part will be taking up at the last of the chapter. That's not very important, but JEE is giving questions on that in recent years. Okay, so let us begin. First part is very basic part, and that is just for building your concept, and it's not really going to be asked, but the concept is going to be used everywhere where you go. Okay, so first let us begin with the classification of haloalkanes. The classification of haloalkanes, just give me 1 minute, let me just change this. Okay, so we will begin with the classification of haloalkanes. So heading, let us put classification. Now this is very basic. You can classify on basis of what? On basis of shape, size, structure, number or something. So here we will be classifying on the basis of number of halogen atoms that has been attached to the alkane. So based on, so I'm writing here in bracket basis, because basis is very important. Basis number of X atom. Now let me tell you, I will be using few few abbreviations very often. That is X for halogens, R for alkyl groups, Me for methyl, Et for ethyl. So please, make sure that you are accustomed to it, because every time it's not possible for me to write halogen. I'll be using the symbol X and I'll be using the symbol R for methyl groups. Not only methyl, ethyl also, but R means any alkyl group. If I have to specify, I will specify. If not, you have to understand. Okay, so please remember that X atom is halogen atom. I'm mentioning over here. Next time onwards, I will not mention halogen. Okay, so basically we will be classifying into very simple monohaloalkane or monohaloarene. So monohaloalkane or haloarene. So monohaloalkane / monohaloarene. Now mono means one, so automatically there will be only one halogen atom attached to the chain, right? So example, write down CH2Cl, CH3Cl, or another one that is aromatic. This is, hopefully you can do the nomenclature part. I will be not dealing with, because that already has been done in GOC, very details. So nomenclature, go back to GOC. Around 3 hours I have taken for explaining the nomenclature. Please watch the GOC lecture. Okay, so monohaloalkane, monohaloarene, for example each I have given. So what does this mean? This means one halogen atom present. So I am writing over here one X atom present. Okay, very simple, very easy. Only one X atom present means that is going to be a monohaloalkane. If not mono, then what? Dihaloalkane. That can be dihaloalkane, dihaloalkane / dihaloarene. Okay, dihaloarene. So what will be the example? Very simple. Again, CH2Cl2 / this time one, second time another, Position you all know, ortho, para, meta, though I will telling you that about later on. This is ortho, okay. This position is meta and this position is para, okay. Alright. So dihaloalane, understood? So what will be the point to note? Two X atoms are present. Right? If one X atom present, then it is monohaloalkane. Two, then dihaloalkane. If not two and one, then what? More than two and one, then that is going to be the polyhaloalkanes. If we sit counting how many halogen atoms are there, then our entire they will go. So we have classified the further orders, that is the higher orders, as polyhaloalkane. Polyhaloalkane. Now that poly can contain any number of halogen atom more than 2. So polyhaloalkane or polyhaloarene. Polyhaloarene. Okay. So that can be like chloroform CaCl3. Then it can be Cl, 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 Cl. This compound will be using somewhere in some reactions you will find. Okay, alcoholic carriage treating with this compound will give you 1,3,5 trichlorobenzene. That I will be discussing whenever it is needed. So understood. See here 6 chlorines are there. It's a polyhaloalkane. This is 3 chlorine is there. That is also polyhaloalkane. So this means what? More than 2x atom. More than 2 halogen atom. More than 2x atom present. Got it? So this is a very basic thing. We have classified haloalkanes, haloarenes into 3: mono, di, poly. Done? No doubt? Very good. Next. Clear? Now, this dihaloalkane can be classified into further 2 types, and that is very important because many a times that common name is used. Okay, so let us discuss about dihaloalkanes 2 types. Okay, Acha. Heading is dihaloalkane. Okay, possible for alkanes only, not for arenes. Okay, now you see, example I had taken was CH2Cl2. Now this is only one carbon is present, so there is no problem with that, right? If there is only one carbon, then the chlorine will be attached to the same carbon only, so I have no problem with that. But the problem arises if I am taking at least 2 carbons. Suppose I am taking an example of dihaloalkane as C2H5 C2H4Br2. Okay, this is a dihaloalkane, correct. Now if I want to draw the structure of dihaloalkane, then how will I draw? If I am writing CC and CCl, so I can write 4 hands of carbon, so 4 hands of carbon. Now I can write hydrogen, hydrogen, hydrogen. I can write bromine, bromine, hydrogen. Or instead of this I can write hydrogen, hydrogen, bromine, bromine, hydrogen, hydrogen. Now you see, both of them are same thing actually. Both of them are same thing, but they are written in different way. On one thing you can see bromine is on the same carbon, both the bromines. Other case, 2 bromines are on the 2 adjacent carbon. So are they something different? Yes, they are something different structurally. They are isomers, but that does not indicate that they are different compounds. The molecular formula is same. Clear? So you can represent this compound in 2 different ways. That is either this way or this way. Now which one is correct? That is the question, is which one is correct? Both are correct. Both are correct. So we have given both of them certain names. Remember, in geography you might have learned the term vicinity. Vicinity means nearby. Nearby, like India is in vicinity to the equator. That means equator lies very close to India, or India lies very close to equator. So we can say that India is in vicinity of the equator, or in vicinity to the equator. My English is not that good, so it might be a wrong preposition used, so I apologize. So it is in vicinity to the equator, means we are very close to the equator. So you can see the two bromines are very close to each other. The two bromines are very close to each other, so they are in their vicinity. They are in their vicinity. So if two bromines, if two halogen atoms are present on two adjacent carbon, we will call it as vicinal dihalide. Remember, we will call it as vicinal dihalide. Vicinal dihalide. Clear? How will you remember? Just now I told. Two bromines are very close to each other, so they are in their vicinity. One bromine is in the vicinity of the other. So it will be a vicinal dihalide. Then what about the first one where both the bromine are on the same carbon? Then it will be a geminal dihalide. Okay, this will be a geminal dihalide. Now spelling somewhere you will also find Z, like this, ZEMINL. Okay, I am writing both, but I prefer geminal, G. Okay, geminal dihalide. So did you understand that when two bromines are present on adjacent carbon, we will call it as vicinal dihalide because they will be present on in their vicinity. Then same applies for alcohols as well. Vicinal diol is possible, but geminal diol is not possible. That I am not going to explain now because next chapter is alcohol, not now. Okay, so this is vicinal dihalide. So remember, the vicinal positions are adjacent carbons. Okay, and geminal is on the same carbon. Clear? Now how to name this? When vicinal dihalide is named, then the common name, not IUPAC name. IUPAC name everyone can do. IUPAC name I don't want. IUPAC name you can also do, I can also do, everyone can do. What is the common name for vicinal dihalide? Because they will be using the common name. The common name for vicinal dihalide is alkylin. Alkynyl. Alkylin dihalide. Alkylin dihalide. Clear? So common name. That's a common name. Sorry, common name. So if somewhere you get alkylin dihalide type of name given like methylene, not methylene, not possible, sorry, propylene dihalide. Let's say propylene dibromide. Then in that case you have to understand that it is talking about a vicinal dihalide. Okay. Now what about geminal? Geminal must also have a common name. Yes, it does have. So the common name for geminal does not have a halide, dihalide in its name. It is alkylidin halide. Alkylidin halide. This is the major difference. What is the difference? Dihalide I am mentioning in the name. In case of geminal, no dihalide I am mentioning in the case because both the halogens are on the same carbon. Clear? Here there is a vicinity, so I am mentioning dihalide. In case of geminal dihalide, there is no dihalide. We will write it as halide only. So the name you can see is different. In case of geminal, no dihalide we mention in the common name. We will write alkylidin halide. But in case of vicinal dihalide, we have to write dihalide in the name. Alkylin dihalide, propylene dibromide, ethylene dibromide. So this type of things will come up. Okay, propylidin chloride. Then what? Geminal dihalide. Clear? Understood? Doubt I don't think you all have. Right. Let us move on. Next topic. See, the first part you will easily understand because this is very easy ones. Okay. Okay. Now, CX bond. We will be studying about different types of CX bond. sp3, sp2. sp is also possible, but we generally don't talk about sp much. Okay. SP, I think it is mentioned in the book, but I am not giving SP. SP, you know, is directly connected to the triple bond. Even if you read it, you will be able to understand. So that's not a very difficult thing, I think. But I'll just tell you, okay? I'll tell you. CX bond. First one we are going to discuss about is sp3 hybridization. Hopefully you all remember what is hybridization, right? So sp3 hybridized CX bond we are going to study. Under that, the first thing we'll be studying is the haloalkanes. The haloalkanes. Haloalkanes, another name we have that is called alkyl halide. We'll see methyl chloride, ethyl chloride. So these are what? These are nothing but haloalkanes only. So we will call it as haloalkane or alkyl halide. Now whatever I have told you till now, they were all haloalkanes. Like suppose your example is CH3CH2Br. Do you see any double bond? No double bond present, so it can never be sp2 or sp, it has to be sp3. Right? So this carbon is also sp3 hybridized and this carbon is also sp3 hybridized, right? Because there is no double bond. Two hydrogen single bonded and two on this side. So 2 plus 2 4. 4 means sp3 hybridized. That also you know, steric number you will find out, then we can find out the hybridization. That much you have done in chemical bonding already in class 11, right? Right. Now come to the second one. This is the haloalkanes or the alkyl halide. What is the next one I will be discussing is about two important parts that often is asked: allylic halide and benzylic halide. Allylic halide and benzylic halide. So let us write allylic halide. Allylic halide. You know what's an allyl group? You know what's an allyl group? Maybe you don't, so let me say allylic halide. Allyl group is, suppose it is CH3 CH2 double bonded, no sorry, CH double bonded with CH2. This is an allyl group. This is going to be called as allyl group. Okay. Now instead of one hydrogen from here, this hydrogen, one hydrogen if I remove and I add a Cl, then I will be calling it as a allylic halide. Simple, clear, simple thing. Allylic halide means the halogen atom will be attached to the carbon just adjacent to a double bond. So you can see just double bond wala carbon তাকে ছেড়ে পড়ার কার্বনটাকেই halogen atom জুড়ে বসে থাকে, that is called allylic halides, right? So what you have to note it, you have to note that X atom is linked to the carbon next to the double bond, Acha, understood? So whenever it is an allylic halide, the halogen atom will be attached to the carbon that is just next to the double bond. No doubt, right? Very clear, simple. Okay, next number 3. Number 3 is allylic, then comes benzylic halide. See, allylic halide in arene system is benzylic halide. What did I say? Allylic halide in aryl system is called benzylic halide. Now aryl system means that conjugated system, right? And that means only benzene we have in our syllabus. So benzene. So aryl system, benzene. Okay. So just this allylic system in benzene will be called as benzylic halide. So how does it exactly look? Let us understand. We have a benzene. See, this carbon is connected to the benzene ring carbon and to this carbon. So let me show the carbon to this carbon is having CH3. This we call it as toluene. So one hydrogen I have removed from the toluene and I have added a chlorine. Then what is this called? This is called benzylic chloride. It's called benzyl chloride, not benzylic chloride, but benzyl chloride. Okay. So where will the halogen atom be attached? Halogen atom will be attached to the carbon directly attached to the carbon of the benzene ring. Clear? So X atom will be attached to the carbon which is directly attached to the benzene ring, but it will not be attached to a carbon which is a part of the benzene ring. That is very important. Attached to a carbon which is directly attached to a benzene ring, But again, what did I say? That this chlorine will not be attached directly to the benzene ring. Then it is not a benzylic halide. Understanding? Then it is not a benzylic halide. It will be called a aryl halide. That I am coming. That will be called aryl halide. So if it is a benzylic halide, then the chlorine will be attached to the carbon which will be attached to the benzene ring. Clear? But it is not a part of the benzene ring. That carbon won't be a part of the benzene ring. Okay? Clear? Concept clear? Next. CX bond sp2 hybridized. CX bond sp2 hybridized. sp2 hybridized. Well, first one we are going to study under this category will be vinylic halide. Vinylic halide. Vinylic halide. First let me explain, then I am going to give you the definition for vinylic halide. Suppose we have CH2 double bonded with CH2. This is called ethylene. No problem with that. Right. Now if I remove one hydrogen and instead of that hydrogen I add up chlorine. Let me show the bonding this way. Okay. Either ways. This side also, this side also. Either of the way. Okay. Then the chlorine is attached directly to a carbon which is double bonded with another carbon. Then this carbon's hybridization is sp2 hybridized. Steric number calculate, you will get sp2 because one sigma bond there, one sigma bond with hydrogen, one with chlorine, so it is going to be sp2, right? Steric number 3, so that is sp2. So this carbon is sp2, so chlorine is bonded to an sp2 hybridized carbon that is directly bonded with double bond. So this type of thing is called vinylic. This type of system is called vinylic halide. So what can we write? X atom is directly linked to a sp2 hybridized carbon linked to a C double bonded C. Clear? Understood? Okay, clear? Or in better words, if you want to write, X atom is directly linked to a CC, or you can write bonded to a sp2 carbon atom of CC bond. This will be better. Okay. X atom will be directly linked to one sp2 hybridized carbon atom that will be a part of the double bond system. Vinylic halide, clear? So we have learned about three types of halide as of now. The major ones. Allylic halide, where we have seen that just the carbon next to the double bond it will be attached. In case of benzylic halide, we have seen it is benzyl system. To the benzyl system, the directly attached carbon, there one hydrogen substituted and chlorine has been attached. Now for vinylic halide, we are seeing that directly to the double bond only the halogen atom is being attached. Clear? So the next case and the last case that we are going to discuss over here is the aryl halides. Aryl halides. Okay. What is aryl halides? Just now when I told you here that this chlorine should not be directly bonded to the aryl system. If it was directly bonded to the aryl system, then it would have been called as aryl halides and not as benzylic halide, because the hybridization number remains sp3. Okay. So example, if you want to see, then see this is this way. This carbon is sp2 hybridized because double bond is there, no? Then what? Does it fall under benzylic halide? No. That is what I am saying. The chlorine will not be directly attached to the benzene because it is not a sp3 hybridized carbon. Clear? So allylic halide, this will be directly bonded to the benzene ring. So X atom directly bonded to the benzene ring. X atom directly bonded to the benzene ring. Directly bonded to. Instead of benzene ring, I can write aryl system. That is aromatic ring. No doubt. Aryl halides, X atom directly bonded, benzylic, leaving one carbon it is attached because the carbon is directly bonded but not the halogen. If the halogen is bonded, there is aryl halide, not a benzylic halide. Clear with the different types of halides? Okay. Clear with aryl halides? Any doubt you are having? No doubt, I think. If you have doubts, you can tell me. No problem is that. Okay. Now if that's an sp hybridized carbon, then you can understand it will be directly bonded to the sp. Like they're like this. Clear? So sp, I don't think I have to say you anything about sp, that you can read. Okay, so I'm not saying about sp, but sp is also possible because at least one hydrogen can be replaced. Okay, but that is usually difficult because it usually undergoes addition reaction. You know that. Okay, next thing we are going to discuss about is the method of preparation. Acha. In your book, you will get a small portion, that is nature of CX bond. Now, what is the nature of CX bond? You all know already. That is, it is a polar bond. It has to be a polar bond because C and X difference electronegativity is heavy. It is huge. So, CX bond of alkyl halide is polarized. So based on that, certain observations have been made, like it can be, I'm mentioning just what can be asked. We make a box. Just you have to memorize this. I don't think you have to memorize even, because brain you have. So suppose the order is asked of bond order. Bond order. Okay. Achha. Not bond order, sorry. Not bond order is what? Same for all. Why bond order will change? Achha. Suppose it is bond length. Achha, what is bond length? First tell me. Bond length means the distance from the nucleus of one atom to the nucleus of another atom, right? Which are together in bonding, right? So if I ask you the bond length order of CH3F, CH3Cl, CH3Br and CH3I, who do you think will have the greatest size? Even if you use a little bit of your common sense also, then your common sense should tell you excuse me, that I minus has great size, huge size. So if it is having huge size, then automatically the size will be more. Automatically the size will be more. So bond length will be proportional to what? Proportional to the size of X atom. Proportional to the size of X atom. So that means CH3I should be the largest, followed by CH3Br, followed by CH3Cl, followed by CH3F. Do you need to memorize this? Do you need to memorize this? Why? Why do you need to memorize this? Chemistry is not always done by memorizing. Yeah, some parts it's okay. Physical, okay. Inorganic, so you have to memorize more. It's not the point. Organic, what will you memorize? Yeah, you have to memorize the reagents used, name reactions, and I will tell you what to memorize and where required. This is not required. And this is moreover a question of chemical bonding, not a part of organic. Okay, clear? Next, if I ask you another parameter, let us say bond enthalpy. Bond enthalpy. Bond enthalpy means the energy required to break a bond. That is also called bond dissociation energy. So now tell me, what will be the bond dissociation energy order? Again, you have your common sense to use. Check out the previous one, bond length. Length is this much. How much energy do you need to give to break this much and this much? This much, give small energy to break, but this much you need to give greater energy. You have read conduction in physics, no? You take a spoon and you keep it under the flame. From there, you will find your hand is also getting, you cannot hold it after a certain point of time. Why? You are not hitting this part, you are hitting that part. Then how come it is coming over here? Conduction is happening. So more will be your length, the greater time it will take to come. That is your experience. You take a long one and a small one. You take a khunti and a chamuch, which will be conducting, provided the material is same. The spoon will be doing it fast because the length is less. Right. So energy will be required to break CH3I bond more. Why? Because the size is more. So what can I say is bond enthalpy is inversely proportional to bond length. More will be the bond length, less will be the, okay. Very simple. More will be the bond length. More I have to keep the bond enthalpy. Clear? Understood? Right? So the practically you have to think. Practically. Simple. Be practical. Longer khunti you take, smaller spoon you take, which will be conducting faster. That much you can know already. Right? Right. But this is chemistry. That is physics. So in chemistry also you have to think. CH3I is this long, so you have to give it energy. How much energy will give it? Longer distance, give energy breaking. And CH3F is only this much, so you have to give more energy. CH3F is only this much, so you have to give it more and more energy to break, because smaller distance means force will be more, so automatically you have to give more energy. Okay, ignore what I said before, that was a little bit twisted and it was wrong. Okay, listen again. Forget what I told. Listen again. You have this long molecule. You have this long molecule, CH3I. This much long molecule. Force from here to here, what will happen? Decrease or increase? Decreased. So little bit energy I will give, it will break. So CH3I is supposed to have the least bond enthalpy. Correct. CH3F is only this much. Only this much. So force between this and this is bhayankar. So I need to give more energy. Right? So more energy. So who will have the highest bond enthalpy? Mr. CH3F will have the highest bond enthalpy, followed by CH3Cl, followed by CH3Br, followed by CH3I. Okay, don't listen to my first one because that I made a little bit error. It was my error. Okay. Last one I will be talking about is dipole moment. So what is a dipole moment that you have studied in the physics dipole moment? So please don't tell me the definition of dipole moment now, because we are not reading physics, we are reading chemistry. What is the order of dipole moment for this? That also you have learned in chemical bonding, that there is an exception standing up here, right? CH3Cl greater than CH3F, though it was supposed to be CH3F greater than CH3Cl, but due to the electronegativity difference, right? This electronegativity difference is higher. Still CH3Cl is more than CH3F, greater than CH3Br, greater than CH3I. Clear? Gone? Done? This you have to just read. I have not said to mukhsto because automatically it will get into your brain. Alright, now we are moving on to the most important part of this chapter, that is going to be your method of preparation. Method of preparation. Method of preparation of haloalkanes. Method of preparation of haloalkanes. Now, question won't be asking you write down the method of preparation of haloalkane because you are in class 12 and those stupid questions won't be asked to you. But what will be asked is reactions will be given. Either it will be given in the form of complete the reaction, or it will be given in the form of conversion reaction, or it can be 1 or 2 marker directly, like what happens to you when you react toluene with chlorine in presence of FeCl3. That type of short questions can be asked, right? So for that we have to read the chemical reaction, we have to read the method of preparation, then only we can solve, because physical property to reaction is not there. Clear? Now please listen very carefully, otherwise nothing will get into your head. Nothing will get into your head, okay? And don't dare to memorize the reactions. Byproduct you can memorize, don't dare memorize the reaction, I'm telling you, because little bit changes in the reagent will be made, then you will be falling on the sky. Okay, because always the same reaction is not necessary to come in the exam. Little bit changes can be made, and for that you need to know that how will the answer change for that, right? So let us begin with method of preparation. Listen to me, you can understand. Okay, Acha. I will be telling you mechanisms whenever and wherever required, but the mechanisms are not included in your ISC syllabus. In your ISC syllabus, mechanism is not included, but for JEE it is. Mechanisms won't be asked, but questions which will be based on the mechanisms will be asked. So without mechanism, I don't think it will be very clear for you to understand. Okay. And mechanisms are not very difficult for you to understand, and if you are not able to understand for ISC you can skip it, but for JEE you need to know the mechanism, because certain cases you cannot do the questions, especially in the rearrangement cases. Okay, so let us start. Method of preparation of haloalkanes. Firstly we are going to see that using alcohol how will we prepare haloalkane. From what? From alcohol. So number one, we are going to see from alcohol how will we prepare this. From alcohol. From alcohol how will we prepare. From alcohol we can prepare this by using around 3-4 processes. Okay. Around 3-4 processes we are going to use. So let me just give you a summary of those. Suppose you have an ROH, that is an alcohol. R is an alkyl group, already I have defined you. Okay. You have around 4 processes. Achha. First one I can use is a HX. What is HX? HCl it can be, HBr it can be, HI it can be, but when I use HI, I have to use HiO3 as well. Whatever. So ROH, HX, then what I will get? Alkyl halide. And there will be a byproduct as well that I will be discussing when I am going to do the reaction. Alkyl halide. Achha. Now instead of HX, I can give suppose PX3. That will also give me alkyl halide. That will also give me alkyl halide. Achha. I don't want to use PCl. PX3. I can use PCl5. That will also give me alkyl halide. That will also give me alkyl halide. Right. I do not want to use PCl5. I want to use thionyl chloride SOCl2. That will also give me alkyl halide. I don't want to use only SOCl2. I want to use SOCl2 along with pyridine. Along with pyridine. That will also give me alkyl halide. No problem. What is the difference actually? If I am using only SOCl2 or I am using along with pyridine, difference I will be telling you when I am going to do the process. Okay. Remember, these last two processes are called Darjan process. Are called Darjan's process. Okay. This is Darjan's process. SOCl2 in presence of pyridine or not in presence of pyridine. Okay. Clear. So you can see I have given you a basic gist of what we are going to discuss about under alcohol. Now you have to read the reactions. If you just go for memorizing this reaction, you cannot do. I am telling you. Maybe in ISC you can, but not in the competitive exams, or maybe in ISC also you may not be able to. Okay. So let us discuss in details about the reactions. So first let us discuss about reaction with halogen acids. Reaction with halogen acids. Reaction with HX. So first let us know about the basic funda. What is the basic funda? ROH is there. We have HX reacting. Basically what you have to do is just throw this out. Throw this person out. So what you are going to get is you are going to get a RX and you are going to get a H2. Oh, what is this? Very easy. No, it's not that easy you are thinking. Okay. Achha. So when I am reacting ROH with HX, I am getting RX and water. So byproduct is my water. That is no issues with that. But where is the issue that is coming up is when there is a possibility of rearrangement. So questions on rearrangement is not supposed to be given in ISC, but in JEE all are rearrangement based questions. So what will you do there? You have to know rearrangement. Okay, so let us just discuss about the mechanism of this reaction. Mechanism of this reaction. Okay, we'll just brief you about the mechanism of the reaction. ROH I have, no doubt. Right. Do you know that oxygen has lone pairs? Yes, it has lone pairs. So it has got two lone pairs. And I am going to use only one, not two. Oxygen is not very loyal. It will give only one electron pair. Okay. Achha. I had HX dissociating into H plus and X minus. Right. H plus is a mad person. You know, he is a mad person. Why he is a mad person? কেন পাগলা? ও পাগলা কারণ ওর কাছে কোনো ইলেকট্রন নেই. He does not have any electron, so he is mad for what? For electron. And oxygen is sitting here, very doyalu মানুষ. So what it will do? It will say hydrogen, come here, I am giving you electrons. So what this oxygen will do is, it will give this hydrogen its pair of electrons. So oxygen shifted its electron to hydrogen. Okay, hydrogen is very happy. Hydrogen says, oh thank you, I am coming to you. Thak kore ke bonding made. So R O H lone pair, another one is left H. Now someone giving electron will be developing a positive charge, and whoever gaining electron will develop a negative charge. But here hydrogen already had a positive charge and it will gain a negative charge, so it is ultimately neutralized. Clear? So oxygen develops a positive charge. Very important. Oxygen develops a positive charge. This step is called protonated alcohol. Protonated alcohol. Because you can see I and alcohol was there and a proton entered. So this is called a protonated alcohol, right? Achha. Now remember, oxygen is a very electronegative element, a very doyalu manush, but a very electronegative element. It does not like a plus charge on itself. So whenever a plus charge comes on oxygen, oxygen's, what is that called? Blood boiling starts. Okay, oxygen's blood boiling starts. Oxygeনের মাথাটা যায় খারাপ হয়ে. So what does oxygen do is it starts taking a pair of electrons from side লোকজন. Now hydrogen to it cannot take. Why it cannot take from hydrogen? Because hydrogen কিন্তু এক্ষুনি ইলেকট্রন দিয়েছে, আর দিয়ে আবার নিয়েও নিল, তাহলে হাইড্রোজেন তো হিবি লাইক গিলে কেন নিলে কেন, হাইড্রোজেন তো ভিখারি হয়ে যাবে, ছিলই আগে ভিখারি, রাইট? So oxygen is again a honest person. Now আমি হাইড্রোজেনকে ইলেকট্রন দিয়েছি, I will not take electron from hydrogen, I will take electron from this person R. আর আমার সাথে আরেকটু বন্ডেড আছে, I will take electron from R only. So in reaction with HX, the OH bond does not break because OH bond was just newly formed. Okay, OR bond will break. So oxygen, to shanto itself, to calm down, what it will do is it will take this electron pair. It will take this electron pair. Bas. Take it. So what will be the next step following? R will develop a positive charge on its head now because R is now lacking electron. So R will develop a positive charge. R now does not have an electron. R এর মাথায় উঠে গেল positive. Moment the oxygen gets electron, it forms H. কি লিখছি? It forms OOOH. What is this? This is nothing but water. This is nothing but what? Water. So water is already formed. Then what about the R plus? What about the R plus? The R plus will be moving around here and there. Yes. Achha. Boys go behind whom? Girls. Boys go behind girls. So whom will plus go behind? Minus. So who is the minus person here? That X minus. Who is also moving to search for a plus. So this R minus will find an X minus and they will ultimately form the Rx. Got it, everyone? So what is the intermediate being formed over here? Carbocation is the intermediate, and in carbocation shifting is possible. Shifting is possible. So if shifting is possible in the carbocation, that means rearrangement possibility rises. Rearrangement possible. Tick mark. Rearrangement possible. Because the carbocation intermediate is formed, the classical carbocation is not formed. It's a non-classical carbocation. So that is going to be a rearrangement possible. Sorry, no, classical carbocation. So that's going to be a rearrangement. So there's going to be there. If there's any, there will be. Okay. So did you understand what exactly is happening? So again I'm explaining. ROH, oxygen has two pairs of lone pairs. Two pairs of lone pair electrons. So if it is having that, hydrogen, that is a proton, H plus, it is searching. It is literally mad for electrons. Oxygen is a very doyalu manush. So what it will do is it will give one electron pair to hydrogen. Say, amar kache esho, I am giving you electrons. Given electrons. So H is very happy, bonded to oxygen. But oxygen er mathata kache kharap hoye. Oxygen has now gone mad. Why? Because oxygen has developed a plus charge. So what oxygen will try to do? He will try to recover his losses. He will try to recover the loss. So he will recover the loss from whom? From hydrogen? No, because hydrogen, he has given thing. Why will he take the thing from hydrogen? He has just given and he will take the thing. Then what is his advantage? Everyone has to think about the advantage. You can see even in real life we think about our advantage. Here even in chemistry the compounds, the atoms think about their advantage. So oxygen won't take from hydrogen because it will have no advantage. What will it do? Alcohol will be formed back. So what is the use of doing? So oxygen is also having a brain. So it will be taking the electron from R. So ultimately water will be formed and R positive because R is now lacking electrons. Positive will search for negative. So X minus will find R plus and R plus will find X minus. They will form a bond Rx. Clear? So this is the first method of preparation, that is reaction with halogen acids. So there can be any acid. It can be HCl, then it will be RCl. If it is Br, then RBr. I have shown the general one. Now with variety of example, it will be given to you in the question paper. And in the question paper, the general format will not be given. There will be a reaction given. The reaction to complete, it will be given to you in the question. Clear? So you have to identify the reagent and understand. If it is given an alcohol and on the arrow mark it is written HCl, then you have to immediately understand it is a preparation of alkyl halides going on. Clear with the thing? This is the first reaction. Understood? Now the thing I can tell you is, basically it might be asked in JEE, if it is asking you for the rate of reaction, like it is giving you three different um, compounds and they are asking you which one will be more reactive with HX, then in that case you have to compare the carbocation stability. Carbocation stability you have compared in case of class 11 GOC. Similar way you will be doing. If it is the electron withdrawing group, then carbocation is becoming more mad. It is already mad, you are making it more mad by taking in more electrons. So automatically if it is electron donating group is present, it will be more happy. It will be happy. So electron donating group will increase the stability. So carbocation stability comparison, I think you all can do. Okay. So rate of the reaction will be proportional to carbocation stability. Rate of reaction will be proportional to carbocation stability. Carbocation stability. Right? Acha. This is the RDS. RDS is rate determining step. Let me write it once. RDS is rate determining step. Rate determining step. Okay, RDS is rate determining step. Now you tell me, is it clear? Achha, now I'm going to tell you one important thing. Achha. Suppose I have taken CH3OH reacted with HX. I have taken CH3. This is CH3OH. Okay, I have taken CH3CH2OH. Let me not write this on. Wait. I have taken CH3CH2OH. CH3CH2OH in presence of HX. I have taken CH3CH CH3OH reacted with HX. I have taken CH3 CCH3 CH3 with OH and reacted it with HX. If I ask you which one will give me the product of fastest or which one will be the most reactive, what will be your answer be? You can pause the video and think and tell me the answer. I think you have already said the answer, so let me say. As I've already told you that the rate of the reaction is proportional to the carbocation stability. Carbocation. So which degree carbocation is most stable? 3 degree. So this will result in the formation of a 3 degree carbocation. Correct or not? This will result in the formation of a 3 degree carbocation. This will result in the formation of a 2 degree carbocation. 2 degree carbocation like this, and this will result in the formation of only 1 degree carbocation. So which one is more stable? This one is more stable. So automatically the third one, which is a tertiary alcohol, becomes more reactive than the secondary than the primary. So did you understand that why the third degree alcohol is most reactive? Why? Because the carbocation formed in this case is the maximum stable, and rate of reaction to carbocation stability already told to you before, right? Because RDS is the rate determining step and rate of reaction depends on the RDS only. Okay, so I will write 3 degree alcohol greater than 2 degree alcohol greater than 1 degree alcohol. Okay, these are the observations that you can make out reactivity. Okay, clear with this? Clear with HX? Any doubt till HX? Clear. I don't think there should be any doubt. Achha. One more question I have, that what is going to be the reactivity order of the halogen acids? What is going to be the reactivity order of halogen acids? If you remember, I have told you that which bond breaks easily. That is why before starting with this, I have discussed this length. Which bond breaks easily? CH3I breaks very easily. That's why it is last. CH3I breaks very easily. You can see that here HX has to be broken down. So who can be broken down easily? HI. So who will be more reactive? HI. See, everything you are doing by common sense. Nothing you are copying and pasting. So if I have to talk about the reactivity order, then I can also say that HI greater than HBr greater than HCl. Okay, HF2 we will not use only due to explosive nature. So HF has no work over here. We will not be using HF due to its explosive nature. So small things matters. Okay, this might seem very small, but this is actually something important. Acha, clear with this? Understood? Why HI? Because HI has to be broken down, and HI can be broken down very easily, that we have seen in the previous page only. Right? Clear with this? Any doubt you have? Oh, fine. Acha. Let me just give you a question. Acha. Suppose you have CH3, CH, CH3, CHOH, okay, plus, acha, no, another one is right, CH3, okay, and you are treating it with HBr. Now, what is going to be formed? Please pause the video and try to do it. Try to do it. Okay, I hope you have already tried it. So now let's solve it. So as I have told you with the mechanism, suppose you don't know the mechanism, what would you do in the examination hall is simply you are going to form an RX, you are going to remove the water. So water you will be removing. So from where will you remove the water? This oxygen, this OH and this H gone. So you will be attaching the Br in this position. As you have seen over here, the R and X is joining up. So here you will attach a Br. So if you do not know the mechanism, then your answer is supposed to be methyl CH, methyl CH, Br, methyl. Achha, me means methyl, huh? That much also you should know. Me means methyl, ET if I write anyway, that is ethyl. Okay, achha. So me, that is methyl. So this should have been your answer if you do not know the mechanism. But this is a minor product and minor products are not to be written. Okay, marks are not given for minor products. For major products only the marks are given. This is a minor product. So this is not the answer. Then how and what is the answer? That is why I have taught you the mechanism so that you don't make any error in the question. What was the intermediate that is being formed? The intermediate that was being formed was basically a carbocation. So first of all, form a carbocation. So let us form a carbocation. CH3, CH, CH3, CH, positive carbocation form CH3. Correct? So this is a carbocation will be formed because OH minus will be removed, carbocation formed. Gone. Water formed. No problem. Here I will write minus water. Done. Now what next? Or let me write here only plus water now. But what next? Directly here this beer will come and attack? No. As I have already told you here, most important, this case. What is this? Rearrangement is possible in case of carbocation. What is rearrangement? Maybe you all do not know about rearrangement. Basically, carbocation will be shifting to that position now where plus is more stable. That means where it has more alpha hydrogen available. So you can see where the plus is currently there. How many alpha hydrogen is possible? Only 4 alpha hydrogen, right? But if I am shifting the plus over here, how many alpha hydrogen? 3 plus 3, 6 and plus 2, 8 hydrogens. This hydrogen will also shift over here only. So there are 8 alpha hydrogen present. So which will be more stable? This one. So the carbocation will be shifting from here to here. And this is only possible for carbocation, not for carbanion or carbene. Okay, only for carbocation the shifting is possible. So what it will happen, this is why it's called 1,2 hydride shifting. Why hydride shifting? Because one hydrogen is available over here, so 1,2 hydride shift. If I did not have any hydrogen available, then I had to shift a methyl, but shifting a methyl makes no sense because it will have reach the same condition, right? So 1,2 hydride shift, then what will happen? CH3C will get a positive charge. This hydrogen will go from here to here, and this plus will come from here to here. Okay, so CH2 CH3, and here it will be as it is. Now you see 3 plus 3 6 plus 2 8, more alpha hydrogen, so plus more stable. Now Mr. Br minus can attack peacefully, so attacked. So after attacking, the product that I am getting is CH3CBr, CH3, CH2, CH. So did you see that if you do not know that what is happening in the mechanism, you can see where you will be falling prey to. Directly would have written this, and that is definitely not the major product, that is a minor product. Major product is this one, but you will be writing the minor product, and that will be khacham kuchum 0. Understood that where and how you are making the mistake? This is the way you are making the mistake. Did you understand the HX reaction? This is a reaction which I am taking a lot of time. I understand I am taking a very lot of time. 1 hour almost I have taken for only this much part. But I have to take because I have to explain. I just cannot give the reaction and move out. Clear? So HBr, HCl, whatever I give, I have to see whether I can do shifting or not. In ISC, shifting is usually not expected because it is not taught in ISC in class 11. So you are expected to not know it, but you should because many of you are giving JEE. Okay, now suppose again I am telling, suppose you have memorized the reaction. You have memorized the reaction that alcohol reacting with HX is always giving me RX plus water. Okay, fine. Ja khushi debe, I will be doing this only. Whenever I find a HX given, I will be doing this. Achha, very, very confident. HX delay korbo. Achha, theek hai. Now, what chalaki I can do is, instead of giving you HX, I can give you this. Suppose I have ROH. I can give you Na2SO4 and I can give you HCl. Okay, if I have ROH, instead of Na2SO4 I have given you NaBr and I have given you concentrated H2SO4. This reaction will not work also, sorry. Instead of this I have given you this, or let us take another one. Let us take, suppose it is, let us take NaI and I have given you H3PO4. Then what? To reaction koroni. What is this? We don't know only what is this. But I will say, you know, I will say you are already knowing this reaction. It is nothing but the HX reaction only. But you have to mukhast the reaction. A question don't know. Then what? I don't know. I have not told you. Why? This is the same thing. That's why I have told you not memorize the reaction. Don't you see that NaBr can react with concentrated H2SO4? Doesn't that strike your brain that NaBr can react with concentrated H2SO4 to do something, to do a double displacement reaction? That is, it can form Na2SO4 and it can give out HBr, and I need the HBr for the reaction. So this HBr will be actively doing the work for me, and I know if HBr will attack, then I will get a RBr and I will get a water. Along with the water, my byproduct will also be Na2SO4 because that is also left. So what was the hurdle? Same reaction I have already told you, but what I have done is I have given a different reagent. Simple. So similarly for here also I will be writing Ri plus water plus Na3PO4. Simple. Achha. Remember, with NaI I can never use concentrated sulfuric acid. Okay. Here I am mentioning concentrated H2SO4 cannot be used. Huh? It cannot be used. Now why it cannot be used? Because H2SO4 will now oxidize Hi to I2, and I don't need I2, I need Hi. So if it is oxidized to I2, it is not my job. Understood? Now reason is because it oxidizes Hi to I2. And if it is oxidizing it, then that is not my lookout now. I don't want I2, I want Hi. But Hi is being oxidized to I2, then why will I use that? So we will be using mild oxidizing agent, which is H3PO4, mild acid. Did you understand? So don't try to memorize reactions. Instead try to understand what is happening. There are small changes I will make and you will be falling from the sky. So that should not happen. That is why I am teaching you one reaction in the last 20 minutes. Clear? Reaction with HX completely clear? If it is clear, then I will be moving on for the next type of reaction. The next thing that we are going to read. Clear or not clear? Please tell me. If you have doubt, write it down. Because you need to understand it. So reaction understood? Very clear, easy one. Next we will move on to the second type of reaction. This was the first method of preparation, that was reaction with HX. So as I've shown you, there are different types of methods. So now we are going to study the second method. Okay. So let's start with the second method. The second method is called Lucas test. Second method we will be calling it as Lucas test. Actually this reaction is supposed to come in the next chapter, alcohol phenol ether, but here I will need to tell because that is the method of preparation of alkyl halides only. But this is actually a test done to differentiate between 1 degree, 2 degree and 3 degree alcohols. Okay, so Lucas test, again it will come in the next chapter. Actually it is a part of the next chapter. Okay, but we have to tell out here also. So what is Lucas test? So we need to know a little bit about Lucas test. Lucas test is a test used to differentiate between 1 degree, 2 degree and 3 degree alcohols. Okay. So what is Lucas test used for? It is used for differentiating between 1 degree, 2 degree and 3 degree alcohols. Okay. So if we are performing certain test, we need to have certain reagent. So what is the reagent that is supposed to be used? So we need to know that. So let us write reagent. So reagent that we are supposed to use in this reaction going to be anhydrous ZnCl2, anhydrous ZnCl2, along with that we will be using HCl. Better to write concentrated HCl. Fine and understood. So you have to remember the reagent. So if we are performing Lucas test, we will be using anhydrous ZnCl2 and we will be using concentrated HCl. So what is this test used for? Used for differentiating between 1 degree, 2 degree and 3 degree alcohol. Alright. Now how will the difference be observed? Let us understand. So suppose I have a 1 degree alcohol. Okay. Basically what happens is ROH, if I give it with Lucas reagent, this is called Lucas reagent. So instead of concentrated HCl and ZnCl2, I can write Lucas reagent. So that also means the same. So ROH, if I give Lucas reagent, then what should I get? I should get the corresponding alkyl halide. Which alkyl halide? RCl only, because Cl is there plus water. This RCl, no, you will observe it as a white turbidity. That means, no, meghala gholote type you will find it as. Okay, cloudy thing you will see, that is white turbidity. So the RCl that you will find it is form of white turbidity. Now how is it going to help us differentiate between 1 degree, 2 degree and 3 degree alcohol? That we need to understand. So suppose I have 1 degree alcohol, let us take CH3OH. If I give pass Lucas reagent, or if I react it with Lucas reagent, then I will not get any white turbidity. No white turbidity. No white turbidity. Clear? 1 degree alcohols are the least reactive. Just now we have discussed it here. 1 degree alcohols are least reactive because the carbocation formed by 1 degree alcohol is very unstable. So this is going to give no white turbidity. Fine. If I have 2 degree alcohol, let us take CH3, CH2, let us take CHOH, CH3, CH3. Valence is satisfied. 1, 2, 3. Okay. If I pass this through Lucas reagent, then what will I get? White turbidity I will get, but white turbidity I will not get immediately. White turbidity is seen after 5 minutes. White turbidity is seen after 5 to 10 minutes. So we will be able to see white turbidity, but that white turbidity will be able to see after 5 to 10 minutes. Understood? 1 degree alcohol, so nothing you will get to see. 2 degree alcohol, you will be able to see white turbidity, but that you will be seeing after 5 to 10 minutes. Okay. If I use a 3 degree alcohol instead over here, if I use a 3 degree alcohol and I give Lucas reagent, then what will I get? I will get white turbidity. Okay, white turbidity. See, immediately. So did you understand? If I am using a 1 degree alcohol, nothing I will get to see. If I am using a 2 degree alcohol, I will get to see white turbidity, but that will be after 5 to 10 minutes. Okay, and if I am using 3 degree alcohol, I will not get to see white turbidity after 5 to 10 minutes, but immediately I will get it. Immediately, just you add it, you will get white. Understood? 1 degree will not be able to see. 2 degree will be able to see after 10 minutes, and 3 degree, they immediately will get it. Not even after 1 minute. You give it, you will give it. You will get it. The white one. The white color. Okay. So this was a 1 degree alcohol. This was a 2 degree alcohol. And this was a 3 degree alcohol. Clear? Did you understand that this is the Lucas test that is used to differentiate between 1 degree, 2 degree and 3 degree alcohol? Understood how differentiation happened? Actually, the formation is of an alkyl halide. That is why it is a method of preparation of alkyl halide also. But we do not take it in that sense. We use this for a differentiating test between 1 degree, 2 degree and 3 degree alcohols. So question might be arising from that point of view also. That means from the point of view of the second chapter. Alright. So did you understand Lucas test? So did you all understand Lucas test? Any doubt regarding Lucas test? I don't think there should be any doubt because it is easy. Easy to remember, easy to understand. So Lucas test, clear? So we have understood two methods of preparation. One is reaction with HX. Second one is Lucas test. Clear or not clear? If clear, then tell me, then we'll be moving on to the next method of preparation. So let us move on to the next reaction with phosphorus halides. Our next reaction is reaction with phosphorus halides. Reaction with phosphorus halide. Phosphorus halides. Okay. So that means it can be either PX3 type or it can be PCl5. Alright. So reaction with phosphorus halides. Okay. Let's understand the reaction. Here I have to utilize 3 moles of uh, alcohol, 3 moles, because you can understand px3. So what I can use here is px3 type of molecules, px3, or I can use PCl5, right? Okay. Okay. What is the reaction? Let us understand. Suppose I have 3 molecules of ROH and I am making it react with PCl3. Then what I am supposed to get? There is it px3 only as of now. px3. Acha. Remember, PCl3 can be possible. That means it exists as PCl3. But PBr3 or PI3 is very unstable. So instead of PBr3, in the question paper it will be written as red P plus Br2. Meaning is same. It is basically px3 type only. But the PBr3 molecule is unstable. So we write it as red P plus Br2. Is it clear? Red P plus Br2. So it is nothing falling from the sky. Same thing, same jinis. So this will form 3 molecules of Rx, and the byproduct that will be formed will be H3PO3. These 3 halogen atoms will be replaced by OH minus. So there will be 3 OH minus ions. Clear? Okay. So same, instead of this, if I write red P plus X2, will you be afraid? You will not be, because this is the same reaction, 3Rx plus H3PO3. Done. Okay. Now if I make this same reaction with PCl5, PCl5 is the only known one. Okay. PBRC I have not found anywhere, so I'm not talking about that. Okay, 3ROH PCl5. Then what will be forming? RCl will be forming, plus I will get POCl3 plus HCl. Okay, this reaction is a little bit important because this is a little bit different reaction, and mechanism of this reaction is not there in our syllabus, so I will not even tell you about it right now. Okay, so this reaction you can just learn the byproducts. So if I am treating 3ROH with PX3 type of halide, then I will get H3PO3 as a byproduct, and instead of PX3 if I write red P plus X2, no changes. But if I give you PCl5 instead of PX3, then I will be getting POCl3 plus HCl as my byproduct and not the H3PO3. Okay, clear? Now you want to know the mechanism, what is exactly happening, so let us know the mechanism. Mechanism starts. Mechanism. Ears should be towards the screen. Eyes also. Obviously, eyes should not be behind and your ear is towards the screen. Both the things should be coordinating, right? Okay. So I have ROH. ROH. We know that oxygen is a very loyal manush. So oxygen has 2 lone pair written. Okay. Coming to px3, px3, let's take px x x. All right. Now this is highly electronegative, highly electronegative, highly electronegative. Now p bechara is sitting in between, sitting sandwiched in between. Everyone is pulling electron towards itself. So ultimately this p is feeling a shortage of electron. This p is feeling lonely. Why? Because all the x atoms are pulling the electrons towards itself. So ultimately there will be a plus charge developing. No, not entirely. Fractional positive charge developing on first p. Did you understood? আরে বাবা পি তো মাঝখানে বসে আছে আর তার দিকে 3টে হ্যালোজেন, হ্যালোজেন সব ইলেকট্রন টানাটানি করছে নিজেদের মধ্যে। তো ও হ্যালোজেন এ ওইদিকে টানছে, এ ওইদিকে টানছে, তো পি ব্যাটার কাছে ইলেকট্রন কম পড়ে গেছে, তো পি এর ওপর ডেভেলপ হয়ে যাবে আ fractional positive charge. Okay, now oxygen is a very loyal মানুষ. So what oxygen will do? It will say, acha, you are feeling shortage of electron. No, I am here though. Why are you chinta karaing? I will give you electrons. So oxygen now gives electron. So what does oxygen do? Oxygen says, I am here, don't worry. So oxygen gives its lone pair to this person. Now phosphorus forming one bond with oxygen, and it will not break one bond, that is not possible, because we know always when there is a bond being formed in chemistry, there has to be the old ones being broken, any one of the old bonds being broken. So what will phosphorus do? Phosphorus will say one X atom to get out. One X atom to get out. So let's say this X atom goes out. Alright. So phosphorus says, I have got electrons. Now you please get out. Ekjonke bollo, you get out. Okay, fine. Then what will happen? You can see the O will be linking to the phosphorus. So the structure will be somewhat like this. O, H, one lone pair on oxygen, phosphorus linked, and it is having X, another X. Right? Now oxygen is a দয়ালু মানুষ, but oxygen has donated its share of electron. So oxygen এর মাথায় চলে এলো positive charge. Now as I have already said you before also, অক্সিজেনের মাথায় যদি পজিটিভ চার্জ আসে তাহলে অক্সিজেনের মাথাটা খারাপ হয়ে যায়। তাহলে if অক্সিজেনের মাথা gets খারাপ, then what it will try to do? It will try to take electron from someone. Now who is that someone? He does not know, but it will take some electron. It will take some electron from someone. Here also হাইড্রোজেনের থেকে ইলেকট্রনও নেবে না, because he thinks oxygen thinks that হাইড্রোজেন is a ভিখারি, ওর থেকে অক্সিজেন নেব না আমি। what am I saying? ওর থেকে ইলেকট্রন আমি নেব না, বাট আর এর কাছে তো পাওয়ার আছে, তো আমি আর এর থেকে ইলেকট্রন নেব। ঠিক আছে? It is not like that oxygen will always take electron from R only. No, you will find cases when hydrogen also will be removed. Like oxygen will take electron from hydrogen and throw out the hydrogen. That it will also come. But here, oxygen's matlab is not to take electron from hydrogen, but to take electron from R. Okay. Achha. So what it will do? It will take the electron from R and suffice itself. মাথাটা ঠান্ডা করবে, because it is getting power. Why? Because plus charge on oxygen. Oxygen does not want a plus charge on itself, but it has a plus charge on itself. So oxygen does not want a plus charge. এর ওর মাথায় প্লাস চার্জ চলে এসছে, তো ওর মাথাটা যাবে খারাপ হয়ে। তো করলো ইলেকট্রন নিল, নিয়ে কি করলো? নিয়ে এবারে স্ট্রাকচার ফর্ম করলো। তাহলে আর রিলিজেস আর ইন্টারমিডিয়েট আর প্লাস প্লাস, এই পুরো পার্টটা যদি ভেঙে যায়, মানে এই বন্ডটা ভেঙে যায়, পুরো পার্টটা একটা হয়ে গেল। তাহলে what I can write it as, can I write it like this? OH X2. See, same thing I have written. POH X2. Clear? Okay. Now what will this R plus do? This R plus will go with someone from here. It will pick up a Cl minus. Which Cl minus? এই যে একটা Cl minus free হয়েছে এখানে। This X minus when free. So here there must be a minus X minus ion, right? Because this X minus ion when free. So this will go with the X minus ion. Where is the X minus ion come from? Here one X minus ion went free. That X minus will react with R plus to form what? To form Rx. Done. Now in this entire reaction there will be a solvent being used, that is preferably water. So there will be OH minuses. So what this OH minuses will do? They will keep on replacing the X2 until the X2 finishes. So one X2 replaced, then becomes this, then another X2 replaced, finally it becomes POH whole 3. And this is nothing but, better way to write is H3PO3, and that is the byproduct you get. Clear? So all the halogen atoms will be replaced by OH groups. Clear? So did you understand what is exactly happening? It is much easier than the previous one. Acha. Carbocation intermediate is formed here as well. So what you have to take care of? Rearrangement. Because wherever carbocation comes into play, rearrangement is awaited. Rearrangement possible. Right? Rearrangement possible. Acha. But this thing does not happen. This is why this thing does not happen. According to whatever I have written, this thing should happen. Then R is going, R plus is being formed. POH X2 POH, that is fine, leave it. But R is giving its electron to oxygen, and rather oxygen is taking up the electron, so R is getting a positive charge. Fine. X minus is attacking after R plus. Who has given that guarantee over here? That is a factor. That is a very much factor. See here, if R is a 3 degree, that means the ROH is a 3 degree alcohol, then I can say that this thing can happen. Then I can say that R plus has a chance to be formed. But still, due to steric hindrance, that will not be preferred, because you can see the steric hindrance will be caused. But if it is a 1 degree alcohol, then what? R plus won't be formed because as I've already told you, R plus for 3 degrees maximum stable. So if R is a 1 degree alcohol, for most cases it will be a 1 degree alcohol. So what happens is the X minus attacks before the formation of R plus, means R plus does not form only. R plus does not form only. This case what I have written is SN1 mechanism where carbocation is forming. But here actually in this case no carbocation forms. Why carbocation does not form? Reason is very simple. Because ROH is a 1 degree alcohol. Usually 1 degree alcohol. In 3 degree alcohol is usually not used because it will be difficult for the oxygen to bind with that phosphorus due to steric repulsion or steric hindrance, whatever you say. Okay, so what is the problem over here is that R will give its electron and before even it can develop a positive charge, the X minus will touch kore marbe oke giye. Did you understand? So carbocation is not going to form, so no question of any rearrangement. So what will happen is only this part I will change. So I am erasing the rearrangement part because rearrangement will not be formed if there is no carbocation, right? Okay, so what will happen is here, as I said, that the Cl minus will be attacking Cl minus and not X minus. The X minus will attack the carbon, attack the R ion like this from behind. This kind of backstabbing is called SN2 mechanism, which I will deal with later on. This kind of backstabbing is called SN2 mechanism. So you can see directly an XR is being formed. Directly an XR is being formed. There is a why they write XR and not RX are the same thing. But if R is chiral, then XR, because inversion will happen. That all things I will tell you, not now. And already I think it is done in class 11 as well. XR inversion will happen. So you do that. Achha. So did you understand that here SN2 takes place? SN2 is preferred because ROH, if it is a 3 degree alcohol, then definitely carbocation will be formed. If it's a 1 degree alcohol, then SN2 mechanism is preferred, and usually it is a 1 degree alcohol only, or 2 degree also SN2 preferred. So we will be talking about the SN2 mechanism. But the first mechanism that I showed, the carbocation intermediate being formed, that is possible for 3 degree alcohol. Okay, but 3 degree alcohol, you can understand that there will be methyl groups, ethyl groups, or whatever groups it is, there will be large alkyl groups, so that will cause steric repulsion. When the oxygen will try to attack this center, it will cause repulsion. Repulsion, there will be problem. Understood? So here, is there any carbocation intermediate being formed? Here too it is not formed. Previously I have shown it was formed, but that was for 3 degree, not for this. We will talk about 1 degree, 2 degree. Okay. Is there any carbocation being formed? No. So is there any question of rearrangement? No. If R is chiral, then XR will be inverted. Inversion of configuration for SN2 mechanism. That also I will tell you. For now, just listen to what I am saying. Okay. So can I repeat from the first once again? ROH, oxygen has 2 lone pair of electrons. So it will give 1 lone pair to the phosphorus who is having a plus del charge. Why? Because 3 halogen atoms, they are pulling electrons towards itself. Okay. So phosphorus is getting a deficiency of electron. Done. Oxygen gives this lone pair to phosphorus. Phosphorus making one new bond breaks one old bond, that is breaks one X bond. Done. So one X minus is freed. Done. So ROH plus bonded with PX2. Done. Oxygen, since it has given one electron pair to phosphorus, will develop a plus charge. But oxygen cannot bear a plus charge. Its brain starts malfunctioning. So it will take one electron pair from its adjacent atoms. Oxygen forgives hydrogen. It does not take electron from it. It takes electron from the R. R, instead of forming carbocation, or rather before it can form a carbocation, X minus backstabs R. X minus backstabs R. So it attacks from behind and it directly forms XR. Okay, and the other part is POH X2, where X2 replaces X, where OH replaces X2 and ultimately forms H3PO3. This is the entire mechanism which you need to remember. Clear? This is the reaction with phosphorus halides. Please try to understand. Then we'll move on to the next one. Alright. So phosphorus halide reaction clear to everyone? You do understand what exactly is happening. So here SN1 mechanism is not preferred, okay, because 3-degree alcohol will be sterically hindered. So SN2 mechanism will be preferred. Alright, reaction with phosphorus halides clear. Next, let us move on to the very important reaction. The next reaction we are going to study is the Darzin's process. The next reaction we are going to study is Darzin's process. Darzin's process. Alright. So let us understand what exactly happens in Darzin's process. So basically in the Darzin's process we use ROH and we treat that with SOCl2. Alright, so we get RX. X here is Cl only because we have SOCl2 only. Okay, acha. Then we have SO2. Then we have HCl. Okay, byproduct is important because you know why it is important. Okay, now if I am using pyridine also, if I am using pyridine as well, no problem, same product, no change, only change will be in the stereochemistry. Okay, pyridine. Then also the product will be same, plus SO2 plus S. But you can see that I have written it as CLR. So just now I told if it is SN2 mechanism, inversion of configuration, and that is what happens over here in second case. So did you understand? Achha, what is exactly SOCl2? SOCl2 is called thionyl chloride. Okay, thionyl chloride. So Darjan process is basically dealing with preparation of alkyl halides from alcohol using thionyl chloride and pyridine. Alright, so we are going to know the mechanism. Before that, you should be knowing that Darjan process is the best method to prepare alkyl halide. Best method to prepare alkyl halide. Best method to prepare alkyl halide. Now, why is it the best method? Best method to prepare the alkyl halide. Why? The reason is SOCl2 you see or you see HCl, both are gases. So will they be in the reaction mixture? No, they will be leaving the reaction mixture. So if they are leaving the reaction mixture, then what will happen? The concentration of the product will decrease. Then according to Lachatellier's principle, the reaction rate will be increasing because the equilibrium shifts to the forward direction. That much you have done in class 11. Alright, so best method to prepare alkyl halide. Why? HCl and SO2 being gases leave the reaction mixture. Leave the reaction mixture. Okay. Then what happens that according to Lachatellier's principle, here you write third bracket indicates products concentration. Okay, decreases. Third bracket indicates concentration. I might use third bracket somewhere, that is for concentration, that I will say. Okay, according to Lachatellier's principle, spelling, forgive me, spellings are very awkward, you know. This is La or Lea, that also I forgot, really Lea only. Okay, Lachatellier's principle, P means product, decrease in the product concentration shifts the equilibrium in forward direction. In forward direction. Understood? So why is this the best method? Because HCl and SO2 both are gases. So if they both are gases, then they will leave the reaction system. So if they are leaving the reaction system, concentration of product will be decreasing. If concentration of product is decreasing, then according to Lachatellier's principle, the equilibrium will be shifting in the forward direction. So if equilibrium is shifting in the forward direction, I will get more product. So I will get more RCl. That is my advantage. Clear? So main thing is this one. best method to prepare alkyl halide. Don't forget, it's important. Don't forget it, very important. Very important. Huh? Putting 2 stars, very important. Best method to prepare alkyl halides. Okay, now let's understand what exactly is happening out here. So as I have told you, I'll tell you about the mechanisms as well. So let us understand what happens in a mechanism. First mechanism that I am going to talk about is going to be without pyridine, with pyridine. I will show you with pyridine, without pyridine, both. Achha. First let us talk about without pyridine. Without pyridine. Okay. Now let's understand what happens exactly without pyridine. Achha. We had ROH. We know oxygen is a very dayalu manush having 2 electron pairs. Okay. SOCl2 is somewhat this. S double bonded O, single bond Cl, single bond Cl. Now you can see here the same thing is happening as phosphorus. Sulfur is getting sandwiched in between. Oxygen is pulling electron, developing a negative. Chlorine is pulling. This chlorine is also pulling. So ultimately sulfur is developing a partial positive charge, an intense partial positive charge. Why? Because too much electron is being pulled from both the sides. Now oxygen is a dayalu manush. So oxygen will be donating this electron pair to sulfur. Now sulfur is forming a new bond with oxygen, very happy. So what it will do is it will break one bond. Now since a pi bond is present, it will try to break the pi bond first, because pi bond will be broken easily. So what it will do is it will do it. Done. Okay. Now what will happen? So this bond broken. So bond is being formed like this. RO H, oxygen, 2 electrons are still there. S formed. Oxygen got a negative charge because this bond shifted to oxygen. Then we have one Cl. We have another Cl over here. Done. Okay. Now oxygen will develop a positive charge. Why? Because oxygen is giving up electrons. So oxygen will develop a positive charge. Right. Now I have already told you that oxygen positive charge, mata kharap hoye jabe, so it will try to take electron. Now oxygen thinks that I have taken too much electron from R. আগের বারও নিয়েছিলাম, তার আগের বারও নিয়েছিলাম. This time let us take electrons from hydrogen. আগে দুটো কেসে, in case of HX and PX3, both the cases we have seen that oxygen is taking electron from R and breaking the R bond. But this time oxygen thinks something new. Oxygen thinks R এর থেকে ইলেকট্রন নিয়ে না এবার আমার লাভ হবে না. অক্সিজেন থিংস আর এর থেকে ইলেকট্রন নিয়ে না আমার লাভ হবে না কোনো, তা আমি হাইড্রোজেন থেকে বরঞ্চ ইলেকট্রন নিলে এবার লাভ হবে আমার. তাহলে what does oxygen do is oxygen says, oh hydrogen বাবা come here, give me electron and you get out from here. তো হাইড্রোজেনের থেকে সবকটা ইলেকট্রন নিয়ে নিল, নিয়ে হাইড্রোজেনকে বাইরে বার করে দিল, হাইড্রোজেনকে ভাগাও, তাহলে হাইড্রোজেন গন আউট. আচ্ছা, সালফার আবার এদিকে আরেকজন, সালফারও এখনো প্লাস এটা নিয়ে বসে আছে, কারণ এই ইলেকট্রন টেনে যাচ্ছে, এও ব্যাটা টেনে যাচ্ছে, তাহলে এখনো এর ওপর প্লাস ডেল চার্জটা আছে. তো ওর থেকে ইলেকট্রন নেওয়ার পরও লাভ খুব একটা হয়নি. Even after taking electron from oxygen, sulfur has got no such big advantage because still it is being in the state of deficiency. So what does sulfur do? Sulfur says one chlorine to get lost. Sulfur throws out one chlorine and forms this bond. Because it is breaking one bond with the chlorine, it needs to reform one bond, otherwise it will be more pagla. So it is forming the oxygen double bond once again and it is throwing out one chlorine from there. Okay. So what is going to be the next step is R, oxygen has got back its 2 lone pairs, hydrogen has gone out. So here I have to write minus H plus gone out, and as well as minus Cl minus. Now this H plus and Cl minus will combinedly form HCl. So you have got your first product. These 2 personalities will form HCl, and that is one of the product that you have seen, right? Okay. So what I am left out with ROS double bond O and Cl. Right or wrong? After this I am left out with ROS double bond O Cl. Now I do not have any pyridine. Since I do not have any pyridine, then there cannot be external attack of nucleophile. So what happens here is internal nucleophile only attacks. Now what is internal nucleophile? This is SN internal mechanism. That also I will teach you later on, but the same reaction I will be giving there also. SN internal mechanism. আচ্ছা ক্লোরিনের কাছে লোন পেয়ার আছে. Chlorine is also very দয়ালু মানুষ. No, it is a দয়ালু মানুষ, but not as দয়ালু as oxygen because it pulls electrons also. Chlorine is দয়ালু, but it takes electron also. Right? Chlorine has lone pair. So what chlorine will do? It has 3 lone pairs. 1, 2, 3, 4, 5, 6. So I am showing only 1. Huh? It has 3, but I am showing 1 because I need 1 only. Chlorine has a lone pair. So what it does is, it can see that this plus has developed over this R because oxygen is pulling too much electrons from this R as well. Oxygen is pulling too much electrons from it. আচ্ছা ক্লোরিনের ক্ষেত্রে সালফারের উপর পজিটিভ চার্জ হতে পারতো, তাহলে ও সালফারকে ইলেকট্রন দিতে পারতো। আরে পাগলা, সালফারের সাথে তো নিজে অলরেডি বন্ডেড আছে, তাহলে আবার ও সালফারকে ইলেকট্রন দিয়ে করবেটা কি? ও কি দুটো হাত দিয়ে বন্ড করবে নাকি? ও তো একসাথে, ইট ইজ অলরেডি বন্ডেড টু সালফার, ইট ক্যানট গিভ ইলেকট্রন টু সালফার again, it has already given electron to sulfur. How much electron will give to sulfur? Sulfur will have 5 bonds or what? Okay, আচ্ছা। So this R has also got a plus charge. Now chlorine is sitting at that corner and saying that R is having a plus charge. So what does chlorine think? Chlorine এর মাথায় এলো, আচ্ছা let me give its electron and form a bond with it. So what does chlorine do is, chlorine sends its electrons to this person. Chlorine sends its electrons to R. So what happens as a result? This bond will shift here. If this bond will shift here, oxygen will develop a minus charge. This minus charge will shift here. Ultimately chlorine will be thrown out. Because chlorine is actually giving its electron to this. So chlorine is breaking the bond only, but directly it will not break. Chlorine will try to stay in the bond. It is giving electron to R. R is breaking the bond. Oxygen developing a minus charge. Minus charge coming and forming a double bond here. Sulfur forming an extra bond, kicks out the chlorine from there. Says chlorine, you have done Goddari, get out. Fuck kore bar kore dilo bayre. Okay, so what is the product that I am seeing over here? I am writing over here, huh? The product that I am seeing is R forming with Cl, and you can see S double bond O double bond O, somewhat like this structure. Double bond double bond. What is this? This is only the SO2. This is only SO2, and that is also one of the product. This is a required product. Did you understand the mechanism? Very interesting mechanism. This mechanism is called SN internal mechanism. SN internal mechanism, because there is an internal nucleophilic attack. So this is SN internal mechanism. We learned about SN1, SN2 in class 11, but it's a different type. This is SN internal mechanism. Did you understand that without filling in what exactly is happening? I am explaining once again. Okay, I am explaining once again. ROH is there. Oxygen has 2 pairs of lone pair electrons. Alright. SOCl2 looks like that somewhat. So what does oxygen see is that sulfur is having a very intense del plus, because oxygen double bonded is pulling electron towards itself. Both the chlorines are pulling itself electrons towards itself. So ultimately sulfur is developing a plus del charge. So what does oxygen do is, oxygen sends its pair of electrons to del plus to satisfy sulfur. Galo electron. Now electron donation by oxygen means oxygen will develop a plus charge. Oxygen is supposed to develop a plus charge. It has developed. So structure becomes ROH plus on oxygen bonded with SO minus. Sulfur has to break a bond. If sulfur is forming a bond, sulfur has to break a bond. So what does he do? He breaks the pi bond, because pi bond is easier to break. So pi bond it has broken and it has sent O minus. So SO minus ClCl. Done. Now oxygen and matha plus means oxygen and matha kharap. So what does oxygen try to do? It tries to remove that plus charge of itself. So last 2 reactions we have seen that oxygen removes this plus charge by taking electron from R. But this time it thinks that R এর থেকে electron নিয়ে আমার কোনো লাভ হবে না, লসই হবে আমার। R এর থেকে electron নিয়ে লাভ কিছু নেই, লসই হবে আমার। So what does it try to do? It tries to take electron from hydrogen this time. Says hydrogen, এ তো একই ভিখারি, বানিয়ে দিই ভিখারি একেবারে। তো what does it do? It takes the electron pair from hydrogen, satisfies its plus charge and throws out hydrogen. Gone. So hydrogen released as H plus. Bhikari again. Achha. S is still having a del plus charge. Even after getting electron pair from oxygen, Sl del plus charge is not satisfied. Okay. S, what does it do now? It throws out one chlorine. It throws out one chlorine. Chlorine gone out. One chlorine gone out means another bond needs to be formed somewhere. Otherwise, still it will have more plus charge. So what does it do? It reforms the double bond with oxygen. Formed. So the structure we get is ROS double bond OCl. Done. Now, there is no one externally to attack. That means there is no external person to attack and throw out R from the compound. It is not there. So in this case, internally the nucleophile attacks. That means chlorine is a hidden doyalu manus. Oxygen is a very doyalu manus, we know, because it donates electron easily. But chlorine is a different kind of person. It can donate electron, but it does not donate electron easily. Rather, it takes electrons. So it is a hidden type of doyalu manus. Right? Here its character comes out. Chlorine is closely observing that R has got a del plus charge. Sulfur also has a del plus charge, but it is already bonded to sulfur. So okay to R electron নিতে পারবে না, কারণ it is already bonded to sulfur. আর কিভাবে ইলেকট্রন দেবে? Already তো bonded. Double bond তো বানাতে পারবে না. Double bond তো মাথা খারাপ হয়ে যাবে. Double bond not possible. So what does chlorine do? Chlorine observes R and says, I have lone pair of electron. I will give electrons to R. So it sends electron to R. But it does not break the bond with sulfur. Chlorine is very chalak. It will not break the bond with S. So chlorine is bonding, throws the electron towards R, R catches the electron. R will break the bond because R cannot form two bonds. R breaks the bond with oxygen. So oxygen gets a negative charge because the electron shifts towards oxygen. So oxygen's negative charge now forms a double bond with sulfur. Now sulfur is very confused. আমার কাছে double bond formed, I will get pasta bond or what? So what does it do? It says chlorine, you get out. You have formed another bond, you get out from me. I will not form a bond with you anymore. So sulfur throws out chlorine. This type of mechanism is called SN internal mechanism because there is an internal nucleophilic attack. No external nucleophile has been attacked. Right? So ultimately I am getting RCl. And S double bond O is basically SO2. And that was what we have written over here. Did you understand? Did you understand? This is the basic mechanism when there is no pyridine. Okay, now let me copy the same slide. Copied. Without pyridine clear to you? Any doubt that you have not understood without pyridine what is happening? I think you have understood without pyridine what is happening. Now we will be talking about what happens if pyridine is present. What happens if pyridine is present? So let us understand. I am just erasing this part. See, the first part is whatever it was, it will remain same. First part is having no change. First part is having no change. Whatever we have done, the same part will be the first part, but the parts will change after this. With pyridine. With pyridine. See here. After this step, what formed was ROS double bond OCl. Right, this one only formed ROS double bond OCl. ROS double bond OCl. This was formed, wait properly, ROS double bond OCl. Now HCl has gone. Just before some time we have seen HCl has gone out. Now what is the problem over here is this external pyridine. This external pyridine is a problem. Have you ever seen what is pyridine? If you have not seen, then I am showing you. Pyridine is somewhat like this. If you have seen benzene must be like this, then just replace one end of benzene with nitrogen and every alternate form a double bond. This is called pyridine. Every alternate double bond is there and break one bond. This is called pyridine. Nitrogen. This is pyridine. Now, if you know pyridine's lone pair, nitrogen has a lone pair, right? 5 electrons, 3 electrons are there. Where is the other one? Here. Pyridine is a very strong base. Do you know what is a base? A base is someone who can donate electron to H plus, right? That concept also I will be giving you after some time. So nitrogen's lone pair is not involved in the resonance. You know what is a resonance? In class 11 you have done resonance. Resonance means if you have to explain all the properties of a structure, then you have to draw certain different structures. Like one structure cannot give all the information of that compound. So the different structures are called canonical structures or resonating structures, and ultimately the hybrid of those will give you the resonance hybrid, and this phenomena is called resonance, right? If the electrons are involved in the resonance, that means it is not very much available for basicity, it means for donation. But here in case of pyridine, the electron pair is not involved in resonance, it is out of the plane, so it is not involved in resonance. See, I am linking too many things, so listen to me carefully, you will understand. In the last lecture of hydrocarbons, hydrocarbons or GOC, I exactly don't remember, either of the lectures, I have taught you Huckel's rule of aromaticity. What was Huckel's rule of aromaticity? A compound can be aromatic only if all are sp2 hybridized carbon, it means they are planar. They are planar. So this compound is planar, but the lone pairs are not in planar. The lone pairs are not in the plane. So if the lone pairs are not in the plane, they cannot undergo resonance. That means complete delocalization of electron is not possible. So this lone pair electrons will not undergo any resonance because they are out of the plane. So pyridine nitrogen part has two electrons. Two electrons is one lone pair. So it can donate to any hydrogen. Now you can see that this H plus has formed here, H plus formed, Cl minus formed. So what it will do is it will catch this HCl. It will catch this HCl. Base will donate electron to this H plus. So ultimately what will happen? HCl এর H plus টাকে electron donate করে দিয়েছে. So this will catch an H plus. So what will be formed? Like this. This is called pyridinium ion. Pyridinium ion. Pyridinium ion. And what will be free? Cl minus will be free because HCl to form হয়েছিল, but pyridine suddenly takes up the H plus because it's a very strong base. So ultimately it makes Cl minus free. So Cl minus ঘুরে বেড়াচ্ছে. So this time the internal nucleophilic attack will not happen. Instead, who will attack? The external Cl minus, which is free to attack. So Cl minus was free to attack. So this Cl minus will attack over here. But this Cl minus will not directly attack. This Cl will attack from behind. But here I have to give the arrow forward because I do not have space for that. Achha, let me then move out from this space. Achha, after this reaction, we extend the because I have to show it from behind. I cannot show it like this. Achha, I am writing the continuing of the reaction over here. So, what is happening? R O S double bond O Cl. External nucleophile Cl minus will now attack. How it will attack? This way it will attack. This bond broken. Minus will come over here. One form. This will thrown off. So ultimately what is being formed? R chlorine X chlorine R plus SO2. Understood? Clear? Check. This is going to be the case. So you can see here there is an external nucleophilic attack. So this is called SN2 mechanism reaction because external nucleophile attack. Please make sure that you have understood the thing, what is happening. I am repeating on the first. First part too is same. I am not telling from that part. ROS double bond OCl is formed. Last time what did we see? That internally this Cl donates its electrons to R and ultimately breaks off. Right. Here what we are seeing is we have used an external thing called pyridine. Pyridine looks like something benzene, but the para position has nitrogen, and nitrogen has two lone pairs. Important thing that is to be noted is that nitrogen's lone pair is not involved in delocalization. Here it is not involved in resonance. So if it is not involved in resonance, then what? It will be available for donation. Something, if it is not involved in resonance, it will be available for donation. In class 11 GOC, you have learned the order of basicity, order of acidity. Basicity is proportional to the strength of conjugate acid. Acidity is present conjugate base. This you have done it, no, right? So in case of pyridine, the lone pair is not involved in the resonance. So if the lone pairs are not involved in resonance, it is more available for donation. So easily the lone pair can be donated to someone. HCl was found before, or H plus was also found before. So what it will do is it will try to attract H plus. So it will say, I have lone pair vector, you come to me. Pyridine will call H plus. It will say, come to me, I have electrons. So it gives H plus electron. So H forms a bond with this. This will be called as pyridinium ion. So if H plus is bonding with N, then who will be left out? Cl minus will be left out. So Cl minus is now free. And Cl minus is a very good nucleophile. That also I have told you. So what will Cl minus do? This time, instead of the internal Cl, the external Cl will attack. I am not saying that internal Cl will not attack. It will. Some percent internal will also be formed, but that will be the minor product. Major product will be the external Cl attacking the R. And that is a backstabbing. Cl minus will backstab R. So ultimately it is a SN2 mechanism. So you need to understand that when we are not using pyridine, it is going to be SN internal mechanism. But when we are using pyridine, it is going to be SN2 mechanism. It is called SN bimolecular mechanism. Okay, so with pyridine, it is going to be SN2 mechanism. Without pyridine, it is going to be SN internal mechanism. What is the mechanism? Understood, I hope. No doubt with that. Directly it is happening. This step till this much step, it is same. Till this much step, it is same for both the case. Whether you go for this one or whether you go for this one. First step I have not changed only. But the second step is different. Because here external nucleophile falls in, and here the internally only the Cl minus attacks. In details we will study about SN1 and SN2, SN internal, SN prime, that is in the later part of the chapter. Okay, so this is all that you have to study from Darjan process. So Darjan process I hope is very clear to you. No doubt will be there regarding Darjan process. Darjan process is one of the important part that you have to understand from this part. Okay, see the what we have studied till now. Let us summarize once. We were studying ROH with HX, gun done. PX3, PCl5 done. SOCl2, SOCl2, pyridine done. So the first part that we have started, that was done. From alcohol, if we have to prepare alkyl halide, then we have this methods, and we have done the method. We have done one extra method as well. That was Lucas test, Lucas reagent, which was actually supposed to be done in the next chapter, but we have done in this chapter itself. Right. So if you have any doubt till me, you can ask me. Mechanism will not come in the exam, but if you want to really understand what is exactly happening, the mechanism is important for you. Alright, and from if I talk about from JEE NEET point of view, then the mechanism you need to know, otherwise you cannot answer. Acha, clear? Now, when the questions come from stereochemistry, suppose the question is asked from stereochemistry using wedge and dash format, then in that case, if you don't know where will be the inversion and where there won't be inversion, like here there is no inversion. Achha, let me mention also. No inversion observed. No inversion. No inversion observed. Why is there no inversion observed? Why is there no inversion observed? Because there is no SN2 mechanism. If there is no SN2, then there should not be any inversion, because inversion is seen only in the SN2 mechanism. But here SN2 is happening, then inversion I will see. Now if you don't know that where inversion is seen and where inversion is not seen, stereochemistry question 2 will get wrong, because there will be one option which will be talking about the wrong one. Clear? Because NT also knows that many of you don't know only what is inversion, what is not inversion, which mechanism they have not studied only. So for that type of students, the council needs to do something. Clear? Clear with this? Next, we'll be studying about the next type of method of preparation, that is class 11 level topic from alkanes. Now, from alkanes, do I need to really explain anything? You all know free radical mechanism. Okay. So, preparation of alkyl halide from alkanes. So, let's start. Second topic is from alkanes. We are done with alcohols. Now, from alkanes. From alkanes, you have done it in class 11. If you remember, we have understood the free radical mechanism. There was in detail, that was the only mechanism we had in class 11, free radical mechanism. The same thing is going to repeat over here, repeat telecast of whatever you have done before. Okay, so let's do it till. So the reaction basically is like, suppose you have methane and you are treating it with a chlorine in presence of H nu. So you get CH3Cl plus HCl, but reaction will not stop here. Further you will give energy in presence of Cl2, then the second chlorine will enter, second hydrogen will disappear, again another HCl will form, then also the reaction will continue, Cl2, then again what will happen is ClCl3 plus HCl. Ultimately when you stop this reaction at this CCl4 plus HCl, right? So this is going to happen by radical mechanism, you can see, and we are writing the major product CH3Cl actually. Here this compound CHCl3 is called chloroform. Very important, because we will discuss later on also chloroform test, iodoform test, chloroform property, Voskine formation, that we will be talking about in the later part of the chapter. But chloroform is CHCl3 and not the CH3Cl. You have to will write ulta, though I don't expect that, but you might write ulta, that is CH3Cl. That is not chloroform, that is methyl chloride, but this is chloroform. Alright. So do you want to know that what is happening over here? There is a mechanism of the reaction, right? I think you all already know about it, but still I'll be talking about it. Just give me 1 minute. Mechanism of the reaction. So you remember that the three-step mechanism, right? First one is the chain initiation, second one is the chain propagation, third step is the chain termination. So if we go for the first step, that is called chain initiation. Chain initiation. So what happens in the chain initiation? Who will initiate? Even if you use your common sense, who is initiating the process? কে শুরু করছে প্রসেসটাকে? শুরু কে করছে? Who is starting the process? Cl. So there must be the Cl bond rupturing. So Cl bond breaks into two Cl free radical. Okay, homolytic fission, and two free radicals are being formed. Chain initiation done. Second step we are seeing chain propagation is happening. Chain propagation. What happens in chain propagation? You had a CH4. That CH4 gets attacked by a Cl. So what will form? CH3 free radical plus HCl will be formed. Did you understand, or I have to show how it is being formed? I think I need not, because you have done this in class 11, right? And I have also taught this in the video, the hydrocarbon or GOC lecture, so you can go there and watch. Okay, basically still I am saying you CH like this, it is there, CH, and this Cl minus Cl. So this bond will now break. Done. So this H has one free radical, one free electron, and this free electron will combine. As a result, CH3 will be a free radical that is being formed. Okay. So next what will happen in the same step? Another step is there. What will going to happen? The CH3 free radical will break one Cl bond this way, and it will take one Cl with it. So what will be formed is CH3Cl plus a Cl free radical. So Cl free radical the first step will form hoyeche. In the second step also it is going to get formed, because CH3Cl is also being formed, and Cl free radical will be formed. Third step is the chain termination. In the chain termination step, whatever free radicals will be there, they will be dimerized. what will happen? They will be dimerized. So Cl free radical will be dimerized with another Cl free radical to form chlorine. We can write Cl2 or ClCl, no problem. Another guy is there, that is CH3 free radical will dimerize with another CH3 free radical to form CH3 single bond CH3. But this quantity is very less, that's why it is a minor product. Major product is that one only will get CCl4. Minor product is CH3. Clear? So this is the entire mechanism. This I have already told to you in the GOC lecture or hydrocarbons maybe, but I have told you this in class 11. Same thing is been repeat telecasted over here. Understood? Very easy thing. You already know, so no doubt should be there. Next, let us move on to something. Here too we have been using Cl2, Br2, no problem is there, no problem. But the moment I am using I2, this is an important one, huh? I am putting a star mark because this is important. Okay. What I am doing is for I2. So if I am suppose using CH4 plus I2, then along with I2 I have to also use HiO3. Okay, so CH4 plus I2, then I will get CH3I plus HI. Then the reaction will continue as and when it is going to happen. Okay, and I am showing till this much only. So basically why we are using the HiO3 is because this HI, if HiO3 was suppose it is not there. Suppose it is not there, then what is going to happen? HI will be making this reaction reversible. Mane we will get back the reactant. Product we wanted, but we are getting back the reactant. So আমাদের কাজের কাজ নয়, আমাদের তো দরকার product, but I am getting back reactant. So that is not my good job. I need to get a product, but I am getting reactant. What is this? So you have to prevent the reversibility of the reaction. That I can prevent by decreasing the concentration of the product. So I have to decrease the concentration of HI. So for that I am using HiO3. What HiO3 exactly is going to do is, HiO3 is going to oxidize this HI to I2. Okay, I2 plus water. So as a result I am getting I2, and I2 so I need also for the reaction. So concentration of product is decreasing and I am getting more of reactants. So automatically according to Lorentz principle, reaction equilibrium will shift to the forward direction. So more product I will get. Understood? So if the question is asked, though it is not expected in 12, because this question is a class 11 level question, and that we have asked in 11 also, that why is HiO3 used for halogenation? Clear? Reason is this HI is reversible, makes the reaction reversible. So to prevent the reversibility of the reaction, I need to use HiO3. Okay, so just write down the question. Answer you all will write on your own. Question is, why HiO3 is used during substitution of alkanes. Or why is HiO3 used during preparation of iodoalkane? This will be a better preparation of iodoalkane. This is a better question. So why is HiO3 used during the preparation of iodoalkane? Answer to I have already given. So you will be writing it in your own answer. Main point to be noted, I am writing the main key point, that is to prevent reversibility of the reaction. To prevent reversibility of the reaction. Reversibility of the reaction. Okay, and if you can give the reaction, very easy. You can see the reaction is given above. You can just copy and paste the reaction. Clear? So if we are going to use I2, then not only I2 I will use, along with that I have to use HiO3. But for Cl2, Br2, no such thing is required, because they will HCl or HBr does not make the reaction reversible. Clear with this? Okay. No problem? Clear. Okay. Now let's do some examples. Let's understand. Now you see what I have shown you is for CH4. That's the simplest one. The simplest one I have shown. That will be easy for you to understand. But question though will not ask you methane. Then what will question ask you? Certain big ones. Like maybe butane, propane or pentane. Then in that case, what you will do? That means suppose I am giving you example with help of ethane. Okay, ethane. Ethane looks like, sorry, propane. There's a propane. CH3, CH2, CH3, and I'm telling you, you halogenate it, Br2. Not to the final step. Only one step you halogenate. Okay. No need to show me the final step. First step only you will show. So in presence of H. Then what will you do? Now you see, someone can tell that it is my freedom that I will do this. Okay. I am doing this. Not wrong. Someone says no, I will do this. Now if you want to do over here, then that is this only, na? What is the problem? এখানে করলে যা হবে আর এটা করলেও তাই হবে, same thing. So no problem with that. Right? So I am getting two possibilities, either this one or this one. Now which one to do? This one or this one? That is a big question. So for that the mechanism is here. For that the mechanism is here. Where is, you can see that there is a free radical being formed. No, this is the point. There is a free radical that has been formed. I am highlighting the free radical being formed. Here is the free radical form. This is the free radical form. So this free radical is going to determine which one will be more stable. Right? Here to one carbon, but here to not one carbon. So let us not directly jump into conclusions. Let us understand by steps. Okay, so let us erase this. Now you tell me that from the mechanism that you understood, that CH3 free radical will be formed with the help of Cl free radical. That is going to form HCl. Right? So here one Br is supposed to attack and one H is supposed to leave. Right? So if I am suppose doing CH3, CH2, CH3. Suppose I want to remove one hydrogen from here. Okay, fine. Okay, first tell me how many different type of hydrogen is present. Because sometimes question asks how many monosubstituted halogen products are possible. So for that you have to check how many different number of hydrogens are there. See, this hydrogen and this hydrogen, they are same. Why are they same? Because numbering will be same. No? You do from this side or you do from this side. Same point, same position. So these two hydrogens are same. So either of these we will take and another take this one. So we have two possibilities out of which we are going to decide. Right? Okay. So let me remove one hydrogen from here. Okay. So I have removed one hydrogen from here. I have removed one hydrogen from here. So that means what? The entire personality has got a free radical. Where is the free radical form? Here. Now, if not this, then what? If not this, then what? Then I can say that I have removed one hydrogen from this position. Okay. Then what? Then I can say that the free radical that will be formed will be over here. And this will be as it is. So now you tell me which free radical is more stable. Is it the 1 degree or is it the 2 degree? Is it the 1 degree free radical stable or is it the 2 degree free radical more stable? Of course 2 degree more radical. Right. So 2 degree free radical. This is a 1 degree and this is a 2 degree. See, 2 carbon attached, so 2 degree. 1 carbon attached, so only 1 degree. So automatically 2 degree will be more stable. And we know that the more stable product is the major product. So this is going to be more stable intermediate. So this will be forming the major product. So if I write CH3CHBr, CH3 plus HBr, then it is a correct one. But if you write this one, CH3, CH2, CH2Br plus HBr, then that is going to be a minor product. But minor product, if you mention in your answer, that is going to fetch you no marks. You have to mention the major product, not the minor product. This is the minor product that you cannot mention. If you want to mention along with the major product, it is a different thing. But only minor product you cannot write. Did you understand that how am I getting the answer? It's not like copy, pasting, raktamara. No, not that. Okay. We have got a free radical intermediate over here, and we have to just see that which free radical is more stable. Whoever is more stable, they will be the major product. As I have told, only and only carbocation shows the possibility of rearrangement. No other thing shows the possibility of rearrangement. So don't rearrange the free radical over here. That is not possible. Okay. Acha. In carbocation also on the classical carbocation, non-classical that don't show rearrangement. That also I have told you. So please remember that you don't end up shifting a free radical from lower part to higher part. That is less alpha hydrogen to more alpha. Only carbocation you can shift. Clear or not clear? Understood? So this is how you can prepare alkyl halides from alkanes. Class 11 done already. Still I have discussed it for around 15 minutes. So I think now you should not make any error on this. Done? Can we move on to the next one? Okay, fine. Next we have from alkenes. From alkenes. Again, this is also what you have done in class 11 from alkenes. This is also you have done in class 11 alkenes. What is alkene? Double bond containing system. Which double bond containing hydrocarbon is called alkene. That everyone knows. How will you prepare alkyl halide from alkene? Very easy one. Done in class 11. How? Suppose you have a C double bond C system like this, and you are reacting it with HX. Then what do we get? C double bond breaks, one side hydrogen attaches, other side X attaches. Right or wrong? And this is the case. This is anti-addition, so I have written it one upore one niche. Clear? So this is a very simple thing that you have done, nothing to worry about, nothing to do anything. This is a very easy one that you have already done in class 11. HX, HBr, HCl, HI, anything it can be. Okay. Do you want to know the mechanism? I hope you don't want to, but still I will say. You have done in class 11. Mechanism, let us understand first, then I will be giving you the example. Mechanism. We have C double bond C. Let us break the C bond. HX already broken down into H plus and X minus. So this bond breaks means what it will form? Carbocation and carbon ion. So this side will get minus, this side will get plus. I hope no problem. So plus and minus, what will do? Who will attack over here? Someone or the other must attack. Then who will attack? The plus attacks minus. X minus won't attack now. X minus will attack a little bit later. H plus will immediately come here. Okay. H plus will immediately attack over here. So what will happen is C positive, then it will be H. Okay, clear. Now carbocation is being formed. So please remember carbocation intermediate. Carbocation intermediate rearrangement. So wherever you are getting a carbocation, rearrangement possibility will be there. So rearrangement you have to look for. What will happen in the next step? In the next step, Mr. Chlorine will come and attack. Whoever is halogen, sorry, not chlorine only. It will come and it will attack the carbocation and ultimately will form this. Okay, no doubt. Very simple. Go by the mechanism. No need to do anything else. Rearrangement you have to do, because directly if you try to do, you cannot get questions correct, I am saying. Alright. You have learned in class 11 a term called Markovnikov rule, right? Markovnikov rule everyone remembers. Negative part of the addendum attaches to the carbon containing less hydrogen atom. So I am writing it over here. Markovnikov rule. Markovnikov rule. Though actually you should go by the mechanism and not by the Markovnikov rule. Negative part of addendum. Addendum means who? Who is the addendum? This person is called addendum. 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 That means whoever is getting added, যাকে add করা হচ্ছে addendum. Markovnikov rule, negative part of addendum gets attached to carbon containing less number of hydrogen. And it is nothing but actually coming from the mechanism only. Or automatically, if the carbon is having lesser number of hydrogen, no, it will be a 2 degree or 3 degree. 1 degree they cannot have least hydrogen. Then 2 degree carbon is more stable. Common sense, right? So you will be doing it by the mechanism. Markovnikov rule I had to say, so I just said. Okay, don't always go by the Markovnikov rule, because some questions you have to know the concept more than the rule. If you know only Markovnikov rule, then you will find you will not do any rearrangement, you will die in the question. Okay, हो जाएगा question में. ठीक है, next let us understand certain examples. Suppose you have ethylene is the most simplest one. So if I am giving it HCl, then what it will form? It will form CH3 and CH2Br. Done? No problem. Directly this side also hydrogen same, so no problem with that. Acha. This is called symmetrical alkene because both the side of double bond carbon number is same. Markovnikov rule is always applicable for unsymmetrical alkene, because if it is symmetrical, then both sides equal hydrogen will be there. Then what is the use of doing? Same hydrogen both sides. Okay. Now let us talk about a unsymmetrical one. Then what? Let us take this one. Pass HCl. Now what? I can attach here. I can attach here. Where will I attach? Obviously I will attach over here, because here the carbocation will be formed, will be more stable. Here it will be a 1 degree carbocation. Here it will be a 2 degree carbocation. So automatically the 2 degree carbocation will be preferred. So this will become CH3 CHCl single bond CH3. This is going to be the major product. Okay. Tell me, clear or not clear? This is very simple. Just you have to remember that the intermediate that you are forming is a carbocation. If there is a carbocation intermediate, then you always have the possibility of rearrangement. So you have to always look for whether rearrangement is possible or not. If rearrangement is possible, then do the required rearrangement. If it is not possible, then what will I say? Clear? But you have to remember that the intermediate that is being formed is a carbocation. Now tell me, clear or not clear? Should I write it somewhere? Okay, let me write it on your list. Carbocation intermediate. Carbocation intermediate. Carbocation is an intermediate. Achha, clear? So from alkene, how will you prepare alkyl halide? I think it is clear to you. I think there is no doubt anymore. Alright. Can we move on to the next one? Alright, let us move on to the next one. After this, we are going to discuss the from alkenes only. Another variety is there. You will find HX sometimes along with peroxide. Along with what? Peroxide. So that is a different case only. So I can mention this as case 1. Then that will be case 2. Okay. Case. What is the case 2? Nothing much changes I will make. Just I will add one peroxide over there. So I had C double bond C and I am giving it HBr in presence of peroxide. Then what I will get? Here to double both sides same carbon, same number of carbon, so there won't be any difference. So I will get one side X, one side H. No problem. Now mechanism you have to study to know what exactly happened. Mechanism. Now here you see anti-Markovnikov rule follow. Here anti-Markovnikov rule follow. I am writing it at the side. Anti-Markovnikov rule followed. Anti-Markovnikov rule followed. Okay. I will at the side. You might not be able to see, but when I share the notes, you will be able to see. Camera ta okhane ache to okhane dekhte pabe na. When I will share the notes, you will see at that time. Alright, let us talk about the mechanism. Last mechanism we have seen that there is a carbocation intermediate being formed. There is a carbocation intermediate being formed. But here there is a peroxide. Okay, do you know what is a peroxide? A O single bond O. This type of thing is called a peroxide. Right? O single bonded O. This is a peroxide bond. So here I can take peroxide. I can take, usually what peroxide is given to you is the benzyl peroxide. But a peroxide is a peroxide. Whether it is a benzyl peroxide or hydrogen peroxide, does not matter. So I will be showing you with the help of hydrogen peroxide. It will be easier for you to understand. In the book you will get the benzyl peroxide, the bigger one, that you can do. If you want to do with that, you go ahead with that. I am showing it by hydrogen peroxide. It is easier for me to show. Alright, okay. So you understand that what exactly is happening is, suppose I have H2O2. So this will be like this peroxide bond. Achha, let me just hide the H also. So, let me write R double bond OR, okay? R double bond or single bond or single bond. R can be anything. If it is a benzyl peroxide, R will be C6H6. So both sides there will be a phenyl group attached. Then that will be benzyl peroxide. Okay, if you want to go with benzyl only, then let me go with benzyl only. I think in the book it is benzyl only. So it will be PHOOPH. Okay, which is benzyl peroxide. So you can see that this oxygen has lone pairs. This oxygen also is lone pair. And two oxygens are sitting nearby with two pairs of lone pair electrons. Do you understand how much repulsion they will be creating between themselves? So what exactly will happen? This bond will gone. This bond will break. Now, moment this bond breaks, the electrons are equally distributed between these two persons. So what exactly will be formed is the same type. You can see this side and this side similar. So that similar two things will be formed. So I can write 2PHO free radical. Can I write 2PHO free radical? Right? I can write like this, 2PHO free radical. Because two times the same thing are being formed. This side also same thing, this side also same thing. So 2PHO free radical. Done. Now you see that I have the original compound 2RO. Now let's take one RO only I will take. PHO. Okay. And I had HBr. So HBr. Let me break this bond as well. HBr bond broken. So what I will get is PHOH. Got it? This is phenol. This is phenol, right? This is phenol. Here in this case it is phenol. O was free radical. Here hydrogen also got a free radical. So they will form OH. OH, which is phenol. Br now is free as a free radical. So Br free radical. Now we had the original compound C double bonded CC. Let me shift the bond. Let us homolytically break this bond. So I have two options for this. Either it can be that this side, or it can be this side. But here to both sides are same, so not a big deal with that. Okay. Let me take an example very well to understand. So I am taking a 3 compound example. Okay. So let us take the example as CH3 CH double bond CH2. Okay. So you can see that the bond can break in two sides. I have taken the example as this to make you understand the mechanism, because if I take this one, then you will not be able to understand, because same thing is there. So now you can see that there can be two possibilities. What are the two possibilities that can be formed? First one, I can say that a possibility can be formed that suppose CH, one time free radical can develop over here, and the hydrogen, and this can be over here. Br can come and attach over here, and free radical will be left over here. And one time it can happen that the Br comes and attaches over here, and the free radical remains over here. Tell, correct or not correct? There are two possibilities. One time free radical is over here also, here also. So Br একটা জায়গায় এসে attach করবে, আর একটা জায়গায় free radicalটা পড়ে থাকবে. So one time I am seeing that Br is attaching over here. So this free radical is left as it is. One time I am saying Br attaching here. So this free radical is left as it is. Now you tell me which free radical is stable? 1 degree or 2 degree? 1 degree is unstable. 2 degree is stable. So this is 2 degree, but this is 1 degree. So which free radical will be more stable? Automatically the 2 degree free radical is more stable. So I will say that this free radical is more stable. This one is more stable. . This free radical is more stable. More stable. So who will be the major product? This person will be the major product. So major product when I am going to deal with, so I will be considering this one only. So CH3, CH2 free radical, CH2Br. Acha, if Br free radical is formed from here, another HBr molecule was also there. So from there, H free radical can also be freed. So that H free radical from somewhere of the solvent or from the peroxide, somewhere or the other, and H free radical will also be arriving. That will join over here. So I will get CH3, 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 CH2, CH2Br. This is going to be my major product. 1, 2, 3, 4. Done. Clear or not clear? Clear or not clear? Why did I get a speech? So CH3, CH2, CH2Br. Understood that why the main major product is ulta in this case and ulta in this case. In this case to carbocation being formed. But this is proceeding through free radical mechanism. The previous one was by the carbocation mechanism. And this is not by the carbocation formation. This is by the free radical mechanism. Clear? Tell me, understood? So in this case, this will be the major product while this will be the minor product. Okay, this is the major product. That is why I have told follow anti-Markovnikov rule. Now in this case, directly you can follow the anti-Markovnikov rule, but as a carbocation is being formed in the previous case, in that case you cannot just blindly follow Markovnikov rule. You have to do rearrangement whenever and whenever it is required to. So I think this part is clear to you. Now I know that there are two questions coming up in your minds right now. What are the questions? The question number one can be that why are we using POP only HBr? Specifically, I have mentioned HBr, but the previous week we have seen I have mentioned HX. That means anyone can be used. But why am I specifically mentioning HBr over here? The reason is very simple. And this is a famous question also. In class 11, I think this question was asked also. Why is HBr used? Why? Achha, no. The question can be, why does HCl and HI not give Kharash effect? Not give Kharash effect. Answer, you all already know that Kharash effect. First of all, what is Kharash effect? I have not told this term before, but the first time I am using the term. Why? Because this is only Kharash effect. When I am using peroxide, I will be calling it as Kharash effect or Kharash peroxide effect. Okay, this effect is called peroxide effect. Side peroxide effect or Kharash effect, based on the scientist who discovered this. Okay, please don't ignore, written at the side, but don't ignore. Kharash effect or peroxide effect. So question is, why does HCl and HI not give Kharash effect? Kharash effect is shown only by HBr, not by HCl, HI. So intentionally in some questions, what they will do is, they will give you HCl and peroxide. So if you fall in that trap and if you do the anti-Markovnikov, then gone. You have to know that HCl HI does not give Kharash effect. So even if it is given HCl peroxide, you will be following the Markovnikov rule only. Okay. Why? The reason is HCl bond is strong. HCl bond is strong. It cannot be broken down. Problem is there in breaking down. It cannot be broken down. It cannot be broken down easily. Second, HI. HI is very weak. HI is very weak bond. It breaks and forms I2. Do I need I2 for the reaction? I don't need I2 for the reaction. But HI breaks down and instead it forms I2. I2 I don't need, then what will I do with HI? HI bond is a very weak bond, okay, ইজিলি ভেঙে যায়, আর ভেঙে আবার HI দেয় না, ভেঙে আবার I2 দেয়, তো I2 নিয়ে তো আমার কাজ নয়, I don't need I2, I need HI, that I'm not getting. So even I cannot use HI or nor I can use HCl, neither of this I can use. Clear? HCl bond is strong, it cannot be broken down, but HI bond is very weak, it is easily breaking down, but it forms I2 and not HI. Alright, HBr bond is of comparable energy and it gives us the desired effect. So only and only what we can use is the HBr, the rest we cannot use. Clear or not clear? Clear, Kharash effect clear? Kharash effect clear? Let us just discuss one example. Same example I will show you. CH2, CH2. This example I think I already gave you in the mechanism only. Still I am giving over here once. In presence of HBr peroxide, CH3, CH2, CH2Br. Okay, this is going to be a major product. Easy, easy. Next, we have a very small one. I will just tell you the thing. Nothing in details you have to read about that at this level. Okay. Questions are also very less asked from that part. Okay. Next topic that I am talking about is the reaction with NBS. Reaction with NBS. NBS is nothing but N-bromosuccinimide. 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 Okay. If you want to see how it looks like, then it is a very good looking compound. How does it look like is this. This is NBS. Okay. What you have to remember is that this personality is a famous personality who causes substitution at allylic and benzylic position only. Bus. Causes substitution at allylic and benzylic position. Allylic and benzylic position. But simple logic, allylic position, benzylic position, before only I have explained to you. So this personality will only cause substitution at allylic and benzylic position. This is very important and please keep it in your mind. So this is the only thing you have to read. Clear? So this personality is going to do what? They are going to do only substitution at allylic and benzylic position. Now what it will substitute, that is also a question. What it is going to substitute? And what it is having? Bromo? No. So it is substitute bromine. Simple logic. So let me just give you one example. Let me wrap up with this. This is a short one. Suppose I have CH2, CH, CH3, CH double bonded CH2. If I am using NBS, then what will I get? Substitution at allylic position. So allylic position is this position. So what I will get? CH2Br, single bond CH. Then NBS is going to do only at substitution at allylic and benzylic position. Done. Alright. Next, suppose I have this. I am using NBS. 1, 2. Then what will happen? Then simple logic. Substitution at allylic position and at benzylic position. Done. Done. Okay. Next. After reaction with NBS, we have another important reaction. Reaction with X2. Reaction with X2. This is important. Reaction with X2. Achha. Remember, if I am doing the reaction with this halogens, dihalogens, at very high temperature, then it will just do the same thing as this personality was doing. So if I am going to give it at high temperature, at high temperature, then what it is going to do? Causes substitution at allylic and benzylic position. Clear? Causes substitution at allylic and benzylic position. Done. Only this much. So suppose if I have one compound, let us take CH3CH double bonded with CH2. Then if I am going to do with X2 at around let us take 700 Kelvin, then what will I get? I will get CH3 allylic position. So CH2X CH 2CH2. Okay. Oh, this will not be an alkene. Just make one correction. This won't be an alkene right here. This will be an alkene. We are preparing haloalkane. So this will be clear. Clear. So this is going to be the case. CH2X CH2 CH2. Okay, the visit one is a simple one. Let us go to the next one. Reaction with X2. Now not at high temperature. Normally if we react with X2, then what is going to happen? This you have done in class 11 again, but the mechanism might not have been done in 11. So suppose we have C double bond, suppose we have, let us take C double bonded C, and we react that with X2 in presence of CCl4. First one we are going to check for non-polar solvent. Non-polar solvent. What is this? Non-polar solvent. That means the solvent which we are using is not polar. So CCl4 is a non-polar solvent. So X2 in presence of CCl4. Then what will I get as the product? One side I will see I am getting a Br attached, which is an alkene. So another side also I will get Br attached. Right? But the Br will be ulta ulta. Okay, why did I write Br? X I had used. Why did I write Br? X, X. Clear? This is going to be an anti-product. So that is why we are doing opposite direction. Done. This is a very simple one. But the mechanism you need to know that what exactly again is happening. So as to understand. So let's understand the mechanism of this reaction. Let us understand the mechanism of the reaction. XX you are having XX. Let us break the bond. So I can say that somewhere or the other X positive and X negative is being formed. See, actually X positive, X negative does not form. Partial positive, partial negative charges arise. But I am showing it as X plus and X minus so as to simplify. Okay, please do not write this step in the exam. What will you write instead? You will write del minus, del plus like this. Okay, and the del plus center will make attack. But don't write it as carbocation and carbanion because that it does not happen in reality. Okay, so I am getting one del plus, one del minus, del plus, del minus. Now I have the famous molecule C molecule. What it can do? Break the bond. So breaking the bond, then what will happen? Carbocation Babaji will form. This side carboanion Babaji will form. So what will happen? This person will be looking for a plus. This person will be looking for a plus. And this is already plus. Why will it look for a plus? This person will be looking for a plus. So this person will come and attack over here. Right? But the carbanion does not attack easily. That I have already explained to you before why. কার্বোক্যাটায়ন আগে অ্যাটাক করে, কার্বো অ্যানায়নটা পরে গিয়ে অ্যাটাক করে লাস্ট স্টেপে, যখন ডিআইজে ভিএমএ সব হয়ে যাওয়ার পরে গিয়ে এক্স মাইনাস অ্যাটাক করে বিকজ ইট ওয়ান্স লেস থিওরিক্যালি হিন্ডার্ড পার্ট টু ইজিলি অ্যাটাক. Okay, so first attack will be done by the positive part only to the negative part. Then so what it will be forming? So the first part I am getting is carbocation will is forming at the intermediate and this one let's say X is forming. So I am getting a carbocation intermediate. So will there be a possibility of rearrangement? According to you, there will be a possibility of rearrangement. There will be, there should be, but this is not actually a possibility of rearrangement. Why? The reason is If you remember, I have told you that carbocation to shows rearrangement, correct? But which type of carbocation? Classical carbocation only. If it is a non-classical carbocation, it will not show a rearrangement. Now, what is a non-classical carbocation? A carbocation to usually does lacks electron. No. So it is supposedly not to have any electrons, free electrons. But if a carbocation has free electron, then it is called a non-classical carbocation, and their rearrangement is not possible. Okay, you can see this chlorine is having lone pair. Chlorine has lone pair, and chlorine is seeing this plus. Chlorine is seeing that at a plus আছে ওর ঘাড়ে. তো now it says আচ্ছা let me give some electron. তো ক্লোরিন কি করলো, খাচুং করে ইলেকট্রনটাকে দিয়ে দিল. Now chlorine gives electron. Now chlorine gives electron means it will be turning negative, positive, sorry. কার্বনের পজিটিভ চার্জটা শেষ, কিন্তু ওর ওপর একটা নেগেটিভ চার্জ প্লাস ওর ওপর একটা পজিটিভ চার্জ চলে আসবে, স্ট্রাকচারটা এরকম হয়ে যাবে. দেখো এর ওপর একটা পজিটিভ চার্জ এলো, very electronegative element, and plus charge on its head is not stable, so it will try to remove that plus charge easily. For that job, this guy is there. So X minus now comes to attack. Where it will attack? It will attack at one point where it is stable. So it can attack either on this or this, same thing, so no problem. So let's take that X minus attacks over here. The attack করলে এদিকে বন্ডটা ভেঙে গেল. So if the bond breaks, then what will happen? This side it will be X below. X at plus, so again it is gone because the bond breaks. And this side it will be CX double. Understood? So carbocation is an intermediate, but this is a non-classical carbocation. So you cannot just shift the carbocation to somewhere else. You cannot shift the carbocation to anywhere else. Non-classical carbocation, no rearrangement possible. Here I am mentioning non-classical carbocation, no rearrangement. No non-classical carbocation, no rearrangement. Okay, so don't try to rearrange over here. Wherever rearrangement is required, I mentioned it that please rearrange, but here no rearrangement because non-classical carbocation. Okay, so non-classical carbocation, no rearrangement. This is direct question that can be asked, but if you don't know the mechanism of this reaction, very difficult to answer. Here there is a carbocation being formed, but here also there is a carbocation, but we are going to follow the RDS step. This is not the RDS, this is the RDS step. So in the RDS step, the carbocation that is formed is a non-classical carbocation because X is having a plus charge, not the carbo. Clear? So no classical carbocation, sorry, non-classical carbocation, so there is going to be no rearrangement possible. Remember, this case is for non-polar solvent only. We have not discussed polar solvent yet. If we discuss the polar solvent, at that time we will be able to see that there is a little bit difference out there. Okay, so example, I don't think you need any example because this is a very direct one and directly you can do it. Next, let us go to the next. Let me copy this. So now we are going to discuss about polar protic solvent. Okay, before that, let me tell you one important thing. What is that important thing is, you are using bromine in presence of CCl4. The bromine is getting attached, so bromine decolorizes. So this reaction is used as a test for unsaturation. So this is just some points that we can observe. This test is used, what am I writing? This reaction is used as a test for unsaturation. This reaction is used as a test for unsaturation. How it is used? Bromine color decolorizes. Bromine decolorizes. Important? Not that much important, but it is important. Okay. Now, in JEE, the questions you will get is in this format. Fisher projection. This side something, this side OH, again this side something. This way we will get the question. That will be Fisher projection. So two things I am going to tell you that you just remember. This Fisher projection questions will be solved in 2 minutes only. What is that? First one is CAR, Gari, and second one is TAM, not tram. Tram na, Kolkata Street tram er kotha bolchi na, TAM. TAM and Gari. TAM. Car stands for cis. A stands for anti. R stands for racemic mixture. R stands for racemic mixture. Okay. T stands for trans. A stands for anti. Then M stands for meso. So this is going to be very helpful. Okay. Cis, if there is a cis compound and you are doing anti-addition to it, the resultant will always be a racemic mixture. If it is a trans compound and you are doing anti-addition to it, the answer will always be a meso compound. The opposite is also possible. Cis, sin, that will be meso. Cis, sin, meso, trans, sin, racemic. TSR. That I will be telling you whenever it is required. Not now. It will be CAM and TSR. So for now, you remember this. Whenever it is cis anti-addition, then we get racemic mixture. Racemic mixture, what is racemic? D and L, 50-50% mixture is called racemic mixture. Racemization is a characteristic of SN1 reaction, and I will tell all that about later on. So you just remember that there will be a Gari and a TAM. TAM is not TRAM. Okay, STAM, TAM. Car and TAM. So car means cis anti-racemic and TAM means trans anti-meso. Meso compound is something which is having a chiral center. Still, it is a optically inactive compound. Again, to know more about meso racemic mixture, all topics have been discussed in GOC and hydrocarbon. So please go and watch that lecture. Okay. Next, what we are going to discuss is the reaction of X2 with polar protic solvent. Now, what exactly is polar protic solvent? I am not saying polar solvent. Polar protic. Exactly what is polar protic, that I will be telling you a little bit later. For now, just understand polar protic is someone which can solvate both cations and anions. Okay, solvate means dissolve. Solvate means dissolve. So polar protic solvent A, how is the reaction going to happen? We are going to see. See, not much differences arise, but what difference arise, that also we need to know. Achha, this here I will just change X2 in presence of water, and this is going to be a polar protic solvent. So this is going to be water. Instead of water, you can do any polar protic solvent, and this is going to be polar protic solvent. Polar protic solvent. Now what is going to be the change? See, XX bond will break, plus del minus will be formed, no problem. Alkene bond will break, C plus C minus will be formed. X minus will come and attack, no problem. Sorry, X plus will come and attack, no problem. But the problem is over here. Here last time we saw that X minus did one attack, but this time the X minus will not do any attack. So where will be the change? I am showing you the change. The change is, I am highlighting with the white, okay. So carbocation was formed here. Here we have seen that X has donated its pair of electrons to this carbon. So as a result, develop a positive charge. Here we have seen that X minus টা এসে attack করেছিল. This time it will be the OH minus attacking. This time it will be the OH minus attacking. So as a result, we will get what? We will get X and we will get an OH. So this time we are not getting a dihalide. We are not getting a dihalide. We are instead getting monohalide only, but an OH group attached to it, right? Why is now suddenly the OH minus attacking? The OH minus is attacking due to charge density. It is a better nucleophile than Br minus. I say, what terms are you saying? What nonsense terms are this? All the terms meaning I will tell you, but not right now. This is going to be a better nucleophile than Br minus. That is why when there is a polar protic solvent, two halogen atoms are not getting attached. Only one halogen atom will get attached. The other will move out as HX only. Clear? H is there and X minus will move out as HX. Understood? This is polar protic solvent. Very, very important. Polar, non-polar to done in 11. But polar protic was not there in 11 boards. So this time may be asked. Maybe. Because many important topics are there. Other than this, that can be asked, that will be asked. Okay, so this is polar protic solvent that you have to remember. Done? Alright, the next we are going to discuss is from alkenes. Sorry, from alkynes. from alkynes. Now this is again an easy one because you have already done this in class 11. So from alkyne what happens exactly? Let's take an alkyne we have, suppose the simplest one. Okay, so if I give it X2CCl4, then I know that what will happen is one bond will break and both the side XX will attach. The reaction will not stop here, it will continue, and we will see the second bond also breaks. Ultimately it is going to form a single bond, right? So it will form like this, right? This you already know because you have done in class 11. Alright, so this is nothing new, nothing to deal with much. So let me show with halogen acids also one. Suppose you are having AHC triple bonded CH and you are having hydrogen acids, okay, that is halogen acids. So what will happen? The first bond will break, one side hydrogen will come, one side X will come. Reaction will not stop over here, it will continue, and we will find that the second bond also breaks. Another hydrogen attaches over here and there was already one, another one will come. Okay, this results in the formation of a geminal dihalide. Clear? So this is nothing a lot to understand because this you have already done in class 11. I am repeatedly repeating that word that you have done in class 11 so that you can at least recall. Okay, so can we move on to the next one? Alright, next one is very important. So that is from halogen exchange reaction. From halogen exchange reaction. From halogen exchange reaction. This is very important. Okay, this is very important because this will be asked in name reaction. Okay, so the first one we are going to discuss is number 1. We are going to discuss is Finkelstein reaction. Finkelstein reaction. The names are very important. The name is Finkelstein reaction. This reaction is used for the preparation of iodoalkanes. Iodoalkanes. Okay. So this method, Finkelstein reaction, is primarily going to prepare iodoalkanes. Alright. So what you have to use is, you can use RCl. Then you write RX. RX plus NI. NAI in presence of acetone. In presence of acetone, dry. Okay. Then you will get RI plus NX. Remember, X can be chlorine or bromine. Alright. X can be chlorine or bromine because iodine you cannot use. Iodine you are forming. So Rx plus NaI in presence of dry acetone will give you the iodoalkane plus the sodium salt. That is actually sodium halide. So this is the basic thing about Finkelstein reaction. Simple logic, just backstabbing happening. What is that backstabbing? Mechanism is not very big, just backstabbing happens. How? NaI was there, that NaI has broken down to Na plus I minus. So we had Rx, this I minus will backstab this XR. Done. So it will form IR plus X minus, and this is the inverted product. So if there was a chiral carbon, then you have to remember that inversion will happen. So this is the inverted product. Alright, so this was very simple, but you have to remember that whenever name reaction directly will be given, Finkelstein reaction, then you have to write the reaction and explain. Okay, Finkelstein reaction understood? Next reaction, let us move on to reaction number 2 under this category. Reaction number 2 under this category only, that is Schwarz reaction. Schwarz reaction. Schwarz reaction is primarily used for the preparation of fluoroalkanes. Fluoroalkanes. Okay. Finkelstein reaction was for iodoalkanes. This reaction Finkelstein is for Finkelstein was for iodoalkanes. Schwarz reaction is for fluoroalkanes. Okay. Acha. Before starting with Schwarz reaction, let me ask you one thing. Why did we suddenly use this person over here? Why did we suddenly end up using this person? We had so many things to use. Why did we use diacetone only? Because the reason is very simple. NaCl slash NaBr is insoluble in that. Is insoluble in acetone. So if they are insoluble in acetone, they will be settling down. So I can easily separate them out from the reaction mixture. So same thing, product concentration decreases, reaction equilibrium will shift to the forward side. So according to Argentum's principle, the rate of reaction will increase. Alright, basically you are decreasing the product concentration so as to make the reaction yield more products. NaCl NaBr that will be formed will be insoluble. So we can easily separate out that from the reaction mixture. So as a result, I am decreasing the product concentration. Clear? Alright. Now let us come to Schwarz reaction. In Schwarz reaction also, we will be using Rx, but this time the reactant that we are going to use will not be the same. Here we will be using a metal fluoride. A metal fluoride. Okay. Then if I react it, I will get Rf plus the metal halide. This is a Schwarz reaction. If I am reacting Rx with a metal fluoride, then I will be getting the respective fluoroalkane. Here also X will be Cl or Br only. Okay. Now what about this metal fluoride? Which metal fluorides can I use? Remember, metal fluorides that we will be using will be the heavy metals. Like you can use cobalt fluoride COF2. You can use silver fluoride AgF2. You can use Hg2F2. You can use AsF3. You can use SbF3. These are some of the common ones which you will get it. Either of these you will get in the paper. So by the reagents you have to understand that what reaction is this. This is Schwarz reaction that you have to identify from this reagents. So this reagent is very important. Please learn it up. This list is very important. Very important list. Alright. So this is all about Schwarz reaction that you have to study. Clear with Schwarz reaction? Any doubt regarding Schwarz reaction? Clear with Schwarz reaction? Alright, let's move on to the next reaction. We are done from halogen exchange reaction. Now we will be moving on from silver salt of carboxylic acid. From silver salt of carboxylic acid. Okay. This reaction has a special name that is called Hunziker reaction. Okay, this reaction is called Hunziker reaction. Hunziker reaction. So the named reactions are important, right? So you have to remember which reaction and what is the name of the reaction. Alright, so silver salt of carboxylic acid means we will be taking a silver salt. So that's like this, RCOO minus Ag plus. And along with that we are going to react with Br2CCl4 and we are going to heat it. So what we will be getting is, we will be getting RBr plus the CO2 plus the AgBr. This is my Hunziker reaction. Now what exactly happening we need to understand. So what exactly happens, let us check. In the mechanism we will be understanding what happens. Suppose we have RC double bond OO minus Ag plus and we are reacting it with BrBr. Okay, this Ag plus was thrown out already. What happens is this BrBr bond, this Ag plus goes out and Br comes in. So what happens here is RCOO Br. This you can understand why, because one Br will have del plus, one Br will have del minus. So this will move out and this will be coming up over here. So one Br attached. Acha. plus AgBr. Now lone pair over here also, lone pair over here also, here also, here also, here also. Now you see পাশাপাশি so many lone pairs, মাথাটা তো পুরো খারাপ হয়ে যাবে। তাহলে what will happen, this bond will be easily broken down, so this bond will break homolytically like this. Alright, so what will be formed, we are seeing that the formation will be of RCO free radical plus a Br free radical. Now this Br free radical will be going, this R free radical alright, so Br formation clear. Now can you see that this oxygen has a positive, this oxygen has a free radical, that is one electron, and this can undergo resonance, right? So this will undergo resonance, and what it will actually do is it will result in this bond fission as well. So R will be now a free radical, and you can see CO2 has formed along with Br minus. Alright, so now what will happen, this R and this Br will be reacting together to form RBr, and there is all the product. Clear? Any doubt? I am repeating what is happening. First we have a silver salt, O minus Ag plus. Ag plus moves out with another Br. Br has a del plus del minus, so the del plus center is attacked by the O minus. So formation is of RCOO-Br, and Ag takes another Br and goes away. Done. Now this bond homolytically breaks. Why? Due to lone pair repulsion. So due to too much lone pair repulsion, this bond breaks homolytically. So this is a free radical form. Now this free radical will be involved in the resonance. So for the complete resonance, this bond also needs to be broken down. So this bond got broken. So now carbon has a free radical. This free radical and this free radical will be forming a double bond. So ultimately CO2 is being formed, and R free radical and Br free radical is forming RBr. Simple logic, no doubt. Clear with this? This is Hunsdika reaction. So we have learned three important name reactions: Winkelstein reaction, Schwarz reaction, and now Hunsdika reaction. Now you tell me, you have any doubt from this part? Till now what we have done, whatever doubts you have, please write down. Alright, can I move on to the next topic? So we are done with the method of preparation of haloalkanes. Next we are going to deal with method of preparation of haloarenes. So methods of preparation of haloarenes. Now we are going to discuss haloarenes method preparation. First method of preparation that we are going to take up is from benzene derivatives, or benzene, from benzene/benzene derivatives. This reaction in class 11 you have done under the topic benzene in hydrocarbon, right? I am just showing one reaction, you can easily understand. Suppose you have a benzene and you wish to convert it to chlorobenzene, then what you will do? You will be using FeCl3, that also dry or anhydrous, right, in presence of the chlorine. Then you will be getting, and then this will be a dark condition, then you will be getting FeCl3 as a byproduct and HCl as a byproduct, right? Mechanism that in class 11, electrophilic substitution mechanism, that I am not going to show right now, or should I? I think you all know the mechanism of this. Still I am just showing you in brief what is the exactly happening over here. This has a H over here. Let me not show like this. See here, this way is benzene looking like, H is there, right? Now what happens is, this FeCl3 has a vacant d orbital, so it can easily accept a pair of electrons. Okay, that is why its octet is not complete, so it can easily accept one pair of electrons, right? So what we will be doing is, this Cl bond will be actually now a Cl plus plus Cl minus. This Cl minus will be captured to form FeCl4 minus, which is not stable. So this is the required electrophile. Since this is the electrophilic substitution reaction, we need electrophile. So this is going to be my electrophile for this particular reaction. Now what is an electrophile? Who can say what is an electrophile? Something that loves electrons. Something that loves electrons is electrophile. It is not having electron. It is a vicary, so it needs electron. You have to give him some donation. No. So it needs electron, and this is an example of electrophilic substitution reaction. Okay, acha. So this is understood, right? So Cl bond will break down to form Cl minus, Cl plus. Cl plus will be the electrophile, and Cl minus will be going with FeCl3 as it is having a vacant d orbital. So it will form FeCl4 minus, right? So now this Cl4 will come up. This hydrogen is already there. This Cl plus is already there. What will happen is bond will break like this. Let me write it a little bit below. Bond broken like that. So what did it result? Achha, bond broken means this side it will be a minus and this side it will be a plus. I hope that much you can understand that bond JD break korbe, that is a minus, and JD দিয়ে break korbe, that is a plus. So where does a plus attack? In the plus? No, plus will attack in the minus. So plus will attack over here. I am showing it with a different ink so that your brain does not fail. Here it will attack. Done. So what it will form? It will form something like this. Benzene, this bond will be broken, plus HCl. This way. Now it can undergo resonance. This can undergo resonance. I hope you all know how to draw resonating structures. This will come up over here. So the plus will now come here. Bond will be formed here. Cl, H. This bond was there. Now it will come this side. So another resonating structure possible. That is plus is here. Bond here, here. HCl. Okay. Ultimately, I can write this resonance hybrid as resonance hybrid. Now go to class 11. What is resonance hybrid? All the canonical structures, if I am combining, then the original structure that I will get is called resonance hybrid. Canonical structures, the addition of all canonical structures will give me the resonance hybrid. So this is one canonical structure, this is one canonical structure, this is one canonical structure. So if I am adding all the three canonical structures, then the structure that I will get is the resonance hybrid. Now in the resonance hybrid, আমি দেখতে পাচ্ছি প্লাসটা এখানে আছে, এখানেও আছে আর এখানেও আছে. So can I write that the plus has traveled from here to here? The entire path is just traveled, right? Though it is not coming in meta position, that is a different thing. But we cannot omit suddenly in meta position, no? Right. So can I write it like this? You have to show this, huh? This way, dotted, 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 and in between a plus. CLH. This is the way of representing the resonance hybrid. That means the plus has traveled from that ortho to that ortho position. Clear? Clear? Okay. Now we will be picking up any of the resonance hybrids, or you can pick up the resonance hybrid, or you can pick up any of the canonical structure to show the next step. So I am taking this structure. Okay, I am taking this structure because it will be easier for me to show. So I am taking this structure in my consideration. So this was a plus over here, bond was here, ClH. Last step is called deprotonation step. Deprotonation means hydrogen will donate the electron and will leave as H plus. FeCl4 minus was already formed before. This H will now go to this person, take a Cl minus and go. So this will result in the formation of something like this. Check, F plus over here, hydrogen went away, so chlorine alone, but a minus is here, like this. Along with this, I am seeing FeCl3 plus HCl. So what did it do? The hydrogen চুপচাপ একটা ক্লোরিনকে নিয়ে বেরিয়ে গেছে. FeCl4 মাইনাসের মধ্যে যে ক্লোরিনটা এক্সট্রা ঢুকেছিল ভ্যাকান্ট ডি অরবিটালে, সেই ক্লোরিনটার ইলেকট্রনকে নিয়ে বেরিয়ে গেছে প্রায় চুপচাপ. তাহলে FeCl3 plus HCl ফর্ম হয়ে গেছে, যেটা আমার বাইপ্রোডাক্টে ছিল অলরেডি. এবারে প্লাস আর মাইনাস পাশাপাশি কার্বনে আছে আর বন্ড ফর্ম হবে না, তা কি হয়? তাহলে here there will be a bond formation. So the bond will form this way. So did you understand that this is the chlorobenzene that I have taken originally? This one. Clear? So I have got chlorobenzene from benzene. This mechanism is called electrophilic substitution mechanism, which you have already done in class 11. Still I showed it to you. This is the mechanism of this. Okay? Alright? Right. Let us move on to the next one. Next one is a very important one, that is from diazonium salt. From benzene diazonium salt. From benzene diazonium salt. From benzene diazonium salt. This is very important. Very important. Before I will be talking about the actual reaction, you need to know what is a benzene diazonium salt or what is a diazo group. This topic will again come in the chapter organic compounds containing nitrogen, that is the amines chapter. There I will be talking about the mechanism of diatorization. Right now I will be talking about only what is a diazo group. Okay. If you see something like this is a benzene, and on benzene you have N2 plus. This group is called diazo group. This group is called diazo group. Writing it in this way, Rn2 plus. Rn2 plus. This is called diazo group. This is called diazo group. What we are reading is benzene diazonium chloride. Benzene diazonium salt. Normally, if it is an aliphatic compound, then diazonium is not stable. So it results on alcohol on hydrolysis. These all things will come in amines chapter. So if you do not understand now, no problem, because amines I will be telling you in details. If it is a R is a aliphatic, that means normal open chain compound, then the diazo is not stable. So on hydrolysis it will form alcohol. But if it is a aromatic ring, that is a phenyl ring, then the diazo group is stable only at low temperature like 0 to 5 degrees Celsius only. Okay, so if we have to prepare haloarenes from diazonium, first you have to prepare diazonium. That you have to know that how will you prepare diazonium. So diazonium preparation is called diazonium preparation itself is a reaction on amines. Itself is a reaction in amines. That reaction itself is a reaction in chapter amines. There I will be telling you the mechanism, but the reaction is diazotization. So what is the reaction that you are going to study? It is called diazotization. Diazotization. Clear? So diazotization means the formation of diazo. Formation of benzene diazonium ion. Okay. Here I have a aniline. This is called aromatic amine. Aniline. Okay. If I am reacting it with NaNO2 and HCl at 0 to 5 degrees Celsius, then only I will get benzene diazonium chloride, because it is somewhat resonance stabilized. That is why only at 0 to 5 degrees Celsius. Higher temperature not possible. This reaction is diazotization. Mechanism of this reaction is to be discussed in which chapter? Amines chapter. So now I will not tell about the mechanism of this reaction. In amines chapter, let it come, there we will discuss. So aniline, NaNO2HCl, 0 to 5 degrees Celsius, benzene diazonium chloride. This is called benzene diazonium chloride. Benzene diazonium chloride. Alright, clear? If I am trying to zoom it, then what will be the exact structure? Like this, N triple bonded N, Cl minus, this way. Okay, together we address N2 plus Cl minus. Done. So benzene diazonium chloride, clear? So from aniline we can prepare benzene diazonium chloride. The reaction we are following is called diazotization. Now that is not our maqsad. What is our aim? To form what? To form alkyl halides. Alkyl halides? No, haloarenes you have to form. So aryl halides you have to form. So that is our reaction that we have to study, how to form aryl halides. So I am giving you the reaction that you have to follow. Reaction number 1. Reaction number 1 under this is Sandmeyer reaction. Reaction number 1 is Sandmeyer reaction. Now where is the problem, you know? Sandmeyer and the next reaction that will come is Gutterman. Those two reactions will be the confusion, because they are more or less similar. The reagent is little bit different. Let us discuss, then we will understand. See here, Sandmeyer reaction says that you have benzene diazonium chloride, you react that with C2Br2, you react that with C2Cl2, then you will get the respective salt this way, plus N2 group will easily leave. Here also you will get Cl and N2 group will leave. Fine, very easy. Sandmeyer reaction clear. So in the Sandmeyer reaction we are using the copper salt, the copper bromide or copper chloride. Now why am I writing Cu2Br2? Because CuBr is not stable, it forms a dimer, so dimerized, so we write C2Br2. Alright, C2Br2 clear, understood. C2Br2 C2Cl2 is Sandmeyer reaction. Now what is the second type of reaction we are going to study? That is called Gattermann reaction. Now I know everyone will pronounce it as Gattermann reaction only, but in the exam please don't write this. In the exam if it is seen that you write this Gattermann reaction, then gone directly. What is gutter? You write gutter in the reaction. That is not gutter. We say it gutter, but it's not gutter. It's Gattermann reaction actually. Alright, so in the Gattermann reaction what happens is benzene diazonium chloride. This time what changes we have done is we have used Cu slash the acid. We have used Cu slash the acid. Last time you have seen we have used the copper salt only, copper bromide, copper chloride, but this time we are not using the salt directly. Instead we are using copper and HCl, so that the reaction will happen and then it will form CuCl2 ultimately. So this will also form the same product. But what changes are there in the reactant? You can see the changes are there. One is Cu2Br2 and second one is Cu slash HBr. So did you understand where is the difference? One case we are using the copper salt, other case we are using the copper slash the acids, halogen acids. Clear or not clear? Clear or not clear? Because confusion will happen between Sandmeyer and Gattermann, but you cannot get confused. One is a copper salt, other is a copper and the halogen acids. Clear? Make it clear. Next one is Balch-Schiemann reaction. Balch-Schiemann reaction. Acha. Before coming to Balch-Schiemann reaction, if you have to prepare iodine, this I am writing on a separate side. If you have to prepare iodobenzene, then you cannot use this copper Cu2I2, that is unstable. You cannot use Cu slash Hi, that is also not possible. Okay. So what you have to use is Ki. Instead this you have to use Ki. So you use Ki, then you will get I over here and N2 will move out. This is a different type of thing. The reagent is different. Don't end up writing Cui or Cu2I2 or Cu slash I2 or Cu slash Hi. Clear? Don't write that. Now come to Balch-Schiemann reaction. Balch-Schiemann reaction is basically N2 plus Cl minus. We are going to use HbF4. This is called fluoroboric acid. I am writing in bracket fluoroboric acid. In this, what happens is the Cl minus gets replaced by Bf4 minus ion. Upon hydrolysis, you will get fluorine Bf3 N2. Clear or not clear? This is Balch-Schiemann reaction. First, you have diazonium. You react it with fluoroboric acid. Bf4 will replace Cl minus. Do hydrolysis. You will get fluorobenzene. Bf3 will move out on its own, and N2 will obviously go. This is Balch-Schiemann reaction. Clear or not clear? Alright. Now let us discuss about the Physical properties. Now what we have learned was the method of preparation. Now we are moving on after the method of preparation to the physical properties. So let us understand what are the physical properties that we need to remember. Physical properties. Number one, you need to remember BP and MP. Boiling point and melting point. Very, very important. Boiling point, melting point. Always remember that whether it is BP or it is MP, melting point is for solids, boiling point is for gases. So whether it is boiling point or melting point, it will be proportional to the intermolecular forces. It will be proportional to what? Proportional to the intermolecular forces that are present. Alright. Now in the organic compounds, the intermolecular forces that you will mostly see is the van der Waals force. Van der Waals force. So here we have to mostly deal with van der Waals force only. Alright. Remember, BP or MP is proportional to van der Waals force. And van der Waals force is again proportional to what? It is proportional to the surface area. Van der Waals force is proportional to surface area. Okay, more surface area, more van der Waals force, so more will be your BP. Alright, so please remember these two things because this is very important. Alright, so now let me write down just point you can understand. See, if I am writing Ri, R, Br, R, Cl, Rf. Now you see halogen size is more, halogen size less. So lesser halogen size means force will also be less. More halogen size, so forces acting will also be more. So automatically this will be the order. Okay, here I am writing in bracket. Why is the order so? Due to size factor increases, then the melting boiling point will increase. Alright. Second point you need to remember that if I am increasing the number of carbon with increase in number of carbon, van der Waals force increases. Van der Waals force increases. Now if van der Waals force will increase, then what will increase? The BP or MP will also increase. Clear? So if number of carbon is increasing, van der Waals force will increase. So if van der Waals force increases, the surface area will increase. Surface area increases means BP MP will also increase. Clear? Achha. Next, BP of, this is an important one, BP of isomeric dihalobenzene. Isomeric dihalobenzene. लिखे बेंजीन लिखिए. Isomeric dihalobenzene are almost identical. Because their surface area is same, more or less same. Is almost identical. Okay. Reason is surface area same. So if surface area is same, van der Waals force will also be more or less same. So if more or less van der Waals force is same, then boiling point, melting point also, boiling point will not change. So I am meaning that this one is an ortho, this one is a meta, and this one is a para. Then their BP order will be same. Almost same. I am not saying that it is same. Almost it will be same. BP of isomeric dihalobenzene are almost identical because their surface area is almost same. Clear? Achha. Next. Next point that is important to notice. This was only for boiling point. Okay, not for melting point. For boiling point, all are mostly same. But if I come to melting point, then para is more than ortho and meta. MP of para isomer is more. MP of para isomer is more as compared to ortho meta. as compared to ortho and meta isomer, because para isomer is symmetrical. Para isomer is symmetrical and fits into the crystal lattice and fits tightly into crystal lattice. Clear? What is a crystal lattice? If you have read solid state ever, I know you haven't read, but if you have ever read solid state, then you must have seen, I'm showing you a cube over here. If I am following a, if I am drawing a benzene like this, you can see one chlorine will be along this and one chlorine will be along this, right? But if it was not a para isomer, then what would happen? One chlorine will be protruding out from here suddenly in between, that is not along any side. Similarly for meta also একদিক দিয়ে বেরিয়ে থাকবে এইভাবে. So what is this? একদিক দিয়ে বেরিয়ে আছে. So easily that can be broken. But if you see para, then it will easily fit inside the crystal lattice. So it is difficult, a little bit difficult to break it. So you need more energy. So that is the melting point is more of para isomer than ortho and meta isomers. Clear or not clear? Understood? Simple thing, concept clear. Okay? We make it a little bit small. Alright, clear? Done. So this was our first point, BP and MP. Let us move to our second point. Point number 2, density. Point number 2, density. Okay. Density, I will just say two things. For first of all this one, Ri, RBr, RCl, RF. And secondly, I will talk about different methyl groups like CH3I, then it can be CH2, CH2, CH3CH2I, then it can be C3H7I. If the R group is same and only the halogen groups are different, then whosoever size is more, that will be having the more density, because mass will also be more. Size more means mass will also be more and volume will also be more. So automatically the order will become this, because mass will be more. So here I am considering the mass factor. But when the alkyl groups are different and the halogen groups are same, then I have to consider the volume factor. So in this case, this will be the order? No. The order is going to be this. Why? Reason is, if I am going to increase this alkyl groups, alkyl group increase means surface area decreases. Surface area decreases means obviously MP and BP density will also decrease. Clear? Did you understand this? This is due to decrease in surface area. Due to decrease in surface area. Alright. So increase in alkyl groups always going to decrease the density. More alkyl group, density decreased. So just you can write it down. More alkyl groups. More alkyl groups. Density decrease due to surface area decrease. Okay, or you can say surface volume decreased. Done. Next, solubility. Here also only one liner I will give. Nothing much to discuss about solubility. Haloalkanes and haloalkanes are not very soluble in water. Haloalkanes are slightly soluble in water. Okay, haloalkanes are slightly soluble in water. Why? Acha, two things can be soluble in water. When are things soluble in water? When they can form hydrogen bond with water, right? So haloalkanes, they cannot break the existing bond and form new bond. That is why haloalkanes are not soluble in water, or little bit soluble in water. Did you understand? আরে water molecule এর মধ্যে টাকা থেকে hydrogen bonding আছে, So first I have to break the bonding between hydrogen and between water molecule, and then I have to form a hydrogen bonding between the haloalkane and water. So breaking that bond is only not possible, and how it can form a new one. And even if it is a part of it is forming, that is not of the same energy, that is slightly soluble in water. Okay, did you understand? I am not writing that because I have told you, you understand from there what I have told. ইনিশিয়ালি যে বন্ডিংটা ছিল সেটা আইদার ভাঙতে পারেনি, বা যদি ভেঙে থাকে, the new bonding that has been formed is not of that much energy as it was previously. That is why haloalkanes are slightly soluble in water. No one will ask you in details, just you need to know the concept. Okay, done? Clear? Acha. Alright, solubility clear. Now I will discuss two important terms that you will be getting as on when you proceed with organic. Many where you will get this same thing. So let me introduce you to that term. What is that term? That term is polar protic solvent, polar aprotic solvent. Achha, if you remember, we have done one reaction with X2, that is reaction with bromine, in presence of CCl4, in presence of water. What was the difference you have seen? Do you remember the reaction? If you are reacting Br2 in presence of CCl4, then double bond will break, or whatever the unsaturation is there, it will break, and both the sides Br will be attached. But if it is Br2 in presence of water, then one side Br attached, one side OH minus will attach. Actually it will attach as OH only. Why? Because the nucleophilicity of OH minus is greater than Br minus. That is the reason. So you have seen that if we are changing the solvent, the product is becoming different. So we need to understand what exactly these two terms are. So let us understand the two terms. The terms are polar protic solvent. As a non-polar, so you already know when dipole moment is 0, that is a non-polar one. CCl4 is a non-polar solvent. Achha. Polar protic solvent. And second one you will be learning is polar aprotic solvent. Polar aprotic solvent. Now let us understand it with you. Let us understand that what is polar protic, what is polar aprotic. Achha. Let us understand by a simple example. What is the example? The example is, suppose you are here, right? You are here and you are trying to, let us take, reach this place. There is a, let us take a body. Does not look like a house though, but just consider it as a house. Okay, you are trying to reach the house. Now here around you have too many people around you. Let's take, like, what to say, very bheer bhar. Too many people are around you. That's how will you understand which one is you? Wait, let me differentiate. Otherwise you will ask which one is me. Let me make it red color. Now where did the partner come from? Sorry. Let's take this is you. Okay, this is you. And these are your partners. Let me take, not partners, like normal people. They are crowded over here. Too many people, huh? Okay. Fine. So if you want to reach your body, তোমার দরকার যাওয়া বাড়িতে, তুমি আছো এখানে, তোমার আগে এত বড় ভিড়। Now can you easily move through that? No, you have to push the people around. You have to push these people around. You have to throw the people, not throw the people, actually is a wrong word. You have to push the people aside, then you have to. Now suppose you have one of your friend over here, who is over here. Okay, then what will happen? Will you be able to reach faster, or will your friend reach faster? Obviously, your friend will go faster. So what did just happen? You were actually surrounded by a lot of other people. That is why you could not move properly. You were hindered by people. But this person was free to move, so he could easily move. Same thing applies for here in chemistry, in solvent. Remember, when I was talking about, let me go to this one, you understood that what exactly is happening? Something like this is happening. Now let me remove all this. Now you see, when I was talking about Br bond, I told you that Br bond actually is Br plus and Br minus, it will break, right? Now Br plus 2 will be a different person. He will be easily going. But the problem is with Br minus, not Br plus. Acha. Br minus is over here. All around is water molecules. So what will water molecule do? Water molecules hydrogen sites like this way though. Another water molecule like just take hydrogen, let's say hydrogen, like this. So what they will do is, they will try to do this. They will try to hold back the Br. তাহলে the same condition is now applying over here. যা একটু আগে হচ্ছিল, what was happening, that you could not move because there were a lot of people around. Now this Br minus cannot move because Br minus এর চারপাশে অনেক লোক এসে গেছে। আচ্ছা, OH minus, meanwhile OH minus that is present in the solution is a different guy. He is to free because he is to water part only, na? So he is free, so he will easily go and attack rather than the Br minus attacking. OH minus will go. Why? Two reasons are there. OH minus is not sterically hindered by water molecules because it is a part of the water molecule only. Secondly, OH minus, first reason you understand that OH minus will not be sterically hindered. Why it will not be sterically hindered? Because OH minus is a part of the H2O molecule only, na? H2O is what? H plus plus OH minus. So OH minus is a part of the water molecule. So it can go easily and attack before Br minus can do so. Why? Because Br minus is being sterically hindered by other parts of the thing, right? Second, its nucleophilicity is more than Br minus. Lesion is same. Did you understand? Did you understand why OH minus is attacking instead of Br minus? Because Br minus টাকে তো যাকে ধরে রেখেছো ও অ্যাটাক করবে কি করে? ওকে তো আগে ছাড়াও তারপর তো অ্যাটাক করবে। মানে OH minus তো আরামসে গিয়ে অ্যাটাক করে দেবে। Another reason for OH minus being attacking is OH minus এর সংখ্যা বেশি, it is in more number. Quantity ज़्यादा है ना, तो the number is more. So if the number is more, automatically it can attack faster. Did you understand? Clear? So this is the concept of type of solvent we are using. Now if we are not using this water, then OH minus এর কোনো উৎপত্তি নেই। OH minus कहीं से आएगा भी नहीं, आएगा नहीं तो OH minus अटैक करेगा भी नहीं। समझ में आ गया? इजी है जो भी हो। ताले when I am using CCl4, then there is no question of all this because CCl4 is a non-polar solvent. So there is no question of all this. So Br minus will come and it will attack. Simple. Did you understand? Did you understand all this? All this 4 minutes of faltu bakaing? Just erase all this. So what is polar protic solvent? We have understood the polar protic solvent. Example, write down water. Okay, example will be water or phenol, etc. I am not just giving two, many are there. These are all polar protic. Why? Because it can jakre dharaing the molecules of the carbon ions. Actually not the molecules, the carbon ion. Carbon ion take surround korte pare. That is why it is a polar protic solvent. So the main thing I need to remember is solvates মানে ওই যে যাকে ধরাটাকে সলভেশন বলে, ঠিক আছে? Solvates both cation as well as anion, both cation as well as anion. ওকে, সো পোলার প্রোটিক সলভেন্ট যদি হয় তাহলে ক্যাটায়নটাকেও ধরবে, অ্যানায়নটাকেও ধরবে। এবারে পয়েন্ট হলো ক্যাটায়নটাকে ধরবে কি করে? সিম্পল লজিক না, ধরো Na+, this you have studied either in S block. Those who have studied S block, they know already, and if you have not studied S block, no problem at all, just understand it. Na+ gaseous state, when it is dissolved in water, when it is dissolved in water, it gets converted to Na plus aqueous state. This, during this time, there is an energy called hydration energy that is released. The energy is called hydration energy that is released. Hydration energy that is released. Release means loss. Loss means minus. So minus. Delta will be negative. Whatever. Achha. So Na plus. Do you understand? Na plus, when it was in gaseous state, when we are dissolving it in water, it will form aqueous state. So it will become Na plus. And that is this, during this time, the energy that is released is called hydration enthalpy or hydration energy. This you have learned in S block. If you have not read, then just listen to me. So what happens is, Na plus is a positively charged ion. Na plus is a positively charged ion. So water's negative center will be attacking this. So the negative center of water is oxygen. So like this. Now let me keep copying this because I cannot draw it repeatedly. Let us take which I am showing using 6, 7, but there will be many, There will be many. So which center will attack? The oxygen center, because only the oxygen center is having negative charge, Hydrogen is not having negative charge, they are having positive charge. So I am just turning all this, bringing them closer. It will be here only. So what will happen? Oxygen's negative charge, bond interaction, 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 interaction. This one also will form an interaction. Did you understand? So what is happening? Na plus take dhore niche. So Na plus take jodi dhore na hai, tale what will be the condition? You understand? Na plus easily move korte parbe na. That is why one question was asked in S block. In periodic table there has been a question. Li plus, Na plus, Li plus, gaseous state, Na plus, gaseous state, rubidium, K plus, gaseous state, Rb plus, gaseous state, cesium plus, gaseous state. Then the order will be obviously this, right? This you already know. The order of size is this. Achha. Now if I am giving the same question, but I am just changing it to aqueous, Na plus aqueous, K plus aqueous, Rb plus aqueous, Cs plus aqueous, then what will be the order? Just ulta, this way. Now the question is why? Though this is an S block concept and not an organic concept, but since I am talking about solvent, let me just tell you. This will waste some time, but that's not a big deal. You are learning something. So what is this happening over here? The concept is very clear. Listen to me carefully. Achha, think very logically. Think very, very logically. Achha. Suppose you have a very small object like this. Let's take very small object, and you have a this much big object. Okay, you have this much small object and you have this much big object. Alright. Now you tell me, if I am considering this to be magnets, there are iron pieces. Who will be attracting more? Obviously the bigger magnet will be attracting more because it has more surface area. But that is a practical physics. But we are not discussing practical physics. We are discussing chemistry. So think in chemistry, if we have lithium plus, that is chotto size atom, it is also having a plus charge. Na is also having a plus charge. But Na size eta, lithium is size eta. So who is having more charge density? Who is having more charge density? Now charge density to physics concept again. Charge density to physics concept. Charge density to physics concept. Naki? Li plus, let us take the Li plus, radius is R. And Na plus, let us take the radius is R, capital R. Where capital R will be greater than smaller. Always it has to be. Now I am talking about gaseous state. Don't think this is aqueous state. No, this is not aqueous state. I will talk about aqueous state. This is gaseous state. In gaseous state, if I am taking R, and in aqueous state if I am taking R, then R will be greater than R, right? So if I am going to find out the charge density for lithium plus, then what it will be? If it is having, let us take Q amount of charge, though it will be a negative Q amount of charge, but I am taking the magnitude of the charge divided by 4 pi R square, assuming it to be a spherical, and for this I am considering Na plus, then it will be Q by 4 pi R square, the charge is same. So from here I can say that sigma Li plus will be greater than sigma Na plus. I think no doubt regarding that, right? So if the charge density on a smaller atom is more than bigger atom, then who can attract more? Obviously the one with the greater charge density. যত চার্জ ডেন্সিটি বেশি তত টানতে পারবে নিজের কাছে। This was same for Fajan rule as well. Smaller the size of cation, greater the extent of polarization. Fajan rule, right? হ্যাঁ, so যত সাইজ ছোট হবে তত বেশি টানতে পারবে। So that's simple. So Li plus charge density is lesser. Greater. It's great. So it can automatically pull more amount of electron towards it, right? Now here to we are not pulling electron, here to we are pulling a negative center. So charge density higher, size smaller, then it can pull greater number of water molecules towards itself. That is why the radius in aqueous state of lithium plus is more than sodium plus. Okay, in aqueous state lithium plus will form this type of layers. If lithium form this many layers, then sodium will form, let us take this many layers. So size of lithium plus will be more. This is the lithium plus. Clear? So in solvent, in polar protic solvent, the solvent molecules come close to each other and the negative center of that solvent will be forming interaction. I am not saying forming bond, forming interaction with the cation or the anion, whatever it is. If it is the cation, it will be the negative center. If it is the anion, it will be the positive center. Done. Now I got deviated from the topic. I was discussing haloalkanes and I came back over here. So that's not a point. But you have learned something, that is hydration enthalpy. So the interaction formation जब होते हैं, जब interaction form हो रहा है, तब जो energy बाहर गया ना, उसी को हम लोग hydration energy बोल देते हैं, ठीक है? समझ में आ गया सबको? तो ये थोड़ा सा S block का concept आ गया. No problem with that. So polar protic solvent understood that solvates both cation as well as anion. Point, only that much you need to remember. Next comes polar aprotic. Polar aprotic না আরেক লোক। Polar aprotic কি করে? Solvates only cations. এই আরেক লোক only cations। কি করে? Solvates only cation। কারণটা কি? অ্যানায়নকে সলভেট করার কারণটা কি? অ্যানায়নকে সলভেট কখন করবে? যখন নেগেটিভ পার্ট, অ্যানায়নটা তো নেগেটিভ পার্ট, তাহলে যে সলভেন্ট মলিকিউল আছে তার পজিটিভ পার্টটা যখন ফ্রি থাকবে তখনই করতে পারবে। মানে जब पॉजिटिव पार्ट इंटरेक्शन फॉर्म कर पाएगा ना एनायन के साथ, तभी तो होगा ना, तभी तो ये होगा, नहीं तो नॉट पॉसिबल ओनली। सॉल्वेशन क्या है? सॉल्वेशन इज बेसिकली interaction formation between the negative positive or positive negative centers, right? So if the interaction is unable to be formed, then solvation of that particular thing is not taking place. Simple logic. So if I am saying solvates both cation, that means cation के साथ interaction form करते पारे, anion के साथ भी interaction form कर सकता है। अगर मैं बोल रहा हूँ solvates only cation, इसका मतलब सिर्फ और सिर्फ cation के साथ ही interaction बनाया जा सकता है, एनायन के साथ नहीं बनाया जा सकता। मतलब क्या है? मतलब यह है कि जो पॉजिटिव चार्ज है, जो सॉल्वेंट मॉलिक्यूल का पॉजिटिव सेंटर है ना, उसको स्टेरिकली किसी ने बंद करके रखा है, उसको स्टेरिकली किसी ने बंद करके रख दिया है। मतलब पॉजिटिव सेंटर is sterically hindered by some bulky groups. What are the bulky groups? We have to discuss. So solvates only cations cannot solvate anions as positive center is sterically hindered. Examples. Example is DMSO, the most common one you will find, dimethyl sulfoxide. I cannot write this much long, so I am saying, please listen. Dimethyl sulfoxide, dimethyl sulfoxide, dimethyl sulfoxide. It's easy, huh? No need to think here and there. Dimethyl is two methyl supposed to be dimethyl sulfoxide, means in between there will be S double bond O. But simple, dimethyl sulfoxide. None. This is DMSO. This is DMSO. Another one you have is DMS, dimethyl sulfide. Dimethyl sulfide. So it's simple again. CH3 S CH3. Okay. Achha. DMS again is acetone. Acetone, I hope you already know what is acetone. This one will be C double bond. Then only it is acetone. This is CH3 S CH3. Achha. Another one is DMF. I am giving you 4 examples, many more are there. DMF. DMF is basically dimethyl formamide. Dimethyl formamide looks like C double bond O H N CH3 CH3. Amide, CONH is an amide. CONH2 ना हो, it is CONH CCH3 because it is all dimethyl. Formamide, dimethyl. Clear? DMSO, DMS, acetone, DMF. Clear to everyone? Right. DMSO, DMS, acetone, DMF. Remember this? Names are, they will write as DMSO only because the name is too huge. They don't expand it usually in JE. School to leave. JE I am talking about. Okay. So now let us understand that what exactly is happening. Let me take up one structure and explain. Explain করলেই বুঝে যাবে। আচ্ছা, another one, write another one that he will be used in the next chapter. Hydroboration oxidation when I will be doing HMDM. Oxymercuration demercuration I will be doing in the next chapter. Alcohol phenol ether. There OMDM. That time also I will be telling you about that reagent. So just now you note down. It's called THF. The reagent is THF. What is THF? THF is tetrahydrofuran. THF is tetrahydrofuran. Like this. Okay. This is tetrahydrofuran. Just note it. No doubt. Nothing to remember. Just note it. THF. This will come in the next chapter. Achha. So now let me take up one structure and try to explain. This one you can note for your reference. I am not deleting the slide. If you want to note down, you can note down. Suppose I am taking dimethyl sulfoxide, DMSO, the most common one. Right? Let us find the hybridization of this guy. 1, 2, 3, 4, 5, 6, 7, 8. No lone pair. Lone pair gone. 1, 2, 3, 4, 5, 6, 7, 8. No lone pair. So the hybridization will be 1, 2, 3. Leave hybridization. No need to find the hybridization right now. Hybridization will be confusing you more. Hybridization will be tetrahedral, but I am not saying because I have not taught you that chapter only, chemical bonding. No need to hurt your brains now. S double bond O, CH3, CH3 like this. Who is going to be the positive center? Definitely this. But these two groups are very, very bulky groups. These two groups are bulky groups. So whenever S will say, come to me, I will hold you, immediately the CH3 group will repel and it will say, no, don't go. And there is not one molecule like heroin. That's why I have told you. See, there are not one molecules doing this. There are a lot of molecules. So intermolecular CH3 repulsion will take place. So ultimately, the S, the positive center, cannot solvate, cannot form interaction due to this. Okay. So I am writing here, cannot form interaction. Cannot form interaction. So if it is unable to form interaction with anion, if it is unable to form interaction, that is not happening only. Understood? Think simply, it will be done. Think simply. Achha. This one, do you understand? Any doubt you are having? So these are the type of solvent that you just need to note down. Polar protic solvent, polar ecprotic solvent. No one will ask you also what is the definition of this and that, but the concept that I have told you, that will be utilized everywhere. In this chapter, the entire organic it will be used, and every time it will not be told to you. Okay, done. आगे बढ़े, चलो आगे चलते हैं. दो इम्पोर्टेंट टर्म्स को अभी समझेंगे हम, ठीक है. टू वेरी वेरी इंपॉर्टेंट टर्म्स, very similar, but a minute difference make them different. What is that? First let us understand. The terms are basicity, and second one is nucleophilicity. The two terms might sound very similar to each other, but they are not actually same. Similar to bote, but not same. Why? First, let us understand the concept. What is the similarity between basicity and nucleophilicity? Now, in inorganic chemistry and physical chemistry, you have learned basicity is the number of OH minus ions released when ionization of 1 mole base takes place. Is this basicity? I heard this answer from one of my friends in Google Meet. I was taking his class and he said this answer. I don't want to reveal the name because he will kill me. So he told this answer that the number of OH minus ions released when 1 mole of base is dissolved in water. Is the answer correct? Is the answer correct? No. From no angle is the answer correct. I would have said him that it is correct in IOC or physical chemistry, but he has given me such an answer I cannot even say that. Why? Reason is very simple. Basicity is defined for acids, re baba, not for bases. Basicity is not for base. Basicity is for acids. Acidity is for base. That he forgot. तो यू शुड नॉट फॉरगेट दैट बेस देखलाम आराम से बेस बोल दिलाम, बेस दिख गया तो बेस बोल देंगे. नहीं, ये बेस का है ही नहीं. बेसिसिटी तो बेस का बात ही नहीं है. बेसिसिटी किसका बात है? एसिड का बात है, वो भी फिजिकल और इनऑर्गेनिक में, ऑर्गेनिक में नहीं. बेसिसिटी इज द नंबर ऑफ H plus ions donated, number of H plus ions that can be furnished upon ionization of 1 mole of acid in aqueous solution. That is basicity of the acid. Dibasic, tribasic, sulfuric acid, dibasic acid, that you all know already. And how can you give such an answer? I don't know. But ठीक है, पढ़ाई नहीं किया तो और क्या करेंगे. ठीक है. In organic chemistry, the definition of basic character, the definition of basicity is tendency to donate electrons. First, let me write, understand. Tendency to donate electrons. Tendency to donate electron. Tendency to donate electron. Fine. So tendency to donate electron is basicity. Achha. Let me throw this over here. Nucleophilicity ki. Nucleophilicity is also tendency to donate electron. Now you will kill me. Why? Why are you saying the same thing in both the sides? अरे रुक जाओ, सबर कर लो थोड़ा. Both are tendency to donate electron. No doubt. Both are tendency to donate electron. Both are tendency to donate electron. No problem with that. I am not denying the fact that it is. It is. But to whom is the fact? I am saying I love to donate. I love to donate what? I love to donate taka paisa. Acha, fine. I love to donate taka paisa. To whom? To myself, to my friend, to my relative, to the person sitting outside. To whom? That I have to specify that I love to donate to lower caste people. Though I should not talk about castes, actually that's a wrong concept. Okay. I would like to donate to poor people. That's the point. I like to donate to poor people. I'm saying that I'm donating to the poor people, but I have to say to someone what, right? I love to donate to social service. Fine, that's a social service. I love to donate to NGOs. Fine. I love to donate to political parties. Right, fine. That's your point. But you have to specify that to whom are you donating the electron. Basicity is also to donate electron. Nucleophilicity is also to donate electron, but we have given two different terms. If they are meaning the same, then I should not have given the two different terms. They should be meaning something. Somewhere there is a difference. That is why the terms are different. Otherwise, they can be same. Force and torque doing the same thing, analogous, but we have given two different terms. Why? Force is for linear and torque is for rotational. When you are rotating, you are saying torque, but when we are saying we are pushing something, pulling something, throwing something, that's a force. We are not saying torque, right? Suppose there is a table over here and I have this box over here. I am pushing the box. Will I say I am applying torque on that box? No, because it's not a rotational motion. I am pushing, so I am simply applying a force. But if there is, let us take a rod like this, and it is pivoted against this point. Now if I say I have to push the rod, then I will be giving a force like this. Then I will not say I am giving a force on it. I will say I am giving a torque on it. So where is the difference? Difference is what perspective I am saying it as. If I am giving it in a linear motion, that's a force. If I am doing it in rotational motion, that's a torque. So two different terms mean the two different things, but you can see they are same thing. Things are happening same. Both are moving only actually, but one is linearly, one is rotational. So same here. Basicity is tendency to donate electron to whom? To a hydrogen plus, that is to a proton. To a proton. Proton is what? H plus. Please don't think that proton is proton. No, H plus is the proton. We say H plus as proton. So what is basicity? Basicity is donating electron to a proton. To whom? To myself, to NGO, to political party, to whom? To a proton. Will you forget it? Don't forget. Tendency to donate electron to a proton is basicity. Then what is nucleophilicity? Nucleophilicity then cannot be to a proton. Moment you are giving electron to someone who is not a proton, anyone other than a proton, that is nucleophilicity, not basicity. Clear? That is why you have seen then physical properties, just some time before physical properties you have seen a difference. What was the difference? Difference in the order of nucleophilicity and basicity in solvation and steric hindrance. Basicity is tendency to donate to a proton, and basicity is increased by what? Plus I effect groups. But if I keep such a bulky nucleophile, then it cannot donate electron to a carbon deficient atom, right? So this person nucleophile donates electron to whom? To a electron deficient carbon atom. Now even if it is generally or mostly nucleophile donates electron to carbon atom only. Now if it is a hetero compound, then to that hetero atom will also be considered, but any atom other than H plus will be considered as a nucleophile, not as a base. So you have to highlight this, the two are electron deficient carbon atom. How many of you will forget it? Tell me. How many of you will forget this definition? And not actual definition also. So basicity is donating electron to proton. Nucleophilicity is donating electron to an electron deficient carbon atom. That is usually carbon. If it is not, then whatever heteroatom is there, like sulfur it can be, nitrogen it can be, that is also a nucleophile. Now we have seen Darjan process. There we have seen donation of electron happens to whom? S, sulfur, that's the heteroatom. How many of you remember Darjan process? Don't keep forgetting, huh? I might keep knocking you of the previous things. Darjan process, what used to happen? S double bond O Cl Cl, like this Darjan process was there, right? And we had ROH. So we have seen this two lone pair attacks over here. This bond breaks like this. We have seen now. So donation is happening to whom? Donation is happening to a heteroatom, not carbon. Then is this a base? No, this is a nucleophile. Why? Because it is attacking to someone else other than a proton. Okay. Another small thing, let me just write over here, though I should not write that because in class 11 you have already done basicity is proportional to plus I effect. That means more electron donating groups attached, basicity will increase, and it will be inversely proportional to minus I effect. This so I think you already know because you have done in class 11. Nucleophilicity as such I cannot say right now. Just remember nucleophilicity is inversely proportional to steric hindrance. Nucleophilicity inversely proportional to steric hindrance. You have to minimize steric hindrance, otherwise nucleophile cannot attack properly. Tell me, clear or not clear? I have wasted 30 minutes on basicity, nucleophilicity, solvent. But I have to make this point clear so that the concept that will come next will be clear to you. Achha. Clear or not clear? Clear? Okay. Next we have to discuss the factors affecting nucleophilicity. Factors affecting nucleophilicity. Now half of them I have already discussed while explaining only. Factors affecting nucleophilicity. Factors affecting nucleophilicity. Okay, I might speed run because I have already explained all these things before. First one is charge density. First one is charge density. What will happen? Even if you do not know chemistry, but you have something called common sense. Now, if you don't have common sense, then I have nothing to say about it. कॉमन सेंस नहीं है तो और क्या है, दिमाग तो है ना, दिमाग होगा तो कॉमन सेंस भी होगा. हाँ, अब बात ये है कि अगर आप यूज नहीं करना चाहते हो तो वो अलग बात है, पर कॉमन सेंस तो होगा ही होगा, होता तो হবে না হলে হবেটা কি? তাহলে যার যত চার্জ ডেনসিটি সে বেশি ইলেকট্রন দিতে পারবে. কনসেপ্ট ব্যাক টু এলআই প্লাস পার্ট, চার্জ ডেনসিটি মোর অ্যাট্রাক্ট বেশি করবে, তো অ্যাট্রাক্ট যখন বেশি করতে পারবে ডোনেটও বেশি করতে পারবে. চার্জ ডেনসিটি হাই তো ডোনেটও বেশি করবে, অ্যাট্রাক্টও বেশি করবে. শান্তি বুঝা গেছে? এখানে অ্যাট্রাক্ট করার মানুষ নেই, ডোনেটই করবে, কারণ নিউক্লিওফাইলের কাজ ডোনেট করা. তাহলে চার্জ ডেনসিটি যার যত বেশি নিউক্লিওফাইল ডোনেশনও তত বেশি করবে. তাহলে নিউক্লিওফিলিসিটি কি লিখবো? প্রপোর্শনাল টু চার্জ ডেনসিটি. ক্লিয়ার? Next, before next, let me just give you one example. Let us take OH minus H2O. Who will be more? OH minus will be. OH minus is charge density more. Similarly, if I write NH2 minus, NH3 থেকে বেশি, charge density more. Clear? Next, electronegativity. Electronegativity. Electronegativity I will be abbreviating it as EN. মানে বারবার I will not write this long term electronegativity, instead I will use EN. So don't keep on asking me what is EN. Don't write England. It's electronegativity. I cannot write this every time, so I'm just telling you now only. Remember, whenever we are talking about electronegativity, it will be in same group elements, same period elements. Electronegativity factor when I am considering, that will be among the same period elements. Okay, so this just write it, seen in same period elements, seen in same period elements. Okay, this you have to understand by example only, because there is nothing much to talk about it. Remember order of nucleophilicity. Actually, let me write this on a slide before. Order of nucleophilicity, order of nucleophilicity and basicity is same except for number 1, steric hindrance. See, I have already told you that the order will be ulto. Why it will be ulto, that also I have explained. And second one is solvation. So please, these are the some small things which you need to keep in your mind, huh? Small things that you need to keep in your mind, because every time you can see it is not possible for me to mention that what order is what, that you have to remember like this. So what I have told you, न्यूक्लियोफिलिसिटी का जो ऑर्डर आएगा, बेसिसिटी का जो ऑर्डर आएगा, दोनों का ऑर्डर सेम रहेगा. कब सेम नहीं रहेगा? जब स्टीरिक हिंड्रेंस एंड सॉल्वेशन का फैक्टर हमने कंसीडर किया हुआ है. ठीक है, चलो नेक्स्ट. Electronegativity seen in same period elements. Let's take, suppose we have CH3 negative, suppose we have NH2 minus negative, suppose we have OH minus negative, suppose we have F minus negative. Then what is going to be the order? The order is going to be this. Reason is very simple. Nucleophilicity is inverse proportion to nucleophilicity is inverse proportion to En. Why? If you remember, in periodic table, there you must have read minus charge more stable on higher electronegative atom. So if minus charge is more stable on high electronegative atom, then will it easily donate the electron? No. No. But if the minus charge is on some person who is very unstable, তাহলে automatically it will donate electron faster. So CH3 minus rho4, the minus charge is not as stable as it is on F minus. That is why F minus is a very weak nucleophile, but CH3 minus is a better nucleophile because electronegativity of carbon is low. Clear? So electronegativity inverse proportion nucleophilicity. Clear? जार electronegativity कम, तार nucleophilicity will be more. Clear? 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 Next, steric hindrance. Why did you go back? Next, steric hindrance. Now steric hindrance I have already explained, so I don't think I have to explain again. Steric hindrance, I am just giving you the point. Nucleophilicity inverse proportion of steric hindrance, inverse proportion of steric hindrance. Don't worry, you will get these notes. You will get these notes in my WhatsApp community. So if you have to get these notes, please join the community. I know there will be a camera part here, so you cannot see this. We will get the notes for this. Steric hindrance, nucleophilicity inverse proportion to steric hindrance. Done. Now should I give you the example? Okay, let us give you the example. OCH3 minus OCH, O minus only, CH3, O minus, CH3, O minus, CH3, CH3. Automatically this will be a better nucleophile. But if I am going for the order of basicity, let me just copy it. If I am going for the order of basicity, then the order will not be this, the order will be ulto, this. This one is the order of basicity, and this one is the order of nucleophilicity. Clear? Reason I did not explain. Why? Because OCH3 minus size is small. This has three bulky groups. It cannot be easily attacked. Here, basically proportional to plus I groups. Many 3 plus I groups. It is almost much basic. Clear? Understood? Next, fourth factor, that is solvation. Fourth factor, that is solvation. Solvation meaning understood? Interaction form করবে, that is solvation, right? Now here you remember that solvation will be seen again in same group elements. Like we saw electronegativity for same period elements, solvation we will see in same group elements. Seen in same group elements. Okay? Now, listen to me very carefully because this is an understanding concept. Suppose I have F minus, I have Cl minus, I have Br minus, I have I minus. I am going to compare this same thing in two ways. I am going to compare this same thing in two ways. First one, I will be talking about protic solvent. Protic means polar protic. Concept already explained to you. Polar aprotic, two orders. Or if it is polar protic, then the order will be this. If it is polar aprotic, the order will be this. Why? Let us give an explanation for this. The explanation is very simple. Just listen to me carefully. Who is a better nucleophile? F minus is a better nucleophile or I minus is a better nucleophile? Obviously F minus will be a better nucleophile due to charge density. Charge density is more. So if charge density is more, it will easily donate the electron. I have told you, যার উপর চার্জ ডেন্সিটি বেশি সে ইজিলি ইলেকট্রন ডোনেটও করতে পারবে অ্যাট্রাক্টও করতে পারবে তাহলে F minus এর উপর ইলেকট্রন ডেন্সিটি বেশি তাহলে it can donate electron easily and polar aprotic তো cannot solvate cations cannot solvate anions তাহলে F minus is very much free লাফালাফি করে একদম যাবে and it will donate the electron so required then what is happening in protic solvent that I minus is getting the maximum chance to donate electron ये एमन होच्छे क्या 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 ऐसा हो गया क्या ऐसा हो गया कि I माइनस को मौका मिल गया कि वो जाके इलेक्ट्रॉन डोनेट कर दे सडनली करना तो F माइनस को ही चाहिए था पर I माइनस क्यों बीच में आ गया घुसपैठ क्यों कर गया वो बीच में कंसेप्ट समझो तो समझ में आ जाएगा प्रोटिक का मतलब क्या है प्रोटिक का मतलब है कि F माइनस को तो सॉल्वेट कर दिया गया है Cl माइनस को भी सॉल्वेट कर दिया गया है Br माइनस को भी सॉल्वेट कर दिया गया है अब F माइनस का साइज बहुत छोटा चार्ज डेंसिटी बहुत ज्यादा और ज्यादा H2O को अपने तरफ खींच लेगा तो और ज्यादा खींचो H2O को उतना घिर जाओगे उतना तुम जा नहीं पाओगे তো F মাইনাস কি করলো বড্ড বেশি H2O টেনে নিয়েছে তাহলে H2O ঘিরে নিয়েছে ও পারছে না যেতে তাহলে ও কি করে অ্যাটাক করবে এদিকে I মাইনাস এত বড় সাইজের একটা লোক इतना बड़ा साइज का आदमी आराम से सबको थक करके फेंक फूक के खुद जा रहा है आराम से क्योंकि उसको कोई घेर नहीं पा रहा है कि उसका साइज ही इतना बड़ा है चार्ज डेंसिटी भी इतना कम है समझ में आ गया सबको understood what is the logic F minus size is very small charge density high so it can attract lot of H2O molecules towards it so many interactions are being formed so it cannot easily move but I minus being a very large in size and charge density being very less can easily go and attack so that is why in protic solvent in polar protic solvent I minus can be the best nucleophile but in aprotic solvent F minus will be the best nucleophile understood the logic in aprotic तो solvation is not happening so in that case F minus is छोटो खटो मानुष easily it can move faster than I minus so it will go and attack first later on the I minus will come clear with solvation this is the factors affecting nucleophilicity very important very important direct question may not be asked but the concept that I have told you that will be utilized everywhere so please make sure that you are clear with the concept or not all right now let us understand what do you mean by leaving group this term I will be using many times so just I will be giving you an idea of what is a leaving group so let us understand what exactly is a leaving group so let me just mention leaving group all right now first নাম থেকে মাথায় কি ঢুকছে what do you understand from the name from the term leaving group that means from certain compounds since we are discussing about compounds so from certain compounds a group will leave a group will move out so that group will be called as a leaving group so if from a molecule I am removing a group that is called elimination last time only we have read but if a group is leaving that is a leaving group all right so leaving group is basically one group that will be leaving from a compound example of leaving groups you have seen many first example that I have told you in method of preparation first one be Dargent process the alcohol one the Dargent process you have seen there also the water leaves out be it HX there also water leaves out so that is the leaving group so first let us understand That leaving group, when it happens, mostly we'll find this example in case of alcohol. When we'll go to the next chapter, alcohol phenol ether, there you will see the best example of leaving group. Actually it is in alcohols. All right. For example, I am just mentioning a part of a reaction. Okay, this you will understand in the next chapter. Suppose you have something like RCOH OH2 plus, and you have a OR dash, right? So here in this type of things, what happens is this bond breaks and ultimately this group leaves. Now you can see it is having a plus charge on its end. So if you are giving electron to the plus charge, it will become neutral. So if I am giving electron to this plus charge, then this will become neutral and will leave as what group? OH2 is what? Nothing but water only. That only I have written as OH2. So this will exit as water. So water is a good living group. So water is a good living group. So this will ultimately result in the formation of RCOH plus OR negative plus water. So here in this case, this water will become a living group. This water will become a living group. Clear? So what is a living group? A group that leaves. A group that leaves from a compound. So this is called a living group. Understood? So now basic point that you need to remember about living group is living group, weak bases are good living group. Weak bases are good living group. That means more weaker the bases will be, they will be better living groups. Water is a weak base, so it will be a good living group. Many examples of such things you will get. Now strong base like F minus, that will not leave easily. That is why F minus does not leave easily. That is why elimination is not possible. That is why E1CB mechanism takes place. Right? I have taught you E1CB. Oh, sorry, not yet. E1CB I have not taught you yet. In E1CB you will find that due to this living groups disruption, the normal E mechanism does not take place. Normal elimination does not take place. An abnormality happens. Even CB takes place, that I will teach you just after some time. So just remember, weak bases will be good living groups. Why? Because they will be stabilizing the transition state. The reaction proceeds to a transition state. That transition state will be stabilized. Hence, weak bases will be good living groups. So moment you are increasing the strength of the base, they will not leave easily. If there is a OH instead of OH2, that will not leave easily. That will not leave easily. Clear? But OH2, H2O being a weak base, it will leave easily. The group will leave. Understood? So similarly, the large size halogens, I minus, then Br minus, this will also easily leave. Why? Because I minus is a very weak base. I minus size is very huge, so it's a very weak base, easily it will leave. Clear? So weak bases are good leaving groups. This is very important. Okay, now what I can do is I can give you some examples of leaving groups. Examples. First let me give you good leaving groups. Good leaving groups, and then I will be talking about bad leaving groups. So good leaving groups: water, weak base; ammonia, weak base. I have discussed this, right? Ammonia and NH2 minus. Who is weak? NH3 is weak. That is charged, right? Acha. NH3. Then it can be CH3COO minus, easily going out. So these are the examples of good leaving groups. Now let us come to bad leaving groups. Acha. You can also add the halogen family members, the higher halogens. Just let me mention two: I minus, Br minus. More are there. Don't think this much only. Many more are there. Next comes bad leaving groups. The groups that will not leave easily. Who are the bad leaving groups? F minus, you cannot throw it out. OH minus, you cannot throw it out. NH2 minus, very good base, cannot throw out. OR minus, good base, cannot throw out. So these personalities are very bad living groups. You cannot throw them out. That is the reason E1CB has to take place to eliminate F minus in fluorocompounds. Okay? Understood? Clear? So this is a concept of living group. Questions are not coming from based on living group, but the concept of living group will be required in the next few topics that we are going to discuss. Right? What all we have discussed till now, let me just talk about. We started the chapter with methods of preparation. Let us just revise what we have done. Where did the slide disappear? We started from the method of preparation of haloalkanes. Now we will be moving on to the physical properties that is already discussed. Physical properties also have been discussed already. See here. These are the physical properties that we have discussed. Method of preparation of haloarenes are also have been discussed. So we have to study three things in the chapter: method of preparation, physical property, and what? Chemical properties. So we are done with methods of preparation, we are done with physical properties. What we are left out is with chemical properties. So let us now understand the chemical properties of haloalkanes. First haloalkanes, then haloarenes. Alright, so let's start with the chemical properties of haloarenes. Now starts the reaction part. Okay, now be very careful with the reaction part. Now we are coming to the chemical properties. We are going to discuss the reactions. Under chemical properties, we will be studying under majorly two important reactions: substitution, that also nucleophilic substitution, because electrophilic substitution this haloalkanes do not show. Who shows? Haloalkane does not show. Who shows electrophilic substitution? Who shows? Benzene ring shows. That we will be not reading in this chapter. We have already done in class 11, right? But we will be utilizing it as and when we proceed. We will be utilizing the concept that we have done in class 11. So do not think that 11 is gone. No. We will be requiring the Friedel-Crafts, which you have done in haloarenes. So you cannot forget that. Alright? Okay. So let us start with the chemical properties. First of all, we will be reading about nucleophilic substitution. Second, we will be reading about elimination reaction. Other than that, whatever is there that we are going to study. So first one we are going to discuss today is number 1, nucleophilic substitution. Nucleophilic substitution reaction. It is called NSR. I will be using the short form NSR because it will not be always possible for me to write such a long thing, right? NSR. Now, do you remember what is a nucleophile? What is an electrophile? Do you all remember that? Nucleophiles, electrophiles, right? So let me just quickly brain map. Electrophile is what? A plus charge containing, mostly plus charge containing compound, right? So it attacks which center? It attacks electron rich center, because itself it is not having any electrons, so it needs electrons, so it will attack the electron rich center. What is a nucleophile? Nucleophile is a minus charge containing compound, right? It will be attacking the electron deficient center of a compound because it has rich electrons. It is rich in electrons, so it needs to donate its electrons. So donate करवे कोথায়? যেখানে इलेक्ट्रॉन नहीं, जहाँ पे इलेक्ट्रॉन नहीं है वहाँ पे जाके डोनेट करेगा. तो ये डोनेट कहाँ पे करेगा? जहाँ पे ऑलरेडी प्लस है या फिर वहाँ पे डेल प्लस है, राइट? Clear? So nucleophile will be attacking the electron deficient center of a compound. Clear? This is a nucleophile and another one is electrophile. We are discussing nucleophilic substitution reaction. Alright. So what is nucleophilic? Understood? What is substitution? One atom will be replaced by another atom. One atom will be replaced by another atom. This is called substitution. So nucleophile will replace another atom. This is nucleophilic substitution. Clear? Clear? Nucleophile will be replacing another compound. Nucleophile will be replacing another atom. Then that is nucleophilic substitution reaction. This nucleophilic substitution reaction occurs through two different mechanisms. Already you have done in class 11, but I will be talking about it again because I know right what happened in 11. So nucleophilic substitution reaction we are going to study in two ways. First we will be studying SN1 and second we will be studying SN2. These are the ones which we have discussed in class 11, but other than this there are some special ways in which this reaction can propagate. There are some special ways in which this reaction can propagate. Those special ways also we will be discussing, that is SN2 prime and another one is SN internal. These are the two, SN2 prime and SN internal. These are the mostly we are going to discuss. Mostly we will get SN1, SN2, but SN2 prime and SN internal are the two special type of nucleophilic substitution reaction which you have not done in class 11. This is new to you in class 12. So can we start our discussion on SN2 first, then SN1? Okay, understood. So let's begin with SN2. Your ears should be open. Your brain should be there in the brain box only and not in your cupboard, because if your brain is not there you will not understand and then you will be falling from the sky, because these concepts are very vital concepts. Little bit here and there will make the product wrong in the exam. Did you understand? So let us discuss SN2. Let's move on to the next page, a fresh page and a fresh topic, SN2. First of all, let us expand it. But right now I will not expand. First let us discuss. Upon discussion we will expand it. Alright. SN2 mechanism. So basically, suppose I have a basic reaction. Let us take, I have this way I have written so that it will be easier for you to understand. So I have given a base, right? And I am going to do SN2 on this. So after doing SN2, I will find that my product becomes like this, plus X minus. Now I will say ऐसे क्यों लिखा है? मतलब क्या है? ऐसे क्यों लिखा? Why did I write it from behind? I could have written in front only. I'm explaining now why have I written that like that. For now, just take it like that. Now let us understand what exactly has happened. Alright, okay. So see here. We had a carbon with X. So we know that this bond is polar. So this will be something like this. So we know that OH minus is a nucleophile which will attack on the negative part, right? Right? And you all are saying yes. What is this? What is this behavior? Very bad behavior. Negative does not attack on negative charge. Negative attacks where? Electron deficient center. So where is the electron deficient center? Here. So it will attack over here. Clear? So what will happen? It is attacking over here. But what will happen to the nucleophile? Carbon cannot form 5 bonds. But here in the transition state, for a fraction of time, it will form transition state where carbon will have 5 bonds. Understand it? Here carbon cannot form 5 bonds, but for a very minute second, fraction of, not even second, fraction of second, the transition state will be existing where carbon will have 5 bonds. So here there will be a transition state which I have to show by a third bracket. Why? Because this is highly unstable due to very high energy. Alright, so what happens over here is this way. This side, I am showing by dot 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 because the bond is breaking. This bond is breaking and this bond is forming. Here it was OH, so let me put OH on it. Understood? So this is the condition. Now this is our transition state which is highly unstable. Transition state. This is highly unstable. So what happens here is this state immediately breaks. The bond completely breaks and ultimately this product is yielded. That we have already seen the product. COH plus X minus. Now the point is OH minus is backstabbing. This is the special feature of SN2. Here backstabbing occurs. Always backstabbing. Reason is also simple. See, X the halogen atom that is there now, how many lone pairs? 6 lone pair electrons, 3 lone pairs. Repulsion, what will happen to the repulsion? It will be existing. So if OH minus is trying to attack the carbon from the front side, X minus will say, I will kick you out. Why? Because it has 6 lone pair electrons. So OH minus says, okay, I will not attack from your side, I will attack from behind. You cannot do anything over there. Right? So OH minus comes from behind, where there is no repulsion. Did you understand? Did you understand? Now you have a question out there. What is that question? That if there are methyl groups attached there to the carbon, if there are 3 methyl groups, then it will cause huge repulsion. Correct. It will cause huge repulsion, and that is the reason that if there is a 3-degree alkyl halide, it will not show SN2, it will show SN1. See, every logic has an answer. You are saying that if there is CH3 groups or whatever alkyl groups, if it is attached to the carbon, then how can OH minus attack from behind? Correct. Point is correct. Because there will be also repulsion. That is also high repulsion. Then what? It will not undergo this only. It will form a carbocation because that is more stable. So it will go by SN1, not by SN2. Understand it, huh? Understand it. OH minus is backstabbing carbon. It is backstabbing carbon, and it can easily do that when the carbon has hydrogens, 3 hydrogen, because hydrogen will not repulse, right? But the moment I am giving some other alkyl group in presence of hydrogen, I have given 3 alkyl groups, then what will happen? Tremendous repulsion over there. So OH minus cannot backstab. So in that case, SN2 mechanism will not be favored. SN1 will take over. Clear? Alright, something is going inside your brain, I think so. So when there is a 3-degree alkyl halide, then there is no SN2, it's an SN1 reaction. So the first point that you need to remember is, so let me write it a white color only so that you can find it out. The point to be noted is SN2 order is 1 degree favored, 2 degree, then 3 degree. Very, very important. Very, very important, huh? If you are doing SN2, then 1 degree will be the easiest one to do SN2. 2 degree will still do SN2, might do SN1 in some case, but 3 degree will never do SN2. It will always do SN1. Clear? Now chemistry is full of exceptions. Don't blame me if you will get 1 or 2 exceptions. There will be exceptions, right? So 3 degree generally or mostly undergoes SN1 because of the repulsion of the alkyl groups. So did you understand that SN2 order is 1 degree, 2 degree, 3 degree for why? What is the reason for that? The reason for that is very simple, to minimize the repulsion. Because it is backstabbing, it needs less repulsion. If there is more repulsion, it cannot backstab. So in that case, there will be no SN2 mechanism followed. Okay, so the first point you need to remember, SN2 order 1 degree, 2 degree, 3 degree. How many of you have understood this? How many of you have understood this? Right, good. Next, as you have seen that I have done something mysterious here. This one and this one. Suppose I have copied one image of this and I am trying to mirror flip it. Let me try if I can do it. I don't know. See, I have mirror flipped it. Flipped it. Now let me erase this one. So this is a mirror flipped. Ignore this one. This one is extra danda. So I have mirror flipped it. The carbon, this is due to the writing C. If there is original carbon atom, that will not be ulto C because it's same. Anyway, so you can see that if I have flipped this atom, this compound, then I am getting something of this sort where the OH is being attacked. The OH has attached to this position. That means if I am flipping this compound, then I am getting this compound. If I am flipping this compound, you can see I am flipped it. Now I am getting this compound. So what did you see? There is a inversion, because this is a mirror flipping. Mirror flipping means inversion. You stand in front of the mirror. What happens? Your left becomes right. Does it actually happen? No. You are seeing it because of inversion. What inversion? Lateral inversion. Due to lateral inversion, you are seeing your right to be your left and your left to be your right, but actually that's not happening. Actually, it's not that. Due to inversion, you are seeing that, right? So, moment you stand in front of the mirror, you are seeing ulta due to inversion. So, this inversion is also applicable for chemistry. Its inversion is not only for physics, it's for chemistry as well. Inversion of compound. So, here also you can see that there is an inversion that has happened. You can see there is an inversion that has happened. So, this inversion has been given a specific name, obviously based on the scientist's name, that is called Walden inversion. So, the most important point for SN2 reaction is Walden inversion seen. Walden inversion seen. Walden inversion seen. Very, very important. Please star mark it. Whatever marking you want to do, mark it. But very important is that for SN2, you will be able to see Walden inversion. That means inversion will happen. Inversion, I have explained you what is inversion. You stand in front of the mirror, your right becomes left, left becomes right. This is inversion. We have given a specific name to the type of inversion seen in chemistry, that is called Walden inversion. Alright, clear? Now still now, if you have noticed, I have not expanded SN2. What exactly is SN2? I have not yet expanded, because I have not told you one thing. When you will be doing chemical kinetics, there also I will say the same thing. The slowest step is the rate determining step. What is now rate? Rate is what? What is rate? What is rate of change of velocity? Acceleration is the rate of change of velocity. So rate of changing something, rate of formation of product, rate of disappearance of reactant, this is rate. So did you understand? Now we cannot define rate like that. No, we can say that at what rate is the product being formed, at what rate is the reactant being decreased. So that is rate. Based on that, we have formulated a rate law. We have formulated a rate law. This is in chemical kinetics it will come. That is called rate law. According to, I'm not writing the rate law because that's a part of chemical kinetics, not organic. But I'm just saying because you need to know the concept. Rate law. Rate law states that rate is proportional to the active mass, product of the active mass of the reactant raised to some power which may be or may not be equal to their stoichiometric coefficient. What did I say so much? Listen to the word, you can understand. Rate of a reaction is proportional to the product of active mass of the reactants with powers means exponential powers, which may or may not be equal to their stoichiometric coefficient. That means if I am writing a reaction A plus B, and I am saying it is a C plus D, then according to rate law, rate will be proportional to the product of active mass of reactant and product. Active mass of reactant. So reactant's active mass, you write it in third brackets. You have already done in chemical equilibrium like this. Now I have told you that the power to which it will be raised may or may not be equal to the stoichiometric coefficient. So here it will be x, here it will be y. When it will be equal? It will be equal when it is an elementary reaction. This reaction that I have shown you is an elementary reaction. That means it occurs in one step. Elementary reaction. See, I am teaching chemical kinetics, also part of it here only because I need to clear your concepts. Elementary reaction. What is an elementary reaction? Reaction occurring in one step. So single step reaction. This reaction is also a single step reaction. This reaction is also single step reaction. Transition state ignored. Then what? Single step reaction only. Transition state you are not going to consider also. But that you have to consider for the organic. I am not talking about rate law. Rate law I will not consider this, but definitely I am going to consider for the organic. Anyway, so that is a single step reaction. This is not a multi-step reaction, a single step reaction. Right? Now what is a multi-step? That also I will be explaining. So elementary reaction, reaction occurring in one step. Now for elementary reaction, X will be equal to A and Y will be equal to B. This is the point. So if it is an elementary reaction, see, I cannot write so many things. So I am saying a lot of things that you should note down. Okay, I am not writing everything. Whatever I can, I am writing. So for elementary reaction, the powers to which the active masses of the reactants are raised will be equal to the stoichiometric coefficients only for the case of elementary reaction. So here you can see that the reactions are occurring in single step. So can I write over here one more point? Can I write it occurs in a single step? It occurs in a single step, or it is a single step reaction, right? Now why am I explaining so many things? Because there are reactions where the reaction does not occur in one step. Suppose I have to convert from A to C. First reaction is A plus B. Suppose I have to go from A to D. I am doing A plus B forms C. Second reaction is B plus C forms D. So is the reaction happening in one step? No. The reaction is happening in two steps. So this type of reaction is called multi-step reaction. This is not an elementary reaction. This reaction is called a complex reaction. Reactions occurring in more than one step is called complex reaction. Reaction occurring in more than one step. In more than one step. Alright, now here what to write? What to write? Understand it. What to write? One time B is a reactant, another reaction C is also a reactant. Then what we will write in the reactant and what we will write in the rate law, that is a question for us. And this we will discuss in the chemical kinetics. I will not go into that. But I am just telling you the facts. For a complex reaction, the value of X and Y will not be equal to A and whatever is the stoichiometric coefficient over here. Clear? So if it is a complex reaction, it won't be equal. If it is not a complex reaction, it's an elementary reaction, it will be equal. Understood? So now let us come back to here. Before that, one more thing I will add on. Rate of a reaction. That I said at the beginning only. Rate of a reaction is determined by the slowest step. Determined by the slowest step. This line is very, very important. Slowest step. So rate determining step is the slowest step. RDS is rate determining step, slowest step. So now if I am going to tell you over here, how will you know which one is the slowest step? For that I need to tell you. Yes, it will be mentioned in the question which one is slow and which one is fast. Suppose I mentioned this as fast and I mentioned this as slow. Then what? Which reaction will you consider to find out the rate of the reaction? Slowest step. That is B plus C forms D. That I will tell you that this is the slowest step. After that you have to write the rate law. These questions are going to come in chemical kinetics, where they will be giving you a reaction like this and they will be asking to find the rate law for complex reactions. One step will be slow, from there you have to get the value. Right, now you see there is an extra component C which is not supposed to be there in the original question. So that you have to remove. That you can do when I am teaching you chemical kinetics. I will talk about that. I am not telling all that right now. Alright, so did you understand? Did you understand that the rate of the reaction is determined by the slowest step? So have I mentioned the slowest step Over here, no. So which one is the slowest step? Hey Baba, it is only a elementary reaction. Then whichever is the slowest step, only one step is only there. Then what? That is only the RDS, that is only the slowest step. So this one is only the slow. This one is only slow and this one is only the RDS. So slow, RDS. Now the question comes in. In the RDS, let me again come back over here. See here in the RDS, in the rate determining step, I have two reactants. That is why I have written rate proportional to product of the reactants raised to the power of their stoichiometric coefficients for an elementary reaction, right? So if there are two reactants, so I will written 2 over there. If there are 3 reactants, then I will let all the 3 over there, products of all the 3 for active mass. If there are 4, then 5, whatever is there. So here, how many reactants you can see present in the RDS? How many? Transfer is not a reactant, huh? That is a product. That is not even a product, that is intermediate, whatever. One, alkyl halide. Second, nucleophile molecule, right? This is the first, this is the second. So how many reactants are you finding? You are finding 2 reactants in the RDS. So you are finding 2 reactants in the RDS. So if I am giving you to write the rate expression for this reaction, then I have to write rate proportional to Rx, where Rx is the alkyl halide, and the nucleophiles concentration. Here I have used OH minus, so I am writing OH minus. Whatever nucleophile will be there, that will be given. You have to write that. Okay, so you can see that there is no coefficient over here, so that is 1. So I have written Rx OH minus. Any doubt? See, I am going too slow. I know that I am going too slow. I should not have gone too slow, but I have to make you understand, so I am going slow. Did you understand this? You see, when the reaction goes slow. Anyway, that's a point also. Alright, so this much is clear. Right, next. Let me tell you some more things about chemical kinetics. You can see it's a linked parts, chemical kinetics. Acha. Suppose I have rate proportional to A to the power A, where the reaction is same. The reaction is A plus B forms C plus D. This reaction I am considering. This reaction I am considering. If the rate is proportional to A to the power 0, B to the power 0, then I will be calling it as a 0 order reaction. I will be calling it as a 0 order reaction. How 0 order is coming, that also I am explaining you a little bit. Rate proportional to A to the power x, b to the power y. If this is a general rate equation, then x plus y is called the order of this equation, order of the reaction. Okay, x plus y is the order of the reaction. Whatever value x and y will be having, that is going to be the order of the reaction. So here x and y both are 0, so 0 order reaction. Okay, if I am writing rate proportional to A to the power 1, B to the power 1, this one I need not write, so I can write just A, B. So if I am writing rate proportional to A, B, then this is a first order reaction. This is a first order reaction. Is it actually a first order reaction? Is it a first order reaction? No. This is also one of the common mistakes that is being made. This is a common mistake that is being made. You find the powers are 1, so it's a first order. No. What did I say? X plus y is the order. So 1 plus 1, 2 is the order, not 1. Okay. So if I am writing rate proportional to A only, then it is a first order reaction. Rate proportional to A only is a first order reaction. Rate proportional to A only is a first order reaction. This reaction is for this case, for this case, for this case the reaction is a little bit different. For this case the reaction is like this. Let us take it like this. because two reactants, no, it cannot depend on another one. Anyway, it might not depend also, no problem with that. Okay, so let's keep it one only, otherwise we will be getting confused. No need, no need, no need. Let's keep it one only. No need to confuse. So if rate is proportional to only a, or it can be like a to the power 1, b to the power 0, then it is called first order reaction, right? This rate proportional to both a and b will be called as second order reaction. Will be called as second order reaction. Did you understand? It will be called the second order reaction because it is this. So what type of order reaction is the SN2? It is a second order reaction. Write down. Second order kinetics. Follows second order kinetics. Follows second order kinetics. What kinetics? Lot of kinetics are there. We want to study formulas and all that it will follow. Alright. These are the few points which you need to remember from this part. Okay. S. The word S stands for substitution. Substitution. N stands for nucleophilic. N stands for nucleophilic. 2 stands for bimolecular. 2 stands for bimolecular. So what is the entire name? The entire name is substitution nucleophilic bimolecular. Why bimolecular? Because RDS has 2 molecules. Clear? Understood? Alright. Now, can you tell me what is the charge on the transition state? What is the charge on the transition state? Because questions that are asked in JEE and NEET are which is more reactive towards SN2? Which is more reactive towards SN1? This type of questions. So for that you need to know the intermediate stability. That will be the point. The point of difference will be the intermediate stability. So how we are going to know the intermediate stability? First of all, you have to understand that what charge is at the transition state having. Can you guess what charge is the transition state having? Yes, it has to have a negative charge. Why not? This is negatively charged. This is also negatively charged. This is positively charged. Then the net negative charge. So can I say that transition state is net negatively charged? Net negative charge. Net negatively charged. I can say, right. Now, who stabilizes negative charge? Who stabilizes negative charge? Who can stabilize negative charge? Electron donating groups or electron withdrawing groups? Yes, electron withdrawing groups. Because negative charge means electron is already in excess. So you need to remove the electrons. So removal is done by withdrawing group. Donating groups will give more electron that it does not need. It needs to remove the electron. So for the electron donating groups must be present. See, everything is concept. Concept is visualization. That much. You have to visualize and you have to understand. Because I cannot show you like chemistry, right? That is at a very microscopic level, even no one can see it. Right? This is just theory that we are just preparing. Right? Alright. So transition state, which minus is negatively charged. Sorry, del negative charge. X minus is obviously del minus. So carbon has del plus. Negatively overall charged transition state. So you have to stabilize the transition state. Who will be stabilizing the transition state more will be more reactive towards SN1. Sorry, SN2. Right. So for negatively charged stabilization, we need electron withdrawing group presence. Done. So you need to compare based on the presence or absence of electron withdrawing groups. If it is present at all the options of electron withdrawing group, who can withdraw more, that will be the more stable. Understood? So then you have to apply the concept of class 11 GOC, inductive effect, mesomeric effect, resonance effect, that is only mesomeric effect, whatever, hyperconjugation effect, those things you have to apply. Point clear? So can I write down that reactivity determined by transition state determined by transition state stability. Transition state stability. Who will increase transition state stability? Presence of electron withdrawing group. Presence of electron withdrawing groups increases stability. Point clear? Clear? Any doubt till this much part? I might have been talking for like 40 minutes on this SN2. Why? Because this is important. Though you have done this in class 11, but you may not have done this much details. So the most important points that you have to remember is SN2 order, 1 degree, 2 degree, 3 degree, Walden inversion seen, and reactivity. The remaining ones are the secondary options, which you have to remember, but they are not the most important ones. Alright, most important ones are reactivity, order, and Walden inversion, because if you forget that, that will be a problem for you. Okay, clear? Next, few more points that you need to add on. If I talk about the order of living group, then who will be the living group order? Obviously iodine will be maximum. Living group I have already discussed. So if I am talking about nature of living group, then obviously it is going to be I minus the first one to leave, then comes the smaller ones, right? This I have discussed already, so I am not giving you any explanation. I, Br, Cl followed by F. This you already know. Next point is another important point. You know what is that important point? Polar aprotic solvent favor SN2. Why? Aprotic solvent definition, when I have told you, remember that it can solvent cations but not anions. That is the reason. Cations can never act as nucleophiles, but anions are acting as nucleophiles. So if it is not solvating the anions, then it can easily go and attack. That is why SN2 is favored by aprotic solvent, while protic solvent favors SN1. Where I have written, I am showing you. Here you can see solvates only cations, cannot solvate anions. So it cannot solvate anions. So if it is not solvating anions are free to attack. So it can easily act as nucleophile in attack. If it is solvating the anions, it will be difficult for them to attack. Backstabbing not possible. Then in that case, SN1 is preferred over SN2. So this point, you might think that it is not very useful, but it is actually very important point, that polar aprotic solvent favor SN2. It will not be given in the question that this will proceed through SN2 or SN1, but in the option you will get both the options, like SN2 product and SN1 product as well. If you don't know whether the reaction is following SN2 or SN1 reaction, you will end up selecting a wrong option. You might select correct, that is 2K, but that is not supposed to work always, right? So you should know what? You should know my brain? No, you should know concept. Clear? So polar aprotic solvent favors SN2. Alright. So this is all about SN2 substitution nucleophilic bimolecular reaction. Following this, we are going to learn about SN1 substitution nucleophilic unimolecular reaction. Alright. So let me just copy up this slide. I guess I should copy it. Let it be here. I'm erasing all this and I'm going to write fresh. Let's move this box out of here. SN1. Now we are going to discuss SN1. Substitution nucleophilic unimolecular. Alright. Let's understand. Last time I told you that if there are three methyl groups attached to the carbon containing the halogen, that is a 3-degree alkyl halide is there, then the alkyl groups being bulky groups will repulse, right? Repulse is a very bad English. Repel, don't mind my English. My English is very bad, So it will repel. So they are repelling. So OH minus or the nucleophile, whoever is the nucleophile, will not be able to backstab the carbon, right? So SN2 mechanism is not possible. Then if SN2 is not possible, then what will happen? It will undergo SN1 reaction. SN1 reaction will be favored. Okay. So in SN1 reaction, what is happening exactly is we have a carbon, and to that carbon I have attached methyl group. Let us take 3 methyl groups. Okay. Let me show it in like this only. Carbon, methyl group, methyl group, methyl group, and here there is a, let us say, Br. Okay. Achha. OH minus as usual is there. So what will be the product? The product will be this one. Or the product will be this one. So what is this? ये क्या हो गया? एक जगह inversion करेছো, एक जगह inversion करोनी. What is this? One time you did inversion, one time you did not do inversion. Coming. Everything I am coming to. First let's understand the mechanism. Then it will be easier for you to understand. Alright? Achha. First of all, I am showing you the mirror image so that you don't question me up again. See the mirror image carefully. See the mirror is there. You can see mirror. Mirror I have placed this side. First mirror. Now tell me, what did you just observe? I have placed a mirror over here. What happened? This is only this one. This is this one. So what did you get? I have placed a mirror in between, and one time OH got substituted this side, one time that side. So don't you find this is racemization? Don't you find this is racemization? Oh, 11th we have not studied only. What is not this term called racemization? Racemization technique. In optical isomerism, there is a term called enantiomers. You have heard enantiomers? Optical activity is there, right? Due to the presence of a chiral carbon, there is optical activity. Fine. There is a optical activity. But this is not chiral carbon. That is also a point. This is not a chiral carbon. Yet I am showing so as to make you explain. So as to explain you, not to make you explain. So as to explain to you, right? This happens only in case of chiral carbon. This is not a chiral carbon. As you can see, it's not a chiral carbon. This happens in the case of chiral carbon only. But I have to explain, so I am showing this. Okay. Assume that this carbon is a chiral carbon. Assume that this is a chiral carbon. So if this is a chiral carbon, this compound is optically active. So if this compound is optically active and I am creating a mirror image of this, so you can see that this person is the mirror image of this. This person is a mirror image. Right? Mirror image. If I am placing this mirror image on this compound, is it exactly overlapping the compound? Is it exactly overlapping? You will find I cannot see only. Now you see. Is it exactly overlapping the compound? No. This is the mirror image. The mirror image is not overlapping the original compound. And what are these called? These are called enantiomers. Non-superimposable mirror image of each other called enantiomers. Right? Now, the compound that will be rotating the light, plane polarized light, left to the left direction is levorotatory, and if it is going to rotate to the right side, it is dextrorotatory, that you have done in class 11. So accordingly, D and L isomers are done. Again, I have got off topic a little bit, but I have told you about optical activity and why did I draw all this. Okay. Alright. So one point I have told you only. Anyway, let us come to the point mechanism. Here what happens is, first case we find that Me as the OH minus cannot attack here directly. What happens in the first step, the Br leaves. The first step, the Br exits. So ultimately the carbon gets a positive charge, cation formed, and Br minus exits. In the next step, to the carbocation, the OH minus attacks. To the carbocation, the OH minus attacks. And ultimately I will get to form either this side or this side, provided that the carbon is a chiral carbon. Remember, I am repeatedly saying that this carbon is not chiral, but this D and L and all these things will happen only if the carbon is chiral. If the carbon is not chiral, no optical activity. If there is no optical activity, no question of all this. Okay, here I am showing because I have to explain to you. Please do not say that this is an optically active compound because I have told you so. I have never told you that this is an optically active compound. I have told you that if the carbon is chiral, then these things will happen. But here I am unable to show the chiral carbon. Okay, here I have to show using 3-methyl so that I can explain to you. Okay, fine, right. So what did we see? First step, carbocation formation. Second step, OH minus attack. Which one is the slowest step? That I have to say because you don't know that. This one and this one. Two step. So this is a multi-step. So this is a complex reaction. This is a complex reaction. Just now I have told you that if it is a complex reaction, then the rate is not proportional to the rate is not proportional to either of the step. It is proportional to the slowest step. It is proportional to the slowest step. And which is the slowest step? The first step is the RDS. It is the slowest step. So this is going to be my slowest step. How many molecules are involved in the slowest step? Only one. So what is going to be the rate expression? First thing I am mentioning this time is the rate expression. So rate expression will be proportional to OH minus, right? Ete 0 debe. Teacher will cut and give you 0. Easy. OH minus is involved in the first step. Then where did OH minus come from? The rate is proportional to what? Rate is proportional to the concentration of the alkyl halide. Second, it is a two-step reaction. Now, another common mistake I am going to tell. It is a two-step reaction. Fine. Some people are very legend. এক একটা লেজেন্ড কিরকম লিখবে টু স্টেপ রিঅ্যাকশন লিখবে না কি লিখবে টু স্টেপ রিঅ্যাকশনের জায়গায় লিখবে ইট ইজ আ সেকেন্ড অর্ডার রিঅ্যাকশন মানেটা বুঝলো না লিখে দিই ইট ইজ আ সেকেন্ড অর্ডার রিঅ্যাকশন সো ইজ ইট কারেক্ট ইট ইজ আ সেকেন্ড অর্ডার রিঅ্যাকশন কেটে 0 দেবে পারলে -1 দেবে it is a two-step reaction and the second order reaction is very different. It is not at all same. What is Akash or is Patal? Both are same thing. Then what? Two-step reaction is reaction occurring in two steps and second order reaction is something different. Second order reaction is two reactants involved. What do you mean by that? Two-step and two reactants involved, same thing. What nonsense? Clear? So you have to avoid writing this stupid answers. It is a two-step reaction, not second order reaction. Clear? Clear? Doubt? So it follows second order kinetics? No, first order kinetics. It follows first order kinetics. Done? Okay, fine. Now you see three methyl groups. Now if instead of the three methyl groups I am giving three hydrogen, then what? Will the carbocation CH3 plus be stable? 3 degree carbocation is more stable, right? Or maximum stable. 1 degree is very least stable, right? So 1 degree will not undergo SN1, it will undergo SN2. Clear? Understood? So what is the order of this reaction? Order of SN1. Even if you don't know chemistry and you have a brain, then also you can do this question. Order of the reaction, SN1 reaction order is 3 degree, then 2 degree, then 1 degree. Clear? Point clear? The order of SN1 will be 3 degree, 2 degree, 1 degree. Reason? 3 degree carbocation maximum stable. Next. Reactivity. Reactivity proportional to carbocation stability. Reaction proportional to, reactivity, carbocation stability proportional. Right? Now who stabilizes the carbocation? Presence of electron donating or withdrawing? Donating groups. Because carbocation needs electrons. So presence of electron donating groups. See, ultimately you have to compare between carbocations only. And that comparison you have already done in use. So see, so much related to class 11, but you all did not read 11. Whatever. Presence of electron donating groups in compound increases carbocation stability. Clear? So presence of electron donating group increases carbocation stability. Did you understand? The activity understood. Carbocation stability, because carbocation is the intermediate bond. Next, leaving group, it remains same. Leaving group will not change. I am just directly writing it. F minus. Last point, just like last case, is very important. Polar protic solvent favors SN1 reaction. Polar protic solvent favors SN1 reaction. Very, very important. Last time it was aprotic, this time it is protic. One common question that is often asked is, I'm just giving you the question like this. Okay, one time they will ask you water, second time they will give you water heat. Students think both the things will give the same product, but actually both the things don't give the same product. This thing will give you what? Tell me. Me, OH. Done. But this thing will give me what? This thing will give me this. This is the problem which you don't understand. Moment I have given H2 heat, temperature increased, high temperature favors E1. High temperature favors E1. Elimination reaction, not substitution. So you can see the difference. H2 to both the case H2 ache, but when it is only H2, it is substitution. That also says in 1. And if it is H2 heat, that is elimination. That also elimination unimolecular E1. Clear? So small things make a difference. Alright? So don't take heat lightly. Did you understand this one? Polar protic solvent will favor SN1 because polar protic solvent can solvent both cations and anions. Clear? Here cation is also there, anion is also there. So it is to solvent Br minus. OH minus is a better nucleophile. If the solvent is not solvating Br minus, then Br minus will only attack next step. And what was the use? right? Which minus the better nucleophile than pair minus, because pair minus is solvated by the compound. So for that, polar protic solvent need to be there. Clear? So this is SN1 reaction mechanism. So did you understand SN1 reaction, SN2 reaction? If you have understood, type in the comment section. Okay, because the next two topics that we are going to study, SN internal and SN2 prime, those will be new, something new which you have not done in class 11. All right. Achha. I have one question. In SN2 we have seen Walden inversion, we have seen Wandel inversion. What we will see for SN1, that you did not say. Now if you have heard me, I have already said it at the beginning only. Beginning of SN1 only I have explained that what is seen here. But I did not write it here. So I should write that, because then you all will blame me that you did not say. So let us write that and end this SN1 part. What do we find here? Racemization. Racemization observed. Racemization observed. Racemization, if you have to study in details, go and watch my GOC lecture. I have explained there enantiomers, diastereomers, racemization, DL, mesocompounds, everything has been done. So kindly refer to the GOC lecture. Racemization observed. I am writing here, watch GOC lecture. Timeline has been given over there, just go and watch it. You will understand. Mesocompound, enantiomer, diastereomer, the optical activity part. Go and just see it. It will not take much time. Just go and check. Nomenclature is a huge one. Just go and check the racemization part. Clear? So in this case, what all you are finding? Racemization. What is racemization? I am getting mixture of two compounds. One is a D, one is a L. Which one is D, which one is L? That I am least bothered with, because I don't want to know also. But they will be getting two mixtures. One is D and one is L. Dextrorotatory, levorotatory. Levorotatory rotates the light towards left side, and dextrorotatory towards the right side. Plain polarized light. Right? Clear? This is all about SN1 element, SN1 reaction. Next we are going to study about the SN prime. First we are going to study SN2 prime, then we will be studying about the SN internal. Okay? Alright. So this part is clear to you. When we are using water, only water, then you will be going by the SN1 mechanism. When we are using water along with heat symbol, we will be following the elimination mechanism. Alright. Now let us understand what exactly is elimination reaction. We have completed SN1, SN2. Now we'll be going on to the second type of nucleophilic substitution reaction, that is nucleophilic substitution reaction, second elimination reaction. So that is write it over here. The second type of reaction that we'll be studying is the elimination reaction. Elimination reaction. Alright. Under elimination reaction also we will be studying three different types. What are those three different types? First one, you can say it as E1 mechanism reaction. Many of you write it as this way. That's also fine. I prefer to write below. Second one, we have E2 mechanism. Third one we will be learning is E1 CB mechanism. Okay, it is elimination conjugate base mechanism. Okay, so we are going to study about three different types: elimination unimolecular, bimolecular, and conjugate base mechanism. So let's begin with the topic elimination reaction. The first type we are going to study is the elimination bimolecular. Elimination bimolecular. So what is the full form of E2? It is elimination bimolecular. Okay. All right. So first you tell me, what do you understand by the term elimination? Elimination means killed. Someone you have killed. But we are not killing anyone here. So what we are doing? We are eliminating that person from a given compound. So we are removing one compound. Compound we are removing? No. we are removing one group, we are removing one atom from a compound. That is called elimination. So what is elimination and what is substitution? The difference between substitution and elimination and addition is very important. Addition means you are adding a group. Substitution means you are replacing one group with the another. That means one group was there, you are taking out that group and you are putting someone else in place of that group as the replacement. In elimination, you will just remove group from a compound, but you will not introduce any new group inside that. Is it clear? Then it is called an elimination reaction. Clear? Substitution, you are introducing new group. Here, no introduction of new groups. That is why in the previous case, the example you have seen, one time OH was a new member introduced, second time no new member was introduced. Only the Br moved out of the compound. That is where double bond was formed. So elimination reaction mostly leads to the formation of alkenes. Mostly leads to the formation of alkenes. So now let us understand what exactly is E2 mechanism. Your brain should be here, your eyes should be on the screen, then only you can understand it properly. Okay, মাথা ঘুরছে অন্যদিকে, চোখ অন্যদিকে, then you will not be able to understand. Okay, chalo, let's start. If we are going to have a compound, let us take, we are having a carbon bonded with a carbon. Here there may be, let us take, there are two hydrogen or whatever there are, I am not showing whatever, but something is there. Okay, and let us take, here is a halogen atom. Let us take, here we have three groups and one hydrogen, it is here. Alright, now you can see that I have intentionally shown one hydrogen up and the X below. I could have shown hydrogen here and X here also, then what would have been a problem? The problem would have been the repulsion. Okay, the problem would have been the repulsion. Remember, whenever we are doing E2 elimination, the H and the X will be eliminated, which will be anti-periplanar. That means different sides of the plane. You know how does a plane look like? Plane is like this. Here 3D is not possible for me to show, but I am trying. Wait, let me try. I don't think I can show it to you over here. Like this, if I am drawing a plane, okay, one will be above, one will be below. Then only I can eliminate. If both are above the plane or both are below the plane, it will be difficult to eliminate. Okay, so one will be above the plane, the other will be below the plane, so I can easily eliminate them. This is called anti-periplanar condition. And remember, E2 elimination always happens under under anti-periplanarity only. That means both on different side of the plane. Remember this, because why? In the JEE questions, they will be intentionally giving you these questions. They will be giving you like this, and let us take one side, they will be giving you Br. Here they will be providing one hydrogen like this, here they will be providing one hydrogen like this, and they will be giving options where one time double bond will be here, one time it will be here. Now you have to know that if there is no anti-periplanarity, then it will not get eliminated. So this hydrogen cannot get eliminated, this will only get eliminated because it is on the other side. Let's say if this is also in dash, then this and this cannot get eliminated, this one will be going. So if you don't know that it is anti-periplanar, then you cannot solve that question. So you have to know that E2 elimination by molecular always happens when the H and the X atom is anti-periplanar to each other. Clear now? Anti-periplanar concept? Alright. So let us write the reaction. Here we use alcoholic KOH. You know that, I hope. Alcoholic KOH. Please be careful. If you write only KOH, that does not stand for any meaning. Why? Because we have just used aqueous KOH in SN1, SN2. So there we are using aqueous KOH. There also if you write only KOH, no meaning. Because what is the KOH? It is in alcoholic medium. It is in aqueous medium. What? You don't know. Then what you have written that? So instead of alcoholic KOH, I can write ethanol KOH. That also proves that it is alcoholic medium. Okay. But you have to write something which will prove that the KOH is in alcoholic medium and not any other medium. Alright. So if it is an alcoholic medium, then what will happen? This X and this H will get eliminated. So ultimately this carbon will have two hands free. This carbon and this carbon will have their one hand free. Sorry, not two hands, one hand free each. So ultimately they will form a bond, that is double bond, right? So we can say that this 2 carbon will be forming a double bond and the HX will go out. Alright, clear? So here what you have to remember is, I am writing over here, H and X are anti-periplanar. Anti-periplanar. This is important. If they cannot be in the same plane, if they are in the same plane, elimination will not happen. Okay, clear to you? Understood? Okay, fine. Okay. If it is a E2 mechanism, then the reaction proceeds to a transition state. Similarly, we have seen for SN2 also. SN2 proceeded through a transition state, right? E2 will also proceed through a transition state. How does the transition state look like? So let us understand that the mechanism as such is not very big. It's easy one. So you can see that we had a H over here, we had an X over here. So what exactly happened was this H went away, the entire electron came to this carbon, this X took the electron, so plus will develop here, minus will develop here. That is the reason for double bond formation. So can I write del plus here and del negative here? Okay. Now when the OH minus has attacked the carbon, this person is del plus, so attacked. So H minus has taken H, formation of H2O. Formation of H2O. Now remember, the H2O is not formed over here, or I have not written it. It is formed, but I have not written. Why? The question is why? Because I have written HX. There is no question of O coming. When will the O come? When this HX will react with KOH. Understanding? So this HX, when it is reacting with KOH, it will form what? KBr plus H2O. Then the water comes in, right? Clear? So where is the water coming from? After this step the water comes. Okay, here I have not mentioned water due to this condition, because after this step acidic oxide plus base, that is acid plus base, will form salt plus water, then the water comes, not in this step. Alright, so H minus takes H plus, so this will become del minus, this will become del plus, bond will be formed. Right, so transition state, how does this look like? Let us see the transition state. The transition state is the carbon-carbon single bond was there and it will persist, but there will be a partial double bond character that will be formed, because double bond is forming. The hydrogen that was bonded is gradually what? It is gradually leaving. So I am showing by a dotted lines. Here we can see that the hydrogen is getting bonded to OH. So I am showing by dotted lines. Alright, this carbon has two more hands, because this hydrogen is leaving. Okay. Similarly for this carbon we are having two more hands. Here the X group is leaving. So this entire thing that I have shown is called the transition state. So this entire thing is called transition state. Transition state. Clear? So this is the transition state. After some time the entire bond will be formed and this will look like this structure. So it will be C double bond C plus water plus X minus. Clear? So from the mechanism you can see that water is coming, but here how it is coming? By reacting with this. Understood? This is that much simple. That much simple. Nothing complicated. But questions will be coming in such a way that they will be trying to trick you, but you cannot get tricked by that. Okay? Did you understand this much? Okay. Now if I have to write the rate law for this particular reaction, then what will I write? I have explained what is rate law in the last topic, that is SN1. SN1 I have explained you rate law. I'm sorry, SN2 only I think I have explained you rate law. Entire history geography of rate law I have told you. So how will you determine the rate law? The rate law will determine in the slowest step. Here though it is one step, it is single step reaction, just like SN2, this is also single step reaction. So here only one step, and that is the RDS. This is only the rate determining step. So rate determining step has how many molecules? OH minus also, and this entire thing also. So this is a what order reaction? Second order reaction. Right? I have told you that rate, if it is proportional to A and B, then it is called second order reaction. Right? So this reaction will be following second order kinetics. Then that history of this kinetics and all you will be reading in the chapter chemical kinetics. But much introduction of this has been given in this chapter only by me. Alright, so here if I am going to write the rate law, then rate will be proportional to the Rx that we are having as well as the base that we will be using. Alright, here the base is OH minus. Clear? Okay, fine. Remember, many a times it will be told dehydrohalogenation, which you have done in class 10. In class 10 you have done dehydrohalogenation. So this is the dehydrohalogenation which you have learnt in class 10. Okay, so E1 is not called dehydrohalogenation. It is also elimination only. But the term dehydrohalogenation is for the reaction proceeding through E2 mechanism and not for E1 mechanism. Okay, fine. So this reactions, so write down, these reactions are called, beta elimination, beta elimination, beta elimination or dehydrohalogenation, because water and halogen both are moving out. Dehydrohalogenation reaction. Okay, see, I am telling very slow, I can go fast, but that might land up 1000 feet above your head. Anyway, so this is called dehydrohalogenation reaction. Color was not changed, sorry. Or beta elimination reaction. So remember these two terms because it might be used alternatively in the questions. Okay. Alpha carbon, the carbon to which the halogen is directly bonded is the alpha carbon. This I think I am telling for the second time or third time, and this is the beta carbon. Okay, from beta position hydrogen going on and from alpha halogen, so it is called beta elimination reaction. Okay, fine, because beta is involved. Okay, so these reactions are beta elimination reaction or dehydrohalogenation reaction. Now you can see this is resulting in the formation of alkene. So which alkene will be formed, that I cannot say. But I have to predict which alkene may form, otherwise how can I write the reactions? So for that we will be checking the stability of the alkene. So we will be taking the stability of the alkene. So what will be the answer? Major product equals to most stable alkene. So what did I write? I did not write Sedgwick product. I did not write Hoffman product because that is nothing but to confuse you. You have to remember that the most stable alkene will be the major product. That's it. You need not remember Sedgwick product, Hoffman product, this product, that product, not required. Remember that the major product will be the most stable alkene. That can be Hoffman, that can be Sedgwick as well, depending on the reagent being used. Just I will show you the variations right now. I will tell you about the variations, but you have to remember that the major product will be the most stable alkene. Concept clear? Most stable alkene. Now how to check stability of alkene? For that you have done class 11 GOC. There you have learned about an effect called Buchanan effect, also called as hyperconjugation effect. So you have to check for the number of alpha hydrogen. Whichever compound, whichever alkene will have more alpha hydrogen, it is more stable, that will be the major product. It is clear to you that how to detect a major product? By hyperconjugation. Okay, so most stable alkene I am just mentioning over here by hyperconjugation. Why is not looking like Y? By hyperconjugation. Clear? So major product will be the most stable alkene, whether it be Sedgwick product or it can be the Hoffman product. You need not keep it in your mind. Okay, mostly or usually if the reagent is alcoholic KOH, alcoholic NOH, this type of reagents are there, then you will get the Sedgwick product only. Remember, some places you will find Sedgwick written as this spelling, Okay, somewhere you will find it is written as this spelling. So don't need to get tense. Who is Zaitsev now? Zaitsev and Zaitsev both are same. Zaitsev and Zaitsev both are same. Okay, so sometimes you will find me saying Zaitsev, sometimes Zaitsev, same. Okay, so mostly it is Zaitsev product. Sometimes when the base is a bulky base, then you will be finding it to be the Hoffman product. Hoffman is a person who has a lot of contribution to organic chemistry, so don't think that he just did the wrong thing. No, he has a lot of contribution. In the next chapter that will be dealing with amines, they will be finding Hoffman bromide degradation, ammonolysis, many things he has done. So Hoffman product is basically for when you are giving a bulky base. What do you mean by bulky base? Explaining everything. So major product stable alkene. Here I am mentioning if base is bulky, Hoffman product form. But I will not write. Why? Because I don't want to keep you in any confusion. You will be seeing the less stable alkene, which is going to be the Hoffman product. Okay, that's going to be the Hoffman product. So remember, when the base is bulky at that time only, otherwise no. Mostly we will find the base bulky base tertiary butoxide. This will be the most times given base, bulky base. This what it does I am showing you. So in that case we will be writing the Hoffman product. Clear? Alright, so let's understand by a quick example. Alright, fine. Suppose you have CH3, CH2, Cl. Okay, that's a very simple one I am showing you at first. I am using on it alcoholic KOH. So what I will be getting? I will be getting CH2 double bonded with CH2. Not a very big deal, and that's an easy one. Byproduct is there, so I am giving dot dot dot. The byproducts you are supposed to mention. Okay, this one you know. Okay, fine. Suppose I am increasing it to CH3, CH, CH2Cl. Then what? 1, 2, 3. 1, 2. CH3, CH2, CH2Cl. And if I am using alcoholic KOH, then what? Now the question starts. Cl will be taking hydrogen only from the second carbon. That means I am talking about this carbon. It cannot take hydrogen from this carbon because the bond will not be like this, obviously. Right? So this also will be CH3, CH double bond, CH2. Right? Byproducts, please mention it in your answers. Okay? Achha. Next, CH3, CHCl, CH3 using alcoholic KOH. Achha. Now one thing let me tell you. Instead of alcoholic KOH, in the first one, this is reaction number 1, reaction number 2, reaction number 3, another one I will give. In reaction number 1, if I am using tertiary butoxide, same reaction, I will get the same product. Why? Because here the bulkiness of that will not matter, because this side is only small and there are only 2 carbons available. So the hydrogen will be going for the second carbon only. That tertiary butoxide also, the same answer will come, right? Second one also, if I give tertiary butoxide, then also the same answer will come, because no other place is available for it to take the hydrogen from. Okay. Third one also, if I give tertiary butoxide, same answer I will get. Why? Because here also 2 sides there are methyl, so either side it will take the hydrogen from. Tertiary butoxide will also give the same answer, right? Tertiary butoxide will also give the same answer. But I will show you some case where tertiary butoxide and alcoholic KOH will give the different answers. So all these reactions are valid for both tertiary butoxide as well as for alcoholic KOH. Alright? Okay, fine. So now this time what it will happen? It will take hydrogen either from this side or this side, but 2 sides both are equivalent. So directly now we will get the same alkane. Use your common sense, okay? Very much common sense is needed in chemistry. See here, if I take hydrogen from here also I will get the same product. Here also I will get the same product. Then what is my problem? Take from any side. Clear? Alright, so I am taking from one side CH2, double bonded CH, single bonded CH3. Right? Now let's take number 4. Suppose I am writing CH3, CH2, CH, Cl, CH3. Acha, let us move this to the next page. It's an important reaction, so let me just move it to the next page. I'm writing over here first. All the reactions give same product. With tertiary butoxide. All the reactions give same product with tertiary butoxide. Now I am writing over here one of the star reaction. This is just an example. Don't take it that this is the only reaction. Many are possible. I'm just giving you one example. So this is the reaction. Just remove this. Then should I write it fresh? Let's write it fresh. I have CH3, CH2, CHCl, CH3. Alright. Now I am treating it with alcoholic KOH. Right. Now you see this chlorine has two options. Either take from this person or take from this person. उसके पास दो चांसेस है. बाय वाले से लो, डाई वाले से लो. लेगा किससे ये उसके ऊपर डिपेंड नहीं कर रहा है. लेगा किससे ये उसके ऊपर डिपेंड कर ही नहीं रहा है, क्योंकि इट विल टेक फ्रॉम द thing which will form a more stable alkane. Clear? Now here you have to make cases. Now you see what cases I will make. One time I am taking from this, one time I am taking from this. So let us make one case. CH3 CH double bonded CH3. ये एक केस बन गया. दूसरा केस बना देते चलो CH3 CH2 CH double bonded CH2. So I am getting two alkenes. What is the major product that I have to mention in my answer? So as I have already told that the major product will be the most stable alkene. Major product is going to be the most stable alkene. So which is the most stable alkene out of here? I have told you to compare based on Buchanan effect or hyperconjugation effect. So double bonded two carbons ignored. How many hydrogen here and how many hydrogen here? 6. So 6 alpha hydrogen. Remember alpha hydrogen how to count? डबल बॉन्ड सिस्टम्स डायरेक्टली अटैच्ड कार्बन्स हाइड्रोजन्स. माने जो डबल बॉन्ड सिस्टम है ना, डबल बॉन्ड सिस्टम में दो कार्बन होते हैं, उससे डायरेक्टली अटैच जो कार्बन है उसके पास कितने हाइड्रोजन है, वही अल्फा हाइड्रोजन होते हैं. ठीक है, तो 6 अल्फा हाइड्रोजन. सेकेंड केस डबल बॉन्ड सिस्टम ignored. How many alpha hydrogen? We will count this one. This is also ignored. Only 2 alpha hydrogen. So now you tell me which one is more stable. This one is more stable. So which one is the major product? The first one is the major product. So the major product is CH3CH double bonded CH3, and this is called the side-Jeb product. So you don't have to remember whether it will be forming the side-Jeb product or it will be forming the Hoffman product. The answer will come automatically. You have to just go by the format of most stable alkene. Clear? Now the same reaction if I am giving with tertiary butoxide, then what will happen? Let us check. CHCl CH3 with tertiary butoxide. With what? Tertiary butoxide. How does tertiary butoxide look like? Tertiary butoxide is this structure. So you can see oxygen is there with 3 bodyguards. That also very मोटा bodyguards. बहुत ही बड़ा साइज का 3 बॉडीगार्ड लेके घूम रहा है ऑक्सीजन. और इस साइड में हमारे पास है हमारे OH माइनस भैया, जिसके पास तो है ही नहीं कुछ. तो OH माइनस कौन है? एक छोटा सा साइज का एक बंदा है जो जाके चकचक अटैक कर देता है. ठीक है, पर ये टर्शियरी बुटॉक्साइड वाला बंदा इतना बड़ा है, इसके साथ 3 बड़े बड़े बॉडीगार्ड्स मौजूद है कि ये ज्यादा अंदर घुस नहीं पाता. क्यों घुस नहीं पाता? क्योंकि वहां पे गुंडा बैठा हुआ है. कौन है वो गुंडा? Cl है वो गुंडा. तो ये Cl उसको उधर जाने नहीं देगा, ये Cl उसको उधर जाने नहीं देगा, तो ये उस साइड का हाइड्रोजन ले ही नहीं पाएगा. Did you understand? We have done CH2 वाला हाइड्रोजन, CH2 हाइड्रोजन का तो कैसे, but Cl is in between. So Cl is the gunda. Cl is the gunda. It will not allow tertiary butoxide to enter that side and take that hydrogen away. So what will tertiary butoxide say? तू गुंडा है तो मैं भी बड़ा गुंडा हूं, मैं सामने से हाइड्रोजन लेके भाग जाता हूं. समझ में आ गया सबको? क्लोरीन एक गुंडा है जो टर्शियरी बुटॉक्साइड को अंदर जाने दे नहीं रहा है. सो टर्शियरी बुटॉक्साइड ने क्या बोला? तू गुंडा है तो मैं तेरे से भी बड़ा गुंडा हूं, मैं तो सामने से हाइड्रोजन लेके जाऊंगा तेरा, तू कुछ कर भी नहीं पाएगा. So what does tertiary butoxide do? It does not go inside. It takes the acidic hydrogen from outside only. Sorry, acidic hydrogen is the wrong term. It will take the hydrogen from outside only. That means less sterically hindered hydrogen will be taken by this tertiary butoxide. अच्छे से समझो, बहुत ही important concept. Chlorine is sitting there. Chlorine is repulsing the T tertiary butoxide ion. Tertiary butoxide ion cannot take the hydrogen of CH2 because chlorine is not allowing it because of its huge size. Problem is there with its huge size. So what it will do is it will take the hydrogen which is less sterically hindered. Less sterically hindered hydrogen is this one. No steric hindrance or very minimal steric hindrance. But this one has a steric hindrance this side as well as this side. इसके पास भी 3 मिथाइल ग्रुप से. Clear? So what it will do is it will चुपचाप बाहर हाइड्रोजन बैठ जावे. चुपचाप बाहर हाइड्रोजन बैठ जावे. समझ में आ गया क्या किया इसने? चुपचाप बाहर वाला जो हाइड्रोजन है लेके भागो, बस कोई काम नहीं है इसका. तो बाहर वाला हाइड्रोजन लेके भागोगे तो कौन सा प्रोडक्ट बनेगा? CH3 CH2 CH डबल बॉन्डेड CH2. isn't this called the Hofmann product? इसको हॉफमैन प्रोडक्ट नहीं बोला जाता? अभी तो हमने पढ़ा ही कि ये हॉफमैन प्रोडक्ट बना रहा है. देखो बना दिया हॉफमैन प्रोडक्ट. समझ में आया कि ये क्यों हॉफमैन प्रोडक्ट बना रहा है और पिछले वाला क्यों ZZ प्रोडक्ट बनाया? रीजन इज वेरी सिंपल. टर्शियरी बुटॉक्साइड को अंदर जाने दिया नहीं जा रहा है तो वो बाहर से हाइड्रोजन लेके भाग गया, पर वही मैंने अंदर जाके हाइड्रोजन लेके जा रहा है. समझ में आ गया? यही है डिफरेंस ऑफ द क्वेश्चंस एंड दिस इज हाउ द क्वेश्चंस कम इन जेई. विल बी आस्किंग यू बेस्ड ऑन दिस स्मॉल concepts and there only you people will get problem. Is it clear with tertiary butoxide? तो tertiary butoxide क्या करेगा? बाहर से हाइड्रोजन लेके भागेगा. Cl अल्कोहलिक OH होगा तो अंदर जाकर हाइड्रोजन लेगा, मतलब ZZ प्रोडक्ट बनाएगा. और अगर ये टर्शियरी बुटॉक्साइड है तो वो हॉफमैन प्रोडक्ट बनाएगा, बट नॉट नेसेसरीली दिस कंडीशन विल ऑलवेज बी फॉलोड. दैट इज व्हाई आई हैव टोल्ड ऑलवेज चेक फॉर द मेजर एल्कीन, दैट इज द मोस्ट स्टेबल एल्कीन. Clear? For tertiary butoxide, just remove the outer hydrogen and gone. That is whatever the alkene will form, that will be the major product. No need of checking any stable alkene. Clear or not? Clear or not? This is all about E2 mechanism. Next we are going to study about E1 mechanism reaction. Clear? E1 mechanism reaction. This is just corresponding to SN1 SN2 reactions. Okay. This one was E2 mechanism where the reaction proceeds through transition state. Now what we are going to read is the E1 mechanism, which is analogous to the SN1 mechanism where there was a carbocation formed. Here it is not a nucleophilic substitution, but it is an elimination. So we are saying it as E1. Alright. So let us understand about E1 reaction. Just a minute. Alright. Let us understand about E1. Elimination unimolecular. Elimination unimolecular. Alright. Okay. How will we determine the molecularity of a reaction, whether it is unimolecular, bimolecular or whatever? That is dependent on the RDS, that is the rate determining step. I have already explained to you how will you find out the rate determining step and how will you understand whether this reaction is a unimolecular or a bimolecular reaction. So you can go back in the same lecture, you can go back and you can find it out. I have already told it. Now what happens in E1 elimination is a carbocation intermediate is formed. What is formed? A carbocation intermediate. So if there is a carbocation formed, there will be a possibility of rearrangement. So whenever you are doing, please check if there is rearrangement possible or not. Okay. So the first point under E1 reaction, elimination reaction, we will write carbocation intermediate form. Carbocation intermediate formed. So if carbocation intermediate is formed, there will be a possibility of rearrangement, that you have to remember. Alright. Now the major confusion that will be coming up is what to do and when to do, whether the reaction is showing E1 or SN1, because the reagents will be mostly similar. I am giving you an example, but first let us understand E1 mechanism. Alright, okay. Suppose I have methyl, 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 and a halogen atom X. And what I am doing is I am heating it with water. So what is going to happen is I will get an alkene. Let me make the alkene this side. Me CH2 Me. Alright, and what went out was HX. This is the basic funda of E1. Same thing happening, but the way of proceeding is different. So let us understand how this reaction proceeds. As it is a unimolecular reaction, so definitely the nucleophilic attack is not going to be in the first step. Since it is a unimolecular reaction, the elimination is not going to be in the first step. Alright. So in step number 1, what happens is Me, C, Me, Me, X is there, the X leaves. So if the X leaves, then I can say that a carbocation has formed like this. X leaving means X minus is being there. In the second step, this is the RDS. Okay. Now you can see that RDS involves only one molecule. So this is a unimolecular reaction. Alright, fine. In the second step, you will be seeing Me, positive Me. Now you see who is there? Water is there. So water will be attacking. Water can attack from which center? Water can attack from which center? Water can attack only from the oxygen center. Hydrogen still cannot attack. So it will be attacking where? Attacking on the carbon. If it is attacking, now see, now logic is yours. See, let me go on to the next page. Let me just explain you this thing. See here. It was there Me positive. Okay, and you are attacking it with water, right? Now you don't know what to do. You are making the water attack over here. Okay, fine. What will form? Me, C, Me, OH2 positive, right? Now you know that OH2 positive, so O এর মাথায় positive means O has gone completely mad. O cannot have positive. So what it will do, it will drop one hydrogen. So what it will form? It will form Me, C, Me, Me, OH. Did I require an alcohol? Did I need an alcohol? No, I did not need an alcohol. I did not need an alcohol. What did I need? I needed a alkene, but I got an alcohol. So that is not my required product. So the attack that I did was wrong attack. That means the H2O will not attack this carbon. No, that's wrong. That is why we are getting an alcohol instead of an alkene. That was a mistake. So now how to treat the mistake? Because this mistake you will make in the exam as well. Relax and first see what is the reagent given. You can see the reagent given was H2O heat. Remember, if only H2O is given, it is SN1. Depending on whatever the compound is. If H2O as well as heat is given, that will not show substitution, that will show elimination. Because high temperature favors elimination reaction. Okay. Alright, so this attack is wrong. So how it will attack, let me just tell you now. Let me okay, not I will delete it later on. See, I have Me, C, Me positive. Can I write one of the methyl? Can I write like this? See to CH2H. Digitally CHC. So now see H2O. Now the O will attack over this hydrogen. So can you see that it will be like this, CH2 minus Me, C positive, and along with this it will be uh, Okay, HCl. Where HCl came? H came from there and Cl was in previous step. So HCl. Alright. HX rather, let me write. X I wrote the last one. X, right, HX. Right. Now you can see that two positives, sorry, I mean two charges are together. There is also unlike charge. Minus plus, can it stay together? Can it stay together? No, it will not stay together. So what it will form? It will form a double bond. So that's how the alkene comes. So you can see how there is a difference between SN1 and E1. SN1, the attack would have taken place directly on the carbon carbocation, but here it is not taking attack on the carbocation. It is taking a hydrogen. Now this is elimination, not substitution reaction. This is very very important, that where exactly the attack is happening. Alright, so I will not delete this slide because this slide is important. So this will form what? This will form MEC double bond CH2 single bond Me plus it will form HX. Understood? Mechanism is written over here. You can just check. This slide I am deleting because this is substitution. So I am deleting this slide. This slide is a mechanism. Okay. So did you understand? E1 elimination unimolecular reaction. What exactly is happening? This is happening. It's a very simple thing. But the problem is you attack at the wrong place, you get a wrong answer. So please remember that H2O heat, whenever it is given, it is a E1 mechanism, not SN1 mechanism. Okay, fine. Now let me give you some important points. Not many, but I will 2 or 3 I will give you. So let's make a box out here. Okay, important point number 1. Write down high temperature and strong base favors elimination reaction. So if there is a high temperature given, that is why H2 temperature it is given, it is showing elimination and not substitution. Okay, so high temperature and strong base favors elimination reaction. Second, weak base, if it is given, if the base is weak, you have seen tertiary butoxide base, weak base, so it is doing the E2 mechanism, so it will do E2 mechanism, and analogous to E2 mechanism is SN2 mechanism. Alright, okay, but it is not. Weak base tertiary butoxide was doing SN2 mechanism only, then why it is SN1? If it is a weak base, it will undergo E1 mechanism, not E2 mechanism. Okay, E2 mechanism generally done by strong base. Clear? Alright, so if it is a weak base, common mistake is E1. Common mistake is E2, but that is not the actual answer. Okay, so if it is a weak base, it will undergo E2 mechanism, or it will undergo SN1 mechanism. Right? I said E2, mistake, E1. It will undergo E1 mechanism, or it will undergo SN1 mechanism. Okay, third, if it is a strong base, then it will undergo E2 mechanism, or it will undergo its analogous SN2 mechanism. Clear? So if it is a weak base, E1, strong base, E2, SN1, SN2, analogous. Clear? Alright, please remember this. You might need it sometime in your future for solving the questions. Alright, let me just decrease the size of this thing. Next is a special type of elimination reaction. We have seen elimination unimolecular, we have seen elimination bimolecular. Now we will see a special type of elimination reaction which is called elimination via conjugate base mechanism, E1CB. Now what we are studying is E1CB. Full form is elimination unimolecular via conjugate base mechanism. Alright. So E1CB is a special type of elimination reaction unimolecular where the alpha carbon is sterically hindered. Either it is sterically hindered or the leaving group is not good. Mostly it is applied when leaving group is bad, like in case of fluorohalides. Okay. So let us understand with an example. Suppose we have CH3, CHF, CH3. Alright. Now suppose you have given alcoholic KOH. But fluorine is not at all a good leaving group, right? Fluorine does not like to leave easily. So how will you make fluorine leave? Fluorine cannot leave. Electronegative difference is very high, bond is very strong, cannot be broken easily. So in this case, what happens is this hydrogen is taken away. Okay, either this one or this one, because both are beta positions. So either of this side you can do. But when there is unsymmetrical condition, that time you have to be very careful that which one is the beta position. Okay, here both are same, so it will be any of the sides you can take. So what the alcoholic QH will do is সাইডের একটা হাইড্রোজেন নিয়ে বেরিয়ে যাবে, দ্যাট মিনস CH3 থেকে একটা হাইড্রোজেন চলে যাবে, তাহলে CH2 will be formed, minus will be there, that minus will come down and it will throw fluorine out. Did you understand? I am writing, you understand. Product I am writing first. Product will be CH3 CH double bond CH2. Alright, and fluorine will go out as H. Now you did not understand what happened, so let me explain. CH3 CH CH3 F was there. This position is called alpha position where the substituent is attached, that is alpha position. Next to the alpha position is beta. So this side is also beta, this one is also beta, because both sides you can move, but we will not consider both the betas. Either of the betas I am considering, so I am removing one beta. Alright, now this one is the basic idea of alpha and beta position. So this idea you have to have. Let me just make it smaller. Now you see I have the compound like this, CH3 CHF CH3. Now can I write CH3 as CH2H just like I wrote previously? Now in this can I write OH minus, because actually alcoholic OH is giving OH minus only. K plus has got no big role other than reacting with this further to give you KF plus H2O. This is the role of this, right? So that is all, right? Just remember that. So OH minus will attack this hydrogen. So what will be formed? CH3 CHF CH2 minus plus water. Now this minus comes out here and fluorine is thrown out. So you get CH3 CH double one CH2 plus F minus. Did you understand how it is forming? This is the way the reaction happens. So please keep a special look on this. This is an important part. E1CB elimination unimolecular via conjugate base mechanism. Okay, so what is the funda here? Funda is the leaving group is not good. F is not a good leaving group. So if F cannot leave properly, then this type of Taravaka path it has to take. So as to throw throw F out of the compound. Clear? I have no doubt with this. Very good, very good. Next topic. Alright, now we are going to read reaction with metals. We were reading basically the chemical properties of haloalkanes. So if you remember that we have discussed two times chemical properties, nucleophilic substitution and elimination reaction we have discussed. So what we are going to do now is we are going to discuss the third part that is reaction with metals. This is going to be our third part of chemical properties. Alright, so now we are going to discuss reaction with metals. So let us go and let us discuss that. So heading will be reaction with metals. Reaction with metals. Alright, okay. First reaction we are going to study is organometallic compound. Formation of organometallic compound. Organometallic compound. Now what exactly is an organometallic compound? First you need to know that. So what do you mean by organometallic compound? Just a minute. What exactly do you mean by organometallic compound? Understand, organometallic compound is a compound which is having at least one metal carbon bond. What did I say? Organometallic compound is that compound which has at least one metal carbon bond. Okay, it is organometallic compound. Alright, okay, so I'm writing over here at least one metal carbon bond present. Alright, so if at least one metal carbon bond is present, then we will say it as an organometallic compound. Alright, acha. Now let me tell you one thing about Grignard reagent, though I am not supposed to tell it right now, but let me tell you, just we are discussing, we can just tell it. Just remember RMGX, you know what it does? It will take acidic hydrogen from even the weakest of base. Weakest base thekeo H plus it will take. It will take the acidic hydrogen even from the weakest base. So what actually does this Grignard reagent do is it takes the acidic hydrogen. Alright, acidic hydrogen will take. Remember all this because in certain questions this concept can be used. RMGX plus water. Is water a good base? Water is a weak base. Water is a weak base. Even from water it takes up acidic hydrogen. So what it forms? It forms RH and Mg. It had one side OH, it will attach one side X. So do you understand that this will take up H even from the weakest base? Clear? This is basically additional information I gave, not required actually. So is organometallic compound understood? Grignard reagent. Alright. Next let us move on to the second one. Second one is an easy one. Reduction of haloalkanes. Reduction of haloalkanes. Now what will happen if I reduce the haloalkanes? What I mean is if I am reducing the haloalkanes, then I will end up getting alkane. But this method is not actually very legit. Why? Because yield is very poor. Okay. Achha. Now, which type of reducing agent we can use? Any reducing agent which you know. So what are the common reducing agent which you will use? Achha. What is H? H means reducing agent. H means reducing agent. Which reducing agent we can use? Any metal with acid, zinc HCl, tin HCl, Zn with acid, Zn with NaOH. All this you know, Zn plus NaOH gives you what? Sodium, zinc, and hydrogen. I require hydrogen, the hydrogen is being produced. So anything that can produce hydrogen I can use. Amalgam. I can use amalgam. What amalgam? Sodium amalgam. And of course, we have our favorite guy, lithium aluminum hydride, or we can also use sodium borohydride. But generally, we don't use this. So these are some of the common ones. What will be most commonly you can see in your question paper? You can see most commonly SnHCl in your question paper, LiAlH4 in your question paper. These are the two most commonly used reducing agents for this reaction, but others also can be used. Did you understand reduction of haloalkanes? Clear? So basically Rx is getting reduced to Rh in presence of hydrogen obviously, and HX will be a byproduct. HX. These are the reducing agents which you can use. Either of the reducing agents you will use. Most commonly reducing agents have been highlighted. Alright? Alright. Next, let us move on to a very important reaction that is called Wood's reaction. Wood's reaction. Star market, whatever market, very important, very important. Wood's reaction. This reaction you have done in class 10, you have done in class 11, again you are doing in class 12. So I think by now you would have learnt up the reaction completely, right? So what is the reaction all about? Acha, here this reactions I have given you the general syntaxes. I hope that instead of R you can put one alkyl group and you can make up one example. I have not showed example for this because I think you can do it. Similarly here also it's nothing, just you have to put one each. CH3, okay. So let me show one example over here. Grignard I am not showing, that will be your homework to do one example, okay. Suppose I put CH3Cl and I am reducing it. So what I will get is CH4 and I will get HCl. Alright, so this simple reaction, nothing to worry about. Next, Wood's reaction. Wood's reaction, what happens? I take up a RX bond 2 times and I make it to react with 2Na in presence of dry ether. Then what I get? I get R plus 2NaX. This is my Wood's reaction. Let us take up one example quickly over here only. 2CH3Cl plus 2Na in presence of dry ether gives you CH3 plus 2NaCl. Did you understand that if you have to step up the number of carbons, you can use Wood's reaction? Previously, the reaction of haloalkane, we saw that there was no increase in the number of carbons, but here we can see there is one increase in the number of carbon. Clear? Wood's reaction understood? It's an easy one. Achha. One point I will mention. Suitable method for preparation of even number of carbon containing compound. What does this mean? This means that the compound you are preparing will be a carbon compound, will be a carbon containing compound where the number of carbons will be even. This method is suitable. Now it can be that number of carbons are not even, but that is not a suitable method for this. Why? Because a mixture of alkenes will be produced, so you have to separate it as well. So more cost, production cost is more, so obviously it is not a suitable method. So it is a very suitable method for even number of carbon containing compound. For odd number of carbon containing compound, mixture of alkanes are produced which needs to be separated. Okay, so write down, for odd number of carbon containing compound, mixture of alkanes produced, which need to be, okay, so this you need to remember that there needs to be a separation process done. That is why we don't go for it. All right, now let us know about the mechanism. Mechanism is actually two types of uh, theories have been proposed about the mechanism. One is ionic mechanism and one is the free radical mechanism. Okay, so first let us talk about the free radical mechanism. Free radical mechanism. See here, we had Na. Na will get converted to Na plus an electron. Done. We had CH3 or not, let's not take CH3 out here. Alright, del plus, del minus. Understand? Na got broken into Na plus electrons. Right? Right. X minus will be existing as a free one, so X will move out as minus. So this electron goes to this person and this bond breaks. So what will happen? R will get a free radical, it's a dot, and X will become minus. This will further react with, let me show it by this way. This will further react with Na plus to form what? NaX, that is done. Now this R minus will find another R minus and will get dimerized to form R. Okay, this one is called dimerization. Alright, dimerization means same things just combining together. Dimerization. Alright, next is ionic mechanism. Ionic mechanism. See, mechanism remains same. Just in case of ionic mechanism, there is a ion form. So what will happen? Instead of 1 Na, I will take 2 Na. So there is going to be 2 Na plus form. There are going to be 2 electron. Moment there are 2 electron, there will be a carbocation form. Right? So this is 2 electrons. So this bond will break. 2 electrons will come over here. Alright. Alright. So R minus Br minus. Now in another step we have another Rx molecule. That Rx molecule will be attacked by this R minus. That X will move out and this will attack over here. So dimerization will not happen. Directly RR will form. That X minus will move out. This X minus and this X minus will form NaX. That also two times. Did you understand? This is how the processes are happening. This will react with 1 NaX, 1 Na plus. This will also react with 1 Na plus. Ultimately, it will form 2 NaX. Clear? So, what differences you have understood from both free radical and ionic mechanism? One time you have seen one electron happening, that is why there is a free radical. Another time two electrons happening, that is why there is a anion form, carbon anion, carbocation. But carbocation directly not visible over here because of SN2 mechanism. Alright, clear? Clear with this? Alright. Now, note down a very important point. This reaction 2Rx plus 2Na dry ether RR plus 2NaX. This reaction is valid for 1 degree slash 2 degree alkyl halides only. Very important. This is very important. Very important. Very important. 1 degree, 2 degree only this is happening. Now what will happen for 3 degree? Let's take a separate slide to write that. If you are taking a 3 degree alkyl halide and you are making it perform the Woods reaction in presence of the dry ether, then you will not get RR. You were expecting this process, you were expecting this product, but to your surprise you will find that this is not the answer. Then what will form? Remember, if it is a 3-degree halide, then always the product that is formed is alkane. Alkene. And the dimerized product that you are thinking, that will be a minor product. Clear? So very important, whenever you are reacting a 3-degree alkyl halide with a dry ether in presence of sodium, then it will be an alkane, not the dimerized product. Why? Due to steric factors. Due to steric factors, there will be repulsion. Na? Too many methyl groups or ethyl groups or alkyl groups you are using, so there will be repulsion. So due to that, it will not form the dimerized product. Alright, please remember this. This is very important. Alright, done. Now next, we have seen this all for two different molecules. What about we talk about things in a same molecule? Then it is called as intermolecular Woods reaction. Intermolecular Woods reaction. That means within the same molecule, if Woods reaction is happening, like, why am I drawing a square? I am drawing a square for a reason. This is a square. It's not a square. Looks like a square, but square है नहीं. ये है cyclobutane, right? So if I am making this compound twice, so do I need to take twice? Not need it. Same compound. One time only I will take. Plus Na in presence of dry ether. Then do you know what the product will be? The product is going to be this. Let us assume that we have a halogen over here and we have a halogen over here. Then what will be the product? The product will be nothing but plus 2 NaCl. What did I do? The question is, what did I do? Acha, it was X. So 2NaX. This type of question requires no common sense. No common sense also. Just diagram, draw the line. Wherever is the halogen, just remove that and just join those two positions by a line. That is going to give me the answer. Another question let me do for you all. Suppose you have CH3, CH2, Achha, not CH3, CH2Br, CH2, CH2, CH2Br, and you are doing the Woods reaction in a dry ether. What it will form? Achha, I am lowering the font a little bit. What it will form? See here, CH2 removed, CH2, CH2, CH2. This will join with this one. So can I write in a better way? Can I show this? Yes, I can show it in a better way. How? Instead of writing like this, what I can show is, tell, can I show it in this way? Do you have any problem with this? No. Why will there be problem? Both the side B are moved out and they joined. So they join to form a square. Four carbon atom is 4 corners square ছাড়া আর কি হবে? Rectangle তো it cannot form over here, না? Clear? Clear with intermolecular Woods reaction? Any doubt? No. No doubts. I hope it's clear. Alright, next we are going to study about Wood's fatigue reaction. Let's know about Wood's fatigue reaction. Remember, it's not FITTING. It's not fitting. It's fatigue reaction. Alright. So Wood's fatigue reaction is a Wood's reaction of a different kind. Like here we will take one RX and another one we will take is a aryl halide. So both the molecules will not be of alkyl halides only. That means one will be a haloalkane, other will be a haloarene. Last time in Wood's reaction, we have taken both haloalkanes. Here, one haloarene, one haloalkane. Alright, so the product won't vary. The product will not vary. That will be the same. But the reagents or the reactants are vary. So XX will go. So what it will form? This one plus 2NX. Alright, so you can see that there is no variation in the products being formed. Both are combining. Just the reactants are changing. So let's take one example. Suppose we have a CH3Cl. Along with that, I am using, let's take BRI cannot use, sorry, Cl, and in presence of 2Na dry ether I am giving. So this will form toluene and 2NaCl. Alright, this is called toluene. Clear? Wood's fatigue reaction clear? This marks the end of the haloalkanes part. Now we are going to start with the haloarenes part. Okay, so let's begin our journey with the haloarenes. Chemical properties of haloarenes. Chemical properties of haloarenes. So first one we are going to read about is NSR. I hope NSR full form I don't have to say, nucleophilic substitution reaction. Alright, NSR, still I am mentioning it, nucleophilic substitution. Alright, okay. Remember, haloarenes do not undergo NSR at all easily. Haloarenes do not undergo NSR at all easily. Now, in haloalkanes, we have seen SN1, SN2. Similarly, for aromatic system, we will write it as SNAR. That means substitution nucleophilic aromatic. Alright, now in SNAR2, that is in SN2, we have seen transition state. For haloarenes, SNAR2 is possible not under normal conditions, under high pressure and temperature conditions. Okay, SN1, that is carbocation formation. For haloarenes, not possible. Why? Because phenyl carbocation is not stable. Phenyl carbocation is not stable, so it will not, what to say, it will not proceed by SNAR1. So SNAR1 not seen in haloarenes. Remember that. Alright, so let's begin with NSR. First of all, we are going to write down certain points. What points? Haloarenes are much less reactive towards NSR. Alright, because what can be the reason? Any guesses? You all know already. Number one, partial double bond character. Partial double bond character of CX. Right? Second, formation of highly unstable highly unstable phenyl carbocation. Do you get it? Why it does not undergo NSR over here only? Number 3, less polar and shorter length of CX bond. If the CX bond is getting a partial double bond, length has to decrease. Now, হবে তো, length has to decrease because double bond length is lesser than single bond like that. We already have studied in chemical bonding in class 11, right? Okay, number 4. And the last point, repulsion between nucleophile and, understood, benzene ring also has 2 pi electrons. How many pi electrons? 6 pi electrons. So those 6 pi electrons will repel the nucleophile. So there will be a problem. So these are the reasons why haloalkanes are less reactive towards NSR. Alright, please note it down. Okay, pause the video and note it down, then move to the next part. Okay, I hope you have noted it down. So let's move. So points to undergo: haloalkanes, haloarenes do not undergo SNAR1 because of unstable phenyl carbocation formation. Okay, so they do not undergo SNAR1, that is substitution nucleophilic aromatic unimolecular. Okay, next, haloarenes undergo SNAR2 under high temperature and pressure conditions. High temperature and pressure conditions. Right? SNAR2 normally it will not undergo, reasons have been stated before, but under high temperature and pressure condition they can undergo the reaction. So let us write the reactions. You have chlorobenzene, and if you give aqueous NaOH at 623 Kelvin, 300 atm pressure, and H plus, then you will get OH, and this process is famous process called as Dow's process. You will read this in the next chapter, Dow's process. This process is called Dow's process, which is a method of preparation of phenol. This structure is called phenol. I hope you all know that already. This structure is called phenol. So method of preparation of phenol we will learn in the next chapter, alcohol phenol ether. There you also will get the Dow's process. 623 Kelvin, 300 atm pressure, aqueous NaOH, H plus, Cl2OH. Clear or not clear? Clear? Very good. Next point. Presence of electron withdrawing group. Presence of electron withdrawing groups increase SNAR2 reactivity. Means what? This last sentence means what? What have I written and what does it mean? Means a lot. It means if you are attaching certain electron withdrawing groups in the ring, then that particular compound can undergo SNAR2 faster. That means the temperature that you have to give will be lesser. Understood? তার মানে if you are not using only chlorine, instead you are using some electron withdrawing group along with the chlorine, then that will be transforming into the required product faster than this will do. Clear? Like, let us write the reaction to the next page, but remember that is not Dow's process. Dow's process I've already told you. So suppose I have Cl out here and I have, let's take one NO2 over here. So this is electron withdrawing group. So this time my temperature will be 443 Kelvin, aqueous NaOH. Then what I will get? I will get OH NO2. NO2 I cannot remove because that will be there by product. Suppose I am using Cl, NO2, another NO2. Then this same process gets carried out as 368 Kelvin. OH, NO2, NO2. So did you understand that if you are having electron withdrawing groups, then you need to give less temperature. Clear? This is all about nucleophilic substitution reaction which you need to read for haloarenes. Easy? Easy? Good. Okay, the mechanism of the reaction is very simple. You have done in class 11 already. See, you had a Cl along with a NO2 out here. So what happened is basically OH minus, which was present in the solution, attacks. Where it attacks? Acha. Benzene ring I will show like the bonded structure, because this will not work now. So right, so this way the bond broke. So let's take the bond broke this way. So this will attack over here, right? So can I write it like this? Just check it. NO2 minus ClOH, right? Two more bonds are persisting. Now draw the resonating structures. I hope resonating structures you all can draw. NO2, ClOH, another resonating structure. One forms over here, ClOH, NO2. In the last resonating structure, when this comes here, the Cl moves out. Alright, so Cl moves out. So the original benzene was formed with OH over here and NO2 over here. Alright, so this is how the reaction proceeds. This is basically the mechanism which you just need to know. Achha. Two more points that you can note out from here is, remember this is the RDS, these are all resonating structures. So rate proportional to Rx aromatic, as well as concentration of the base. Alright, and second, reactivity proportional to carb anion stability. Why carb anion? Because everywhere you are seeing it is a minus, no, not this minus, sorry, minus, minus, minus. So this is a carb anion stability you have to compare if you have to ever check the reactivity order. Okay. All right, clear with this? Can I move on to the next one? All right, next one. Next one is a special case. Remember, a special case which I will call it as benzene mechanism. What mechanism? Benzene mechanism. Remember it, NSR through benzene mechanism. Benzene mechanism is also known as elimination addition mechanism. Elimination addition mechanism. Why it is called so, that I will explain to you. First, let us understand. So it is also called elimination addition mechanism or benzene mechanism. So NSR is happening through benzene mechanism. Okay, let us understand. We have to convert Cl to using NaNH2 and liquid ammonia. Then I will get, instead of this, NO2. Alright, how exactly this happened? That to understand that, we need to have the concept of the benzene mechanism. So let's understand the benzene mechanism. Acha, NaNH2, I am writing here, NaNH2 gives what? Na plus and NH2 minus. Remember, huh? So now you see, this is a mechanism going on, huh? Cl, NH2 minus. Now, minus attacks where? Minus attacks positive center. So where it will attack? Here the positive center is not available. So that means there will be hydrogen will attack. Gone. These electrons come here. So what it forms? Minus. Understand? Understand it? Right? Right. Right. Now, this minus shifts here. So one bond breaks, this chlorine breaks. That means this chlorine moves out. So what forms next is very important. Have you ever seen this in your life? This is called benzene. This state is called benzene. This is highly unstable. Highly unstable. So this stage is called benzene, where there is triple bond. Now, can you see that during all this time there has been only and only elimination, nothing added, only eliminated. So this part is the elimination part. This part is the elimination part. From here till here only elimination happened, right? No addition, only elimination part. Second part we will see the addition. Benzene is unstable, so benzene cannot stay benzene. Then what will benzene try to be? Benzene will try to get down. How it will try to get down? What am I doing? Benzene. So what will benzene try to do is, benzene tries to break like this. So what happens? Minus, plus. This plus actually does not form because NH2 minus is there. NH2 minus comes over here. So NH2 like this. Okay. Now, just sometime before we saw ammonia molecule going out. How does ammonia molecule look like? Like this. NH, H. Okay, not visible. Wait, just a minute. Now visible, right? Here you see this, here NH3 was also formed. Here NH3 was also formed, which I did not show, but you should know. So NH3, right? Now what will happen is this hydrogen will break up from here and this will come over here. So ultimately I am getting what? I am getting hydrogen over here, NH2 over here, and my bonds are back to back. This is nothing but aniline and this is my required product. Now you see, during this entire time, only addition has happened, no elimination. That is why this is called addition. So that is why this entire mechanism comprises of elimination as well as addition. So this entire mechanism, benzene mechanism, is called elimination addition mechanism. Clear or not clear? So NSR, nucleophilic substitution, takes place via elimination addition mechanism, which is called benzene mechanism. Clear? Alright, so this is done. Next we are going to discuss easy topic EASR, that is electrophilic aromatic substitution. Electrophilic aromatic substitution reaction. Alright, so that means nucleophilic we have discussed. Now electrophilic substitutions can also happen. How that can happen, that you have already done in class 11. So let me just recall that. You used to have benzene and you used to give anhydrous AlCl3 CH3Cl, then just a Cl would enter here, like this you used to do in class uh, 11. Sorry, not a CH, not a Cl, CH3. This used to do in class 11. Now in class 12 what we will do, we will just insert one halogen atom over here. Let's take it as X, and here we will give some reagent. Let us take, we are giving a reagent CH3 and in presence of anhydrous AlCl3. Alright, so what will happen? Nothing, two products will form. One will be CH3 over here and second one will be CH3 over here. Which one will go to a major? This one. Obviously this is a major product and this is the minor product. Okay, byproducts AlCl3 and HCl. Alright, so this you already know. Acha, AlCl3 I have used. There is HX. Alright, so this you have done in class 11, so I don't think I need to repeat it in details about it. Mechanism remains same as I have discussed in this way. Resonating structures you can just draw and you can just do the electrophilic attack. Okay, mechanism refer to class 11. Okay, electrophilic aromatic substitution reaction, I have discussed it in the lecture hydrocarbons, probably either hydrocarbons or GOC. Just go and have a look at that. Alright, not saying the mechanism over here. Okay, different categories were there, like suppose I have to halogenate someone. Halogenation, I am just showing the reaction mechanisms, refer to the lectures. X I am having, I have to halogenate, then what I will use? FeCl3, then I will get XCl plus XCl. Alright, my byproducts are going to be FeCl3 and HCl. Alright, which will be the major? This will be the major product, not visible, sorry, major product. Alright, next after halogenation we have sulfonation. Sulfonation, what do we react it with? We react it with concentrated H2SO4. So X in presence of concentrated H2SO4, reaction happens to give X SO3H and X SO3H. Alright, water. This is going to be my major product. Remember that these mechanisms are already told. Okay, here SO3 is a nucleophile. Okay, next what we have done, halogenation, sulfonation we have done, nitration. Alright, nitration. In nitration what do we do? In nitration we will use concentrated H2SO4, along with that we will use concentrated HNO3. Then what we will get? X will be there, NO2 will be there, adding on with it we will get XNO2, sorry, XNO2. Alright, this is going to be our major product. So these are all easy, which you have done already. Next comes Friedel-Crafts. See, this is all you have done. Friedel-Crafts alkylation and acylation. I am doing all at once. and acylation. What was phenol graft alkylation acylation? Let us just recall it. X, then X, right? This was the case. This is going to be our major product. Secondly, then X, okay, this is going to be our major product. Clear? So this already you have done in class 11. I have got much less to discuss about this because it's already done, right? Alright, next we have some reaction with metals. Reaction with metals. These are also already done. How? Just see. Suppose you have Cl and you are reacting it with CHTCl in presence of not Mg, sorry, in presence of Na dry ether. Then what you are getting? This also I have shown you CH3 plus 2 NaCl. This is nothing but Woods fatigue reaction, right? Woods fatigue reaction. Woods fatigue reaction, right? Okay. Next reaction we are going to discuss is fatigue reaction. Fatigue reaction. We have discussed three types of Woods reaction. One is Woods reaction, one is Woods fatigue reaction. Now only fatigue reaction where both the molecules involved will be a haloarene. Both the molecules involved will be a haloarene, right? So that's going to be a 2Na dry ether. That's going to be a biphenyl. This is going to be a biphenyl plus 2Na. Alright, this is a fatigue reaction. Clear? Alright, we have come to the end of the chapter almost. Next, a little bit, a small topic is left, that is your polyhalogen compounds. Polyhalogen compounds. This I will not tell much about it because this is more of ratta than learning. So just few things I will discuss about polyhalogen compounds. You will be reading it in your home. You will be reading it in your home. Read. I will be explaining just few points out of here. One point I will pick up is your DDT. One point I will pick up is your phosgene and all. Okay. See, chloroform is this one. This is called chloroform. Remember, chloroform was formerly used as anesthetic substance. That means it used to, make people unconscious. But now alternative has been found out, so we don't use chloroform, right? No, see, things have a negative positive side. Positive side is for the doctors, negative side is for the kidnappers. So they used to use chloroform. Now they don't use chloroform. All right, okay. So chloroform, when reacting in with O2 in presence of air, obviously air, or rather than air, I can write light. Then it forms COCl2 along with ACl. This COCl2 is called phosgene, which is a toxic gas. Toxic gas. Okay, the question that arises from here is why phenol is kept in dark colored phenol, I'm saying. Why chloroform is stored in dark colored bottles? Answer is this. Okay. So what the question they will ask? Why CHCl3 is stored in dark colored bottles? Dark colored airtight bottles. Airtight bottles. Answer is this given. Okay. Second thing I will be talking about is freons. Freons. This is a new topic. Freons are basically chlorofluorocarbons. Have you heard chlorofluorocompounds? Right? In geography. So chlorofluorocompounds. What am I writing? Chlorofluorocompounds. Chlorofluorocompounds of carbon. Clear? So they are basically chlorofluorocarbons of carbon. Which number of carbon? So specifically it is chlorofluorocarbon compounds of methane and ethane. Okay, remember they are non-reactive, non-corrosive, and easily liquefiable gas. Easily liquefiable gas. Where are they used? Used as refrigerant. Okay, common one, freon 12. Okay, remember another one, produced by Schwarz reaction. How many of you remember Schwarz reaction? And how many of you have already forgotten what was Schwarz reaction, method of preparation of fluoroalkanes? Right, how it is prepared? It is prepared by reacting CCl4 with SbF3. Then you get freon 12, CCl2F2. Okay. Next I will be talking about is DDT. DDT is the most common DDT that we use is P dash dichloro diphenyl trichloroethane. Alright, P dash means both are at para positions. Okay, dichloro diphenyl trichloroethane. So basically the reaction is CCl3CHO reacting with 2Cl in presence of concentrated H2SO4. This substance is called chloral. Okay, so chloral reaction. So reaction is with chloral and this. Okay, CCl3CHO. So what happens is CCl3CH. Instead of this 2O, instead of the double bond O, there it gets two benzene rings. I am very bad at drawing benzene rings out there. Okay, basically it will be a para position benzene ring. So let's just make two copies out of this. Oh. Okay, and let's shift another one. So this is how DDT looks like. Okay, you have to practice the structure as well as the compounds. All right, so this is all about, you have to read from this chapter. So thank you for staying till the end and listening to the lecture. Please read and practice. Okay, practice the reactions. Reading and practicing will help you to crack this chapter. All right, so I hope you have enjoyed learning this lecture, enjoyed learning this chapter. See you soon with the next chapter on our channel Argentum Chemistry. Bye bye.